In this video, I'll present some of the characteristics and uses of the C++ programming language, and I'll identify the main concepts behind its implementation. So let's start off by talking about its basic language characteristics. So variable types are statically typed, so they're checked at compile time, and you need to be specific about what a variable is used for, what its type is. This helps protect against accidental use, and it improves runtime overhead. So we have user-defined types that are central to C++, like classes, structs, unions, and templates. And C++ takes a balanced approach between elegant and affordable in terms of readability, maintainability, and efficiency. Now, you'll often hear people talk about C++ being cross-platform. The compiled result is not typically cross-platform, so we have a binary that's specific to a particular system, but the language operates at a degree of abstraction above the system. It's not an assembly language with processor-specific directives and registers. So compilers are written for just about every modern computing system imaginable, from low-powered smart cards and microcontrollers to PCs and GPUs and supercomputing clusters. Now, C++ is used in a wide variety of applications. It's not just specially built for one particular area of application. It's not like a SQL nor an assembly language. So there is a bend in C++ towards systems programming and direct hardware access, but that's not due to the language itself. It's more due to the connection to the C language historically, and its emphasis on low-cost or zero-cost abstractions. And also note that C++ is case-sensitive. So variable names with upper and lower case, if they spell the same name but have different upper and lower cases, they're different variables. Now, you can write C++ procedurally, just as you would C. Although you would miss much of its power, it's perfectly valid. C++ supports many approaches and styles, including procedural programming. You can do object-oriented programming, so you have it's modeled around objects instead of actions. So we have object hierarchies, encapsulation, inheritance, and polymorphism. So we have generic programming, so we have algorithms that are typed when they're instantiated. So methods that can operate on a variety of types, including C++ templates. So what are some of the cornerstones of object-oriented development in C++? Well, we have encapsulation, so we bind data with functions that manipulate it. So we have objects with constructors and destructors and operator overloading and basic member variables and functions. We have data hiding, so it hides the details of an object to other objects that derive from it. So we have things like public and private methods and protected access control. We have inheritance, so objects take on the properties of existing objects. So we extend the concept of a particular object into more specific refinements. And finally, we have polymorphism. So an object can take on many forms. So an object's implementation can share elements from a particular base class, as you see here. Objects dog, cat, and bird share elements of the class animal. And in terms of interface, different derived classes can be used through their base classes interchangeably. So we can access a list of animals that are either dog, cats, or birds, but we access them through the animal object using their methods like move and speak. What are some C++ libraries and standards? Well, the core language of C++ are the C++ built-in types, operators, and statements. It has no built-in high-level objects or types or primitives in its core language, not the high-level stuff, just low-level built-in things. It just has the fundamentals of the language itself in the core language. But we get this defined, originally was defined in the ANSI standard C++ in the late 1980s, and then we developed into more high-level ideas that got included in the standard library, which is all written in C++. So this has containers, algorithms, and complex types, all provided in the C++ standard library. What was called the standard template library, or STL, became part of the C++ standard library in 1998, and this was the first ISO standard. C++ was originally created by Bjarne Stroustrup in 1979, and it started as C with classes, and then was extended from there, only getting its C++ name in 1984. The ISO C++ standard was introduced in about 97 and finalized in 98, and by 2011 we got the ISO C++ 11 standard, which incidentally, after I began programming in C++ in the mid-1990s, and then moved away from C++ programming in the mid-2000s, I came back to C++ in about 2010 ahead of this standard, which reignited my own excitement for C++. Now we have further improvements with C++ 14 and C++ 17 ISO standards, adding new features to the language and standard libraries, but while maintaining its core concepts and design approaches. Now, C++ is a general-purpose language, so its use is wide. So we have software applications, many high-level software applications like major tools such as word processors, spreadsheets, and web browsers, email clients, and other major applications that we have on desktop computers are often written in C++, and many modern games are written in C++. We have devices and systems programming, so we create device drivers, device firmware itself, microcontrollers, even smart cards you use in your bank or credit cards. Because of the low-cost abstractions, C++ compiles down to an efficient implementation for many of these platforms. Then we have GUI applications for Mac, Windows, Linux, BSD, Unix, PCs, and workstations. So it's not just limited to a small subset of these. It's not a specific language that only works on a particular operating system or particular windowing platform. It's pretty much across the board. Now, if you use libraries for languages like Python or R for things like machine learning and data science, you'll often see many of its library implementations done in C++, and this is primarily for performance reasons. So many of the implementations for data science and machine learning use GPU libraries for performance reasons, which have interfaces that are written in C++. So you write a lot of the implementation code in Python or R, but the underlying libraries are written in C++. And that concludes this introductory presentation on C++. Eclipse is a popular open source IDE, or integrated development environment, that can be used to develop for many languages including Java, C, and C++. In this video, I'll present how to download and install Eclipse for C and C++ development. So if we go to the eclipse.org website and go to the download section, we can find our download for installing Eclipse. Now, if you need other information on Eclipse documentation and whatnot, you can get it from this website. Now we go to the downloads, and it's going to recommend a location that's close to us. So it says my download file is here. So it downloaded from Canada and a particular host of the Eclipse install win64.exe. Or we can select another mirror and choose a location that may be more appropriate to us, like if I want to download it from the University of Waterloo site. So all these mirrors give us close locations where we can download Eclipse. Now, I've already gone ahead and downloaded it before this, so we don't have to sit through the download process. So if I go to my downloads, you'll see the Eclipse install, Eclipse inst win64.exe. Now, before we install the IDE, before we install Eclipse, we need to install Java, either the JDK, which is important if you're doing Java development, or the JRE, the Java Runtime Environment, if you want to run Eclipse for other development, like C++. So I've also already downloaded the Java Runtime Environment. So I've downloaded let's get out of the menu here. I've already downloaded the Java SE Runtime Environment 8, and I've downloaded it for the 64-bit Windows. So I've downloaded this one, this JRE 8U144 Windows x64.exe. So if we look in my downloads, you'll see it here. So let's open the downloads folder, and we'll start out by installing the JRE. So that's the file right here, JRE 8U144 Windows x64. So I double click on this file, and we'll go through the install process. So I'm going to allow this to make changes on my computer because it's going to install this software. And now we'll just install it in the default location. So I'll click install and I'll let it do its thing. Now it's completed and it tells us we have successfully installed Java. So we'll close this. And now that Java is installed, we can go to our Eclipse installer. Our Eclipse installer here, Eclipse inst Win64. So I'm installing it on Windows. Now, obviously, if you have a different platform, you can choose the appropriate installers and it will work just the same. Eclipse runs across many platforms, including Windows and Linux and Mac. So if you're running on a different system, then just download the appropriate installers and it should work just the same. So I've double-clicked on the Eclipse installer. Now that the Eclipse installer is open, it gives us some choices. The Eclipse IDE for Java developers, for Java EE developers, C, C++ developers, etc. Of course, in this video, we're focusing on C and C++, so we're going to install this particular Eclipse IDE for C and C++ developers. And we're just going to give it the default installation. I'll do an install, and we'll let it create a desktop shortcut and a start menu entry. Now you can read this user agreement and click accept now, and it will carry out the installation. Okay, now that we've launched the installer, one thing I recommend doing before you proceed is going to this menu here, this hamburger menu, and if there's an update available, you'd see it here in this menu and you can click update, and that will update the installer to the very latest version before you continue with the install. Now, in this case, I've already done it. So you can go to, once you've done that, you go and select the Eclipse IDE for C, C++ developers, and click on that and do the install. You can select the version whether you want 32 or 64-bit, depending on your system. In this case, I want the 64-bit version. It'll ask the location of your Java runtime environment, your JRE, which it's found it here in Program Files, Java JRE, the one I've just downloaded. And then it gives an install location. So I've clicked install, and it's going to carry out the install process. Now that the installation is completed, we just click the launch button, and we can launch Eclipse for the first time. It'll ask us on the first run, it'll ask us where to put the Eclipse workspace, and I'm just going to use this as the default and not ask again, and click launch. And now we've launched Eclipse. We can click it to maximize it, and we get a welcome screen with some information about Eclipse with tutorials and samples and the ability to create new C and C++ projects. Now, the installation may have been a bit slow, but once it's installed and you're up and running and launched Eclipse for the first time, you're ready to start developing. And that concludes this demonstration on downloading and installing the Eclipse IDE for C++. Eclipse is an open source IDE for developing applications with different programming languages, such as Java, C, C++, and PHP. In this video, I'll explain how to create a new Eclipse project. Now in this video, we're going to look at creating a new C++ project. Now, if you've just installed Eclipse and you still show the welcome screen, you could always turn it off, and quite often people do turn it off. But if you do have it up, you can go select from the list, create a new C++ project. Now you click it and it will bring up your create project dialog. Now equivalently, you can go up to the file menu and select file new and hover over new, and it will give you a list of different types of projects you can create. Now I'm going to select C++ project. Now if you want to get to this quicker, you can always use the Alt-Shift-N shortcut and bring it up immediately. So there's a nice shortcut key. You can get to it quicker if you're creating a project, or you can just select File New and C++ Project. I'm going to call this project just Example 1. I can select the location of it. The default location is in the Eclipse workspace directory, and under the name of the project. So example 1. You can select a project type. For this, I'm going to select an executable Hello World C++ project. So it's going to give me a basic boilerplate C++ project. And I'm going to select the cross-compiled GCC as my toolchain. So the toolchain is basically the compiler or compiler and linker, whatever tools that surround building your C++ project. Now I'll click Next. And it has some information here. The author I can put in. These are all these are non-mandatory settings. I can just skip over, and I can select the configurations, debug, or release. I'll just leave them both selected. And I can put in some information about the GCC compiler. So I need to select where it's stored on this system. And then once I've selected the compiler, this cross GCC command for compiling, I can hit finish and it will create the project. Now, once I've finished creating it, I need to bring it up. So I need to go over to the menu and bring up some information about my project. Now, I might just want to close the welcome screen. Let's close this, and we can see our project. Now, there's a few errors here because I haven't set up the compiler, so it doesn't know where the G++ compiler. So this, on a fresh install of Eclipse, it expects the C++ compiler to be already installed in the system. As such, I cannot compile using Eclipse for this example anyway. And that concludes this demonstration on creating a new project with Eclipse. The GNU Compiler Collection, or GCC, are tools and configuration options that you can use to compile and link C++ programs from the command line. In this video, I'll demonstrate how to use the GNU C++ compiler, or GCC, to compile an executable file from the command line. I'll be demonstrating this on an Ubuntu server install, so I'll use Ubuntu-centric methods to install the GNU Compiler Collection. That is, I'll install it using apt. Other Linux systems, BSDs, Unixes have similar methods of installing using the system-appropriate package managers. So I'm going to use the apt package manager, so I need to run it using root. So I'll need to do a sudo apt install, and I want to provide the build essential, which will install the GNU compiler collection along with some other basic tools for compiling, for building on a Ubuntu system. I also like installing an editor. Instead of using the built-in VI or Vim, I like to use the Emacs24 NoX, so I have a terminal appropriate install of Emacs. That's what I'll use for an editor. So I'll run this install, and it's going to install the packages I need and a few of the tools, including Emacs. And when it completes, we can create a small C++ program and test out the compiler. So now that it's completed, I'll type clear my screen from all the information from the install. And now let's test our GCC. So one thing you can do is just do GCC space hyphen version. And that will give us the version, or GCC, double hyphen version. So make sure you get the two hyphens in there, GCC double hyphen version. And that tells me the version of GCC I'm running on this version of Ubuntu, this 16.04, and GCC version 5.4.0. So let me clear this again so we don't have all this info showing. And we can create a very simple C++ application. So I'll do Emacs, and I'll call this hello world.cpp. So I'm going to do a few simple things. I'm not going to talk about too much about what I'm going to do. I'll do an include on IOStream, and then I'll do using namespace std for standard, and I'll do int main, and then just a cout of hello world. And I'll put a carriage return in the end, close it with a semicolon, and close our main function. Now I'll save it, close it. Now I'll do a clear, again, to clear the info from the Emacs editor. Now we can do g++ hello world.cpp. And now let's look and see what it's created. So what it's done, it's compiled hello world.cpp and compiled the output into a file called a.out. Now it just uses this default one because we didn't specify anyone. So if I type a.out, it runs hello world. Now if we'd like to specify the output, we could do g++ hello world.cpp, and we can just call this program, so we just give it -o and then HW for hello world. Now if we look in the directory, we see that there's a new compiled binary HW, and if we run it, h./hw, it prints our hello world message. Now there's a few other common options that you should be aware of right off the bat. One is g++, so -WALL for W all. So this is the warnings option. So this will output all compiler warnings. So let's do hello world, and we'll overwrite our HW. So hello world.cpp -o HW. So there were no warnings, and it compiled fine. Another thing you can do is include debug symbols. So you want to be able to debug your code, say using the GNU debugger. Well, to do that, you need to have debug symbols. So to have that information when you compile, so if you want to compile it in debug mode, do a -g, and then compile it as usual. And now if we look in the directory, you'll see now one interesting thing. So you'll see here, this version of HW is 20,000 bytes for a very simple compile. If I compile it without the -g switch, let's compile it again and check in the directory using ls-la so we can see the size. It's only 9,056. So when you compile it for debug using -g, your output size will be much larger because it's included all the information to debug your code line by line. If you omit the -g, it doesn't need to include that information, and your output binary is smaller. And that concludes this introduction to the GNU compiler collection to compile C++ programs on Linux. In this video, I'll demonstrate how to set up a new C++ project in Visual Studio, how to switch between solutions with multiple projects, and how to run and debug projects. So we've started out here with our Get Started start page. So when you launch Visual Studio Professional Edition for the first time, you'll see this page. You'll also get developer news from Microsoft in here, and you can easily expand or hide it with this arrow if you don't want to see it. We have a few options here when it comes to projects. If you have existing projects, you can open them right from this start page or create a new project. You can also access these functions from the menu if you set Visual Studio not to show the start page when it first loads. That's fine. If you have any recent projects, they'll show up here as well. I'm doing this demo on a fairly fresh install of Visual Studio. The only time I've run it before is to set up a few of the options, such as the font size that I'd like to have in my Visual Studio. So this is literally the second time I've run Visual Studio on this fresh install. So let's start off by creating a new project. So I'm just going to go on the start page and click the Create New Project link. So it'll take a second to bring up a dialog that will guide me through setting up a new project. So it's the first time, so it's a little bit slower to initialize. But once you've done it it is a little bit quicker. So it gives me some options of the different types of projects: Visual C#, Visual Basic, Visual C++, JavaScript. Now, since we're doing Visual C++, I'm going to hide the Visual C#, open Visual C++, and let's look at the General tab. And so we can do an empty project, a makefile project. There's some different Windows Desktop, Windows Universal. So let's just look at the different ones: ATL project and test. So what I think I'd like to do is create an empty project. So I'll just leave the name project 1 and click OK. So that should create a new file, a new project with the appropriate files. Now it's successfully created the project. I have it over here. Now I can right click on the project and do some things like build it, which won't do very much right now because there is very little in it. There's nothing in it. So we can just leave that here, and we can go to our source files and we can go add a new item. Let's just add a new item. And it's going to give us some options. I want to create a CPP file. Let's just call it source.cpp. Just leave the defaults in for this example project. And it should include my file, bring up the code, and I'll just do int main, and that's it. We could leave it empty. We could put in a message. Let's just leave it empty. Save the file. I just did a Control S to save it using the shortcut key. Now another thing you can do to build it, you can do a Control F7 to compile it, or you can go up to your build menu and say build solution. So there's a few options on how to build it or build projects. Now we have a solution here. You see in the Solution Explorer, we have a solution, project 1. So solutions we can have multiple solutions in here, but we can also have solutions with multiple projects. Now you'll see here, the build has been successful. If we look in the output window, build 1 succeeded. So everything seems to work fine. Now we could go to some other menus. We could debug it. So we could do F5 to start debugging, or we can select it from the menu, and it will run it in debug mode, and it will recompile it if it needs to when we click run and debug. So if you've made any changes, it will pick up those changes, recompile, and then run it in debug mode. Now it does show me some extra information when I do run it in debug mode, and it just ran it. There was no breakpoint, so it just ran it, and then it exited because the program does nothing. It just launches and then it returns, and that's it. Now let's add another project. So let's do a file, new project, and we'll create another empty project. So this one will just be called project 2. Click OK. And you'll see we have solution project 2, but we no longer have project 1. So that's been closed. So we have our Solution Explorer here. And what we can do is add another solution or existing project and select the project 1. It's going to go into so we go to project 1 and we select the project file and open. So we have a solution here with 2 projects. So we have project 2 and project 1. If I double click on project 1 or right click and say set as startup project, or I can select to build this particular project separately, or I can select scope to this and it will scope to this particular solution, or I can go back. So you can navigate your projects and solutions here in the Solution Explorer and pick which one you'd like to compile or run. You can hide and show them and set them active depending on which one you're working with. So it won't necessarily build all of the projects, just the one you've selected on. So I can say build or rebuild. So it's building project 1. If I right click on project 2 and say build, it will build project 2. So those are some of the things you can do with adding projects and switching between projects with Visual Studio. And that concludes this demonstration on C++ projects in Visual Studio. In this video, I'll break down the elements of a C++ program. So first, every program needs an entry point. In some languages, like Python, it just starts executing the file that you execute. It starts interpreting it from the first level, whatever code it sees, it executes. But in C++, we need a main function. So this is the entry point to any C++ program. So you cannot call main from anywhere else within your program, not from main itself recursively, definitely not, and not from any other function you define. So main is only called as an entry point from the operating system or whatever calling procedure calls your program it calls the main function. So even if in this case we define it as int main, so this is the simplest way we can define main. If we have any command line arguments that we'd like to pass, which I won't get into in this video, it goes as function arguments in these parentheses. And then we have the code block itself. So it starts with a brace and ends with a brace. So this defines the statements, the body of the function for main. And it's declared to return int, but main has a special status in C++. If there's no return in it, it implicitly returns 0, which means success. So if it reaches the end of the function block and doesn't see return 0, it returns it implicitly. So you don't explicitly have to provide it, but you can if you want. If you're used to seeing it that way or for legacy reasons, it's fine to have it, but it's also fine to leave it out. So as I've declared main here, this is the simplest C++ program possible. Now let's expand it a little bit. So we often need to bring in function prototypes or declarations from other files. So what we do is we include them. We do this by using a hash or pound sign or number sign include, and then we open up these less than greater than symbols. So this encapsulates what we're going to include, and I'm going to include IOStream. So this comes from the standard library. So this is a standard input-output stream library provided in C++. So this gives us access to functions to input and output things. Mainly, we use it in simple programs, we use it for the cout function. So we do standard std : so this defines the namespace the function comes from, the function cout, a double less than operator, and then the string we'd like to output. So the strings are in double quotes, and then we end each statement, each line of code, with a semicolon. Now, we could put multiple statements on a single line, but it's typical practice in most cases, to have each statement on a line, and we must end each of these statements with a semicolon. So we've included the IOStream library, which gives us access to this standard namespace std, which we specify with std : the function cout, an operator that the function takes, that this object cout takes, which is the double less than symbol, and then some string in double quotes. So this is a typical first example hello world of a C++ program. Now, a couple other things I'd like to mention about program structure in C++. Comments. Single line comments begin with a double slash, so this is a single line comment. And we can do multiple comments if we want to have, all these lines as comments. But more simply, we can have multi-line comments. So if I leave that single line comment, I'll start a double or a multi-line comment with a slash %, /* and then */ to end it. So anything between the /* and */ is a multi-line comment. So I can put some comments in here. This is comment, and I'll shorten it, and you'll notice there's a little box here with a line in it next to this comment and also next to this function. So one of the features of Visual Studio is that you can collapse these multi-line comments and functions. So I can collapse the comment, collapse the function. If I have a lot of code in there I'd like to hide, I don't want to visually look at it, I can collapse it so I can see what I'm focusing on a little bit easier. So it provides this feature to collapse and expand these blocks, either blocks of comments or functions. So that's a very basic structure for an initial C++ program. The last thing that remains is to compile and run it to make sure we've done everything correctly. In Visual Studio, you can go up to the debug menu and select however you'd like to run it. So start debugging or start without debugging. We're going to start it without debugging. Now you might have seen briefly in the menu, so debug, and we go down to start without debugging. Or more often you'd want to use the shortcut key, this Control plus F5 is the default. So if I'm here in my code and I make a few changes, what I'd like to do is run it. I would just press Control F5. And then if it needs to build it, it will prompt me. And I click yes. Or I can not show it again and just have it build automatically, which I think I might do. Is how I usually set it up myself. Click yes. And it's building the project. And then it will run it. Now it's a command line program, so it launches this command window with the output of my program. So I have hello world as I wrote it in the cout statement. And then it says press any key to continue. And then I just hit any key. And it closes the command line window, the terminal window, and it brings me back to my code. And here in the output at the bottom, when you build something, it shows the compilation information and whether the build was successful or not. And that concludes this demonstration on C++ program structure. C and C++ have some similarities. You use a similar program structure and some of the same essential syntax, but there are many differences. In this video, I'll cover some of the basic differences between C and C++. So the first obvious difference is that C++ has true classes. So these are user-defined type representations that have tightly coupled functions and operators, which we don't have in C. In C, we have objects called structs, which don't have member functions. So here we have a class, a user-defined type in C++ called myClass. Class members have attribute visibility, such as public and private. So public members are accessible to anyone who instantiates a class, and private members are only accessible. These are variables that are only accessible within class members themselves. So these member functions, like the constructor, the myClass constructor, and the tilde myClass destructor, where we initialize and deinitialize or clean up our classes when we're done with them. And then we have member functions like this myFunction, and classes can also have virtual functions and overloaded operators. So the C++ class is a powerful tool with many qualities. On the other hand, C is object-based. So C has structs, which have member variables, and that's it. Like this struct myStruct, which has an int a and a char b. And that's it. So the power of C comes not from how comprehensive these objects are, but it comes from the functions defined to manipulate its objects. Now in C++, we also have structs, but it's just a class whose members are public by default. Enumerations is another difference between C++ and C. So in C++, enumerations are scoped and strongly typed. They can be statically cast to ints, but they're not assignable to ints implicitly like in C. So in C++, we typically use enumerations called enum classes. Although it does have C-style enumerations, the preferred method now is to use an enum class. Whereas in C, we often typedef our enums. So we have this typedef enum, and then some definition here with our enums of false and true. That's of the typedef boolean. Now, one thing to mention here about this boolean enum, which we may have done in C previously, the bool type is a fundamental type in C++, which can take on values like true and false. Now, the enum class, like the enum class size here, these objects are not particularly considered ints by default, or we can't access them that way because these enumerations, these enum classes, are checked at compile time. Now, one similarity between C and C++ is that they both rely on the main function as their entry point, and their main functions are defined equivalently. So the main function you'll see in C and C++ programs. Now, assigning or allocating memory dynamically is very different between C and C++. In C++, we have the new operator, so we take this char star s and we make it equal to a new char, and we specify the size. In this case, we use this array syntax, so we have the bracket 100 close bracket, and that assigns an array, or assigns 100 characters, or allocates space for 100 characters that can be addressed by this char star s. And then we have a pointer to t, this char pointer t or char star t in the C style, which we use malloc. So here we cast it to a char star, which may or may not be required by your compiler. We do a malloc, we specify the size. In this case, we want 100 elements of size char. So this is the space we set aside. Now in C++, it infers that from what we've expressed here. But in C, we have to specify the size in this call to malloc. Now how we clean it up is different as well. So in C++, we allocate with new, and we clean it up or free it with delete. Since we've allocated it using this bracket syntax with 100, we delete it using the double brackets here at the end of delete, and then our variable name. And then in C, we just call the function free. So we call free, give it our variable. Now, one thing to make absolutely sure is that you should never mix these in your program, and never try to free something you've assigned with new using the C style free function. And if you've done a malloc to allocate something, never try to clean it up with delete. They won't work. And then finally, one of the other differences is just basically how we output to a console window or to some output stream when we're outputting strings in our program. In this case, the C++ style is to use the cout. So we have std : from the standard library. Using cout, we give it this double less than operator, which in C would be the left shift operator, but here we've overloaded it to take a string, and we give it this hello world string. So this is the C++ way of doing it with cout. And in C, we typically rely on the printf function. So we do a printf and give it the string that we'd like to print. Now I'll mention a couple of more differences. One is dealing with parameterized types. In C, this often involves function pointers or void pointers to deal with different types. So things that can operate equally on, say, ints or doubles or any numeric value. So we do this in C often without compile time checks, and occasionally we use different implementations for each type that we're dealing with. In C++, we use templates. So we get function templates and object templates that do get checked at compile time. And finally, one last major difference, which I won't highlight, is exception handling. In C++, we have proper exception handling where we can throw and catch exceptions using try and catch. But in C, we don't have that mechanism. Errors are caught by inspecting return values from functions or looking at return codes from functions, or by checking if a global error value has been set somewhere. So there are many other differences, but these are the most obvious and frequent ones we come across. And that concludes this demonstration on some basic C++ syntax differences from C. In this video, I'll demonstrate how to work with two basic I/O streams of cout and cn, and how to use them to read and write formatted character streams from the console. So our program will start off by including our string library, because we're going to use a string, and our I/O stream, which is what we're talking about in this video. Now, to keep things a little bit simpler in terms of typing, I'm using namespace std for our standard namespace, so I don't have to type it everywhere. And now in our main function, let's look at what our code's going to do. So I start off by using the cout output stream from the I/O stream library that we've included. So cout has an operator, this C-style left shift operator, so the double less than symbol, and then it takes whatever string or whatever object that we want to output as a character string or character stream to our console. So in this case, hello, space world. Now, note that carriage returns or end of lines are not inserted automatically by cout, and we have to insert them manually. So that's why I have this \n here. So that will carriage return on the console to the next line. And then I do a cout on hello, space. And then I give it another left shift operator, another double less than symbol, and output the string world, ! and then another operator, and then end L for end line. So this is synonymous with \n, so I can just type it as this end L, or I could change this to the string double quotes \n double quotes. So those would be the same thing. So let me put it back to the way it was. So those are two ways of carrying out the end of line or carriage return. Now I'm going to initialize three variables, an int called intval, a double called doubleval, and a string called str. So these are going to take the inputs of our cin. So we have a cout that prompts us what to enter, so enter an integer, :space, and then we have our cin, which takes the intval, and then we do the same thing for the doubleval and the string str. So the cin looks for input and formats it into the variable that we specify. So we'll get enter an integer, we'll type a number and hit enter, and then cin will put the value that we entered into this variable. Now down here on line 23 near the end, the penultimate line before the return, we have our cout, entered, and then we give it our operator, intval, the operator again, another string, so that we have this formatted output here, our doubleval, comma, our str for our string, and then finally our end line or end L. So let's run the code. I'm going to type a Control F5. That will compile and run our code, and we should get a console window. So we have our first two lines outputted are hello worlds. Now you'll notice the first one I didn't put an exclamation mark in, and the second one appears on the second line because of the carriage return, this \n, and hello world here, it outputs just fine even when we separate it using the cout operators. And now we have enter an integer. So I'm going to enter 10, and then enter a double, say 1.1, and some string, let's just write the word test. And then we get you entered 10, 1.1, and test. So that's pretty much as expected. Now there's some ways to format output and redirect output to other output streams like the cerr output. So the cerr is another alternative to cout. Instead of putting to our standard output, it puts it to the standard error as determined by the environment or the OS we're working in. And that concludes this demonstration on C++ I/O streams. The C++ preprocessor allows you to run code and apply definitions in a precompilation step. In this video, I'll demonstrate how to use the C++ preprocessor to declare constants, constant expressions, and preprocessor macros. So the contemporary wisdom with regards to using C-style macros, like your typical defines, is don't use them unless you have to, at least not in the old way, so avoid them if you can. So what you want to use is consts or const expressions instead of C-style preprocessor macros. So if you're using C++, prefer to use const expressions. Now, when you should still use defines, most often you'll see them as include guards. So this is something that you will see quite often. Now, in this case, I'm using Microsoft Visual Studio, and it uses as an include guard the pragma preprocessor directive. So you'll see this is not a portable way of doing this, but this is a very common industry-wide standard that's used as an include guard. So it's called pragma once. So when you add a header to a project in Visual Studio, it adds the pragma once directive to it automatically. So what this does when you add a header to a file, or if you include it in many files, it only gets processed once. So that saves the compiler much work, and it speeds things up, and it makes sense that you access a header file from multiple source files, but you only process it once. So that's what the pragma once directive tells it. So it's an include guard to make sure that the code inside of it only gets processed once. Now, I say it's non-portable, so it's not always portable, but major compilers like Visual Studio and GCC or Clang, they all support this pragma once directive. Now, if you didn't have this, what you'd want to do is include an include guard using a preprocessor macro. So you'll have something like if not defined or if ndef, and we give it, let's see, std_afx h, you'll see something like this, and then we'll do define xh, and then down at the bottom, we'll have ndif. So what this does, it says that if we've not defined this std_afx_h, then define it, the code gets processed, and then we get ndif. So the next time our compiler sees this file, it will see that it has been defined on the previous include, so we don't need to process the contents again. So that's one preprocessor macro that you should be aware of and that you'll see come up very often. And you won't always see, you'll either see this or the pragma once directive that I erased previously. So we'll just leave it like this, that should be fine, and we'll go back to our source file. So I mentioned the const expression. So this is something that's available in C++ 11 or later, and it allows you to declare typed expressions. So this is not the best way to define pi. I'm only doing this for example. So we have const expr double pi equals some pi to some fixed number of decimal places. So we use const and or const expression to assign values to symbolic names. So this gets, remember, this gets processed by the preprocessor. So it's done at compile time. It's not something that's evaluated at runtime. So you do get this evaluated at compile time. And now we'll go to our C-style preprocessor macro using hash define or number sign define. And I define a function or this macro function called radians, which takes a variable called deg for degrees. Now you'll notice none of this is typed. So there's no return type. There's no type on my input value. And I'm accessing these values without much indication of what. So this doesn't look like C++ code. So if we can have a preprocessor macro language that uses C++ code, surely it should be preferable. But it does support this, and you can still define macros this way, but it's not recommended if you have C++ 11 or later. If you have const expressions, you probably shouldn't do it like this. But, and you know, there's no return statement here, so we don't say we're returning this value. We're just putting this value in, this expression in, and we expect the compiler to know what to do with it. So here's the same thing done, the same conversion, the same function done using the C++ style const expression. So we have const expression, const expr, the return type double, and I'll call this one to differentiate it deg to rad for degrees to radians, and it takes a const double d. So we type our input variable, our argument to this const expression, and then we return using standard C++ code, d times pi divided by 180. So that looks like normal C++ code, except that it's qualified as a const expression. Now, let's get into the main body of our code. I want to show a few of the things you should be aware of when using const expressions. Now, if I declare a volatile variable, this double d1, set it to some value, and I try to use it in a const expression, I'll get an error. So if we go down a few lines to line 21, you'll see I have const expression double d4 equals d1, our volatile variable, times 42. So there's a little IntelliSense error underneath the d1 because it's a volatile variable, and I can't mix volatile variables with const expressions. But the same applies for regular const. So if I have const double d2 and I try to use that in a const expression, I also get an error. What I need to do is declare the variable as a const expression so that I can mix it with other const expressions. So assigning a const expression to another or using it in a computation with another is okay, and all of this gets done at compile time. Now I've declared two more, const expression double dx equals deg to rad with the value 42 as the degrees, and it will return the radians. So this will get processed and evaluated during compilation, but I can also do this using a regular define. So radians is defined using a C-style define preprocessor macro. And I can assign it to a const expression. So that's okay. It's not ideal, and I'd recommend doing it this first way, but you can do it that way if you need to. If you're mixing modern code with legacy code that you have, where you do have macros defined using the older style preprocessor macros. Now, a couple other things before I run the code and before I wrap up this demonstration, let's look at a couple of standard predefined macros, namely file, line, time, and date. So you have these predefined ones that have this double underscore prefix, the name, in this case file, and the double underscore suffix. So file will give us the current source file, the line number, in this case 28, and we can get the compile time and the compile date. So let's run the code, and we'll check this these couts. And you can see here in this output, it shows the source file, where it's located, the full path of it, and the CPP file, and the line it's on, 28 as expected, and it was compiled at this time on this date. And I'll press any key to continue. And that concludes this demonstration on the C++ preprocessor. C++ allows a user to change a command line program's behavior using arguments passed to the main function. In this video, I'll present how to parse command line arguments in C++. So let me run through some example code I've created to demonstrate how to parse these command line arguments. So I'm starting with the typical standard library includes iostream for cout and cerr, and string, so we can parse the command line arguments as a string. So to keep things simple for this video, I'm just going to bring in the full namespace for the standard library to save a little bit of typing, so we're using namespace std. And now let's look at our main function. So our main function takes two parameters, int argc and char star argv, double bracket. So our argc is short for argument count, and our argv is short for argument values or vector. So the v is, I always think of it as argument values, but some call it the argument vector. But it's just an array of character strings representing the command line arguments that you pass to the program. Now, what we usually do is have some sort of notification if the usage is invalid. So if you pass command line arguments to your main function from the command line, so if you type the name of the program and a space, and then you type one argument, space another argument, and then you can pass multiple arguments. You've probably done this many times from the command line. If we pass the wrong number of arguments, we want to show an error. So obviously the person invoking the program has given the wrong number of arguments or has given too many arguments. So we typically check, okay, if we've gotten too many arguments, in this case, if the argument count or argc is less than 3, then we don't have enough arguments. So what we can share is how to use this program, what it's expecting. So the usage, so typically we say cerr, and we provide a usage for the program name. So one of the things, the argv doesn't just contain the arguments we pass, it contains the name of the program invoked. So argv0 is always the name of the program. So we say the usage for this program at this name, so argv at 0, so argv and array index 0. And then we say it's expecting an option followed by a file. So one of the options are double hyphen find. So this is, we want to find the file specified, and double hyphen display. We want to display the file or the contents of the file. So this is just a simple example. So what we typically do is say, okay, if the arguments aren't correct, we return 1, but we also give some conventions on the usage of the program. So we can direct the user how to use it. So if that succeeds, if we have the correct number of arguments, if we have 2 arguments, then we take argv1, which is one of the options, so find or double hyphen find or double hyphen display, we want to set this or pass this to a string. So we're taking a char star, so a character string or an array of characters, to a string. So we're using the standard library string so we can compare it more easily. So since it's arg is a standard library string, we can do a double equals comparison, and we can check to see if it's double hyphen find, and we'll just see out that we've specified the find option. Else if arg is equal to double hyphen display, we see out the display option. And if the argument is neither of these, we just say invalid option. So this is a very simple way of checking a particular command line argument. And then finally, we see out the file argument at argv2. So if you look at the way these are indexed, argv0 is the program name, argv1 is the first argument, and argv2 is the second argument. So it's a very simple way of thinking of it as the arguments themselves are 1-based indexes, because the 0-based one is always reserved for the program name. Now I'll show you how to do this in Microsoft Visual Studio. So when we pressed our shortcut key, our Control F5 to run the program, there's no way of specifying the command line arguments before it runs. So if I just hit Control F5, it will run the program. But before we do that, we'd like to check our command line arguments. So if I go to debug and properties, and we want to go to debugging, so configuration properties, debugging for our project, for our solution, and we want to go to command arguments. So in this case, I've already set it to double hyphen delete file.txt. So this is a way of checking one of the options. This particular argument doesn't exist, so we'll get the invalid branch of our conditional, so it's an invalid option. But let's check our correct option. So I'm going to do double hyphen find file.txt. So I'll hit OK, and now I'll do a Control F5, and it will run the program. It'll compile it first and then run the program, and we should see the find option with the file. So it says find option as expected, and then the file argument is file.txt. Now let's change that again. So we'll go to the properties and debugging, and let's change this to double hyphen display, and let's call this another file.txt. So I'll hit OK, hit Control F5 again, the shortcut key to run it, and we get display option, file argument, another file.txt. Now, it came up a little bit quicker that time because it didn't have to recompile the code. We only changed the command line arguments, so that doesn't change the program itself. So it doesn't need to recompile for each of these options we're changing, because this is passed externally to the program after it's compiled. And my other example, double hyphen delete, which does not exist, and let's just call this file2.txt for lack of a better example. And we'll do Control F5 again, and you'll see invalid option because double hyphen delete isn't an option that we check for, and we have file argument file2.txt. Now, one more thing to check. What if we hand it the wrong number of arguments or too few arguments? So let's go to debugging. Let's remove these command line arguments and run it this way so we can see the error. And you'll see usage shows the entire path of the executable. So it has the entire path and the name of the file, 130.511.exe, option file. And then it shows double hyphen find the file, and double hyphen display the file. So it shows the usage that it expects when we don't specify the number of arguments. Now, one more thing I'll mention. We've done this by hand, so there's a lot of work involved in making this robust and processing many different types of arguments and different types of switches with double hyphens, or some commands take a single hyphen and a single character. So what I've shown here are the basics of command line arguments. If you need something more robust and comprehensive, you can imagine there are a number of third-party utilities which you can use if you don't want to write your own. So two of the more prominent tools, I'll switch over to my web browser. So two of the more prominent tools, one is the GNU getopt from the GNU libc library. So I've shown this here. So if you look for the GNU libc in the documentation, you'll find a parsing program options using getopt. So getopt are functions to make, it says right here, getopt and getopt-long functions automate some of the chore involved in parsing typical Unix command line options. So this will simplify things for you if you use these functions. Another option in C++ is using the Boost program options library. So I'll switch over to the other tab. And at boost.org, you can see in the documentations, you look for program_options, and you'll see a C++ library to do the same thing. And that concludes this demonstration on command line arguments in C++. In C++, you can break your code out into a series of source and header files to make working with large applications more manageable, portable, and modular. In this video, I'll demonstrate how to divide the code into header and source file pairs, and to divide code between declaration and implementation. So in this program, I include two headers, iostream and x.h. Now you'll notice that they are enclosed in different characters. In iostream, we have it surrounded by angle brackets, and x.h is surrounded by double quotes. So we use angle brackets for standard library includes. So things that come from the C++ standard library, we put angle brackets around. And header files that come from our local project, something that's included in our project or relative to the local path, something in the current directory, we use double quotes. So this is a custom implementation, and this is a standard library implementation. So iostream, angle brackets, standard library, double quotes, our own local declaration or header file. Now, a couple of things. You don't want to include other source files in your application, so you don't want to include x.cpp. You only want to include header files, and the includes come before other code in your application. So if we have implementation code, the header files always come first. And also, only include headers if they're needed. Don't include all of your headers in each CPP file just in case you need them. This will not scale well and slow down your compile times. Now let's have a look at our implementation x.h. So we can look at our Solution Explorer here in Visual Studio, and if we double click on x.h, it'll open up this header file. So the header file contains a couple of things that are common to most header files. The first is the include guard. Now there's a couple of different types of include guards, which I won't get into in detail, but this one uses pragma once. So you'll see this at the top of many header files that you include in your application. And in Visual Studio, when you create a new header file, it will automatically put that in. And then many header files have namespaces. So we have namespace EG to differentiate our class X from other classes from other headers that may be called class X. So we have namespace EG, and then we have class X. So in uppercase X is our class name. It has some public members, including a constructor, and two member functions, getVal and setVal. Now, you'll notice in this case, the constructor, very simple constructor, just sets the value, this member variable value, equal to 1. So we actually implement our constructor here, which is fine, but we don't implement these functions in the header file, this getVal and setVal. So we just have the declaration of the function, but not the implementation. That's saved for our CPP file. And then we have a private member int value. So it's a very simple class with a very simple namespace in this header file. So it has a source file companion or pair, so we have x.h, which implements the class X, and we have x.cpp in our source files that implements our member functions. So the CPP file must include the corresponding header file, so include, and in double quotes, x.h. Then we implement getVal just to return the member variable value, and we implement setVal to set the member variable value to what parameter, this int I, we pass to it. Now you'll notice here it's scoped with the namespace and the class name. So this is very important. If there's a namespace, we have to specify it first, then the class name, and we have the double colons in between each one. So e.g. :x :get val. So that's our source and header file pair for x.cpp and x.h. Now let's go back to our main CPP file and have a look at what we're doing. Now when we're including many header files and using particular objects from those header files, what we quite often like to do is use the using keyword, so using, and then we specify the namespace, double colon, and the object we're going to use, this class or struct that we're going to use. So in this case, from the standard library from IOStream, we're only using cout, so I'm specifying using std : cout, and from x.h we're using the x class from the eg namespace, so using eg : x. Now, quite often with simple programs and including standard library definitions, we do something like using namespace std. But that's pretty broad, and in practice, you want to specify what you're using and not just use an entire namespace if you don't have to. So in our main program, we have uppercase X, our class name, which comes from our x.h header, and the lowercase x here, the variable name. So we're initializing class X as variable x, lowercase x, and then the next line we have x, lowercase x dot set val, so calling the member function, and we pass this constant number 20. So we're setting the value to 20, and then the following line we do a cout, we output the string x value colon, and then the actual value calling x.getVal, and then we return the line. So let's run the program and verify that when we do call this, the output is x value colon 20, which is what we'd expect based on the previous line. So we get x value 20 in the output. Now, this is a multiple header approach, so having x.cpp and x.h to organize declaration and implementation. This is what I use by default when writing C++ programs, even for simple programs, just for the sake of consistency. So I like to take this is an approach that I take in all of my programs, even for simple ones. If your program grows, then it's easier to manage, and it generally will compile faster if you take this multiple header approach. And that concludes this demonstration on headers and source files. In this exercise, you'll first list the identifying characteristics of the C++ programming language, then identify the main sections of a C++ program, and finally describe the use of the C++ preprocessor. So now you can pause the video and consider these bullet points, consider these exercise items, write down some of the answers or think of them, and then when you've completed the exercise, you can resume the video and I'll share what I came up with. So for the identifying characteristics of the C++ programming language, what I came up with is that it's statically typed, it's a compiled language, it's general purpose, and it's case sensitive. C++ supports many approaches and styles. It incorporates procedural, object-oriented, and generic programming, and C++ takes a balanced approach between elegant and affordable, so in terms of readability, maintainability, and efficiency. And because of the no-cost or zero-cost or low-cost abstractions, C++ compiles down to an efficient implementation for many platforms. It's a very performant language. So that covers the first bullet point. Now, for the main sections of a C++ program and the C++ preprocessor, I've written a bit of code to go through this. So we'll turn over to Microsoft Visual Studio, and right here I have a small program, and let's talk about the main sections. So some of the important points or the important parts of the C++ program are the includes. So we include header files from other sources, either from the standard library we have here, like IOStream, surrounded in angle brackets, and including some local header file surrounded in double quotes. We have things like using or using namespaces. We have const expressions or other functions declared in our program. And probably the most important part of a C++ program, some component that you can't live without or you can't compile without, is the main function. So every C++ program needs an entry point. And that's the main function, which always returns int and optionally takes arguments like int argc and char star argv. So this is the command line arguments, the way of passing command line arguments to our main function. And this is optional. But the main function is not optional and it must return int. So at the end of it, we have a return 0. Another thing is if it returns anything other than 0, it's not it's sort of an abnormal termination. So returning 0 says that our program exited successfully or it completed successfully. If we leave off the return, so if we delete it, that's fine as well because the main function is special in C++. And it implicitly returns 0 if it reaches the end without returning beforehand. But it's fine just to put in return 0 if you like having it. Now the C++ preprocessor, one of the main things in C++ since C++ 11 or later, so in contemporary C++, we use const expressions. So these are things that are implemented by the compiler and are evaluated by the compiler and not evaluated at runtime. So when we talk about the preprocessor, we're talking about things that are done at compile time and not at runtime. And the nice thing about const expressions over the previous C-style preprocessor macros using defines is that we can specify types. So they're type-checked preprocessor definitions. So in this case, we have const expression double that I call C2F, which is a conversion function from Celsius to Fahrenheit. And this one takes a double C as an argument and returns the Fahrenheit conversion of this value in Celsius. So C times 9/5 plus 32 converts the value from Celsius to Fahrenheit degrees. And in the main function, the body of the function, all of functions in C++ are enclosed in curly braces. So these curly brackets or braces define the function body. And then we have a const expression double in this case to demonstrate a preprocessor variable using const expression. So C is set to 33.0. And then we have const expression double F, which is the Fahrenheit equivalent, which C2F C. Now you'll notice here in Visual Studio, if I hover over F, it actually gives me the conversion. So 33 times 9/5 plus 32, it actually carries out this function for me right now before I compile it. So it shows me that the value for F will be 91.4. So we have cout F and cout, and we output the values. So what I'll do is run the program, and we'll check that the values of F and C are correct. So it'll take a moment to compile, and you'll see here, you can check it for yourself if you want, but we have C set to 33, and F, after the conversion, it's 91.4. So 33 degrees Celsius is 91.4 degrees Fahrenheit. And that concludes this exercise on recognizing parts of a C++ program and the use of the C++ preprocessor. In this video, I'll present some of the characteristics of the fundamental C++ data types. So the first one I'll start off with is the empty type, or void. So this is an incomplete type that can't be instantiated on its own. Now we can have void pointers, which I have here on line 8, or we can have functions returning void, which are okay. So a function that returns void is a function that returns nothing, or it returns empty. So we can't return a value from it. Now with the void pointer, we can point to different pointer types without specifying the type of pointer we're working with. So void pointers are okay, and functions returning void are okay, but we can't have a variable that's of type void. Now when we're working with pointers, we like to sometimes set a pointer to null. In C++, we have, from the standard library, we have the null pointer type. So this is a type-safe definition of null. So it can implicitly interact with any pointer type, but it can't be assigned or compared to integer types except for bool. Now this is different than the way things used to happen in languages like C, where we'd have the uppercase NULL for null, and it can be interchangeable with integers. We can't do that with a null pointer. So anytime we want to set a pointer to null, we set it to the null pointer, or NULL PTR. And then in C++, we have a built-in Boolean type in the language. So we have this bool, which can be set to true or false, where true and false are lowercase spellings of the words. So now, one thing about bool, if you do a size of on the bool, it's not guaranteed to be of any specific size. That varies from system to system. Now, some of the most common types, or the most common fundamental types you'll deal with in C++ are the character, the integer, and the double, or char, int, and double. So the char is for characters, integers for integer values, and double for floating point numbers, or decimal numbers. On top of these common types, we get common modifiers. So they can be signed or unsigned. So signed values can take on positive or negative. So there's a signed bit assigned to the type. Unsigned, it can only be from 0 to a positive value up to the number of bits that the type takes. And then we have short, long, and long, which we can apply to integers, and the long we can apply to double as well. So some examples of these are the signed character, or signed char, which is an 8-bit representation from negative 127 to positive 127, including 0. Assigned short is guaranteed to be at least 16 bits, taking up both positive and negative. The long int is at least 32 bits, and the long int is at least 64 bits. So when I say at least, it's guaranteed to be that size, but it may vary from system to system. So ints, and long ints might all be 64 bits on a particular system. Then we have character types. So the basic character type is at least 8 bits, which we use to represent UTF-8. So I have a char C8 here. The wchar_t is the largest character set supported by your system. So that's typically 16 or 32. And if you want to specify 16 or 32-bit characters, we can do char16_t for at least 16-bit characters for UTF-16, and char32_t for at least 32-bit characters, or UTF-32. And then finally, we have floating point types. So these are typically represented in IEEE 754 format. So this is in terms of the sign bit, the significand, or sometimes called the mantissa, and the exponent. So if we want a floating point number that's at least 32 bits, we typically use a float. So on most systems, many modern systems, it'll be 32-bit. The double will be 64-bit, and quite often the long double will be 80-bit. So we can have an 80-bit floating point number by using a long double. And that concludes this discussion about the fundamental C++ data types. In this video, I'll present how to work with different character types in C++, including UTF-16 and UTF-32. So in this video, I've included the standard library header string, because we're also going to be working with character strings. So in this case, I'm going to be using the standard string, so std : string, and then I want to use the string literals namespace, so I can do some fancy things with the prefixes and suffixes of string and character literals. So if we use using namespace std : string _ literals, it'll give us that ability. So let's look at the first example. So there's 4 different types of character prefixes: the U8 for a basic 8-bit character, L, lowercase u, and uppercase u. So what we can do is with any character, so we have single quotes, a character, so a single character enclosed in single quotes, and then we prefix it by the type we'd like to create. Now we can use the auto keyword to let the literal define what the variable is going to be. In this case with U8, it will define it as a character, so a basic char. If we change it to an uppercase L, and save it. Now the nice thing here in Visual Studio is that when I update it and save it, if I hover over it and with the cursor, it will show me what the character representation is. So what it's going to create. So the compiler will create, when I put an uppercase L, a wchar_t. So it creates a wide character, as wide as the system will allow. If I put a lowercase u prefix and save it, it will give me a char 16. If I change it to uppercase, as you can probably guess, it will give me a char 32. And if I hover over it, you'll see that it will be a char 32. So this auto C will modify or update according to whatever this prefix is. So that's one of the handy things about the auto keyword as well. So we can change our code. We can go from UTF 16 to 32 or to some wchar, and we don't have to change the variable definition as well. We just need to change the prefix. Now for strings, we can use the suffix s. Now if you look in this case, I just have a string of characters XYZ in double quotes. So in this case, at auto s, it's going to define s as a const char. So it's a basic const char pointer to this string literal. But what if we want a standard library string? Well, from using string literals, we can put a suffix s. And I'll save it. And you'll see when I hover over s now with the cursor, it gives me a standard string s. So using the suffix, I can tell it to be a string instead of a const char pointer. Now, if I want something else, I can also put an uppercase L in front of the string. Then it gives me not just a standard string, but a standard wide string. So it's a string of wide characters. And I can do the same with the lowercase u. For UTF-16, you'll see it updates here. It's a U16 string, and the uppercase U, along with the suffix s, will give me a U32 string. So it's a UTF-32 string in C++ just by changing the prefix and the suffix of this string literal. And that concludes this demonstration on UTF-8, UTF-16, UTF-32, and wide characters in C++. In this video, I'll present how to work with C++ data type modifiers. So first off, I'm going to include IOStream in my file and use the standard cout. So I'll type using std:/cout because we want to output some of the things we're working with. Now, the common modifiers I want to work with in this video are sign, unsigned, short, long, and long, long. So let's look at how these are applied to various types. So let's start off with character types. So on line 9, I have a char C, which is set to the character A. So in single quotes, I have the character A. And then I have an unsigned character, an unsigned char, UC, which is set to the character A, but I treat it as a numeric value and add 128 to that value. So I want to get into the higher numbers, the values greater than 128. And then I'll do the same with a signed character. Now, in this case, a character is 8 bits. So we're talking about values up to 2 to the power of 8, so 256. So an unsigned character will be able to represent the values from 0 to 255, and a signed character will be able to represent the values from negative 127 to positive 127 inclusive. So if we add 128 to a signed character, we're getting into a territory greater than 127, so the sign bit will get in the way. So what happens, will output what happens, but you can probably figure it out already. If we set it to a value that's greater than 127, the signed character that is, it will revert to its negative representation. So whatever that value would be as a negative. All right, so then we see out our character C, our character UC, but we'll cast it as an int so we can see the numeric value instead of the character value, and we'll do the same thing with SC. And then, just for the fun of it, we'll do a size of C to see the size of a character. Now, the important thing with signed and unsigned, they don't change the size of it. So it's the same number of bits, but they just reserve a single bit as the signed, the first bit, the highest order bit, as the signed bit, and the rest represents a number for a signed value. So the size won't change. So in this case, the size of C should still be 8, or in this case, it shows it as the number of characters, so it should give us a size of char as 1, so a single 8-bit byte. Now, integers, we have a few more modifiers. We also have signed and unsigned, but we have long, and short. So int I gives us a basic integer. Then we can specify a shorter integer, at least 16 bits, by calling it a short int. So we modify integer with short. Now, quite often you'll just see short and then the variable name. So this implies a short int. So a shorthand for short int is just short. So the int is implied. And the same thing for long, we could do that as well. But technically speaking, we have a modifier long, which is a long int. And then we have unsigned long int. So not only can we have the size modifiers like long, which will guarantee a greater size, but we can create a signed or unsigned variant of it by specifying unsigned. Now the default is signed, but we can force it to be unsigned just by specifying the modifier as well as the length modifier. So this unsigned long int is a perfectly valid type. And then for our curiosity, we'll output the size of these various types. Now this will vary from system to system, and in my case, using Visual Studio and Microsoft C++, it might vary depending on what you're compiling on. So if you're compiling on a different system with a different compiler, you might get a slightly different result. And now with doubles, for floating point numbers, we can have our double, our long double, or maybe we wanted something even bigger. For example here, I put in long double. This is not a valid combination, and neither is the signed option or unsigned. So we can only have a double or a long double. That's the only modifier. So a long double and a double, the long double is at least 64 bits, but we output the size of D and the size of LD, our double and long double, to see what this system gives us. In many systems, a long double can be 80 bits, but it's guaranteed to be at least 64. So let me run the code, and we can look at the results. So it'll take a moment to compile, and then it'll give us an output window, a terminal window with our couts. So here we have our first result was the characters. So this was a character C, which was the character A. And then if we add 128 to that, it gives us a value of 225. But with the unsigned character, instead of giving us 225, it gives us negative 31 because it can't go that high. And if you're curious to know where this comes from, why is it negative 31? Well, if you add 31 to 255, you get 256. So it's kind of a complement of the number in terms of its unsigned representation. Now, size of character on this system is just 1, so it's a single byte. An int is 4 bytes, a short is 2 bytes, so 4 is 32 bits, short is 2 bytes or 16 bits. A long int is 4 bytes or 32 bits. A long int is 8 bytes or 64 bits. And a double and long double are both 8 bytes or 64 bits. So in terms of magnitude, you'll be able to work with larger numbers using unsigned, since you gain an extra bit using those variants. And if you're using long and long, you're not always guaranteed to get a bigger number, but you'll never get a smaller number. So a long int will never be smaller than an int, and a long int will never be smaller than a long int. And the same with double. Your long double is guaranteed to be at least as big as double, and if your system supports it, it'll be an even bigger double. And that concludes this demonstration on data type modifiers. In this video, I'll present some basic arithmetic operations and their precedence or order of operation in a C++ program. So I start out by including iostream and using std:\cout because we're going to use cout to output some of our results. Now let's first start off by talking about precedence. Well, C++ uses left to right operation. So our operations will get applied from left to right, but there's a certain precedence that comes when we're applying certain operations. So if we're doing multiply, divide, or modulus, they get applied first. Then, so this is as a group from left to right. So whichever one it sees first from left to right, it will apply these, the multiply, divide, and modulus. And then, as a group, it'll apply addition and subtraction. So there's no precedence order for any of these groups inside the groups themselves. So if it sees addition first, it will get applied, or if it sees subtraction, it will apply the subtraction first in left to right order. And modulus, if you don't know or aren't familiar with it, it's the remainder. So if we say 5 modulus 2, it's the remainder of 5 divided by 2. So 5 divided by 2 is 2 remainder 1, so the modulus will just return the value 1. So let's have a look at our main function and see the example that I've come up with. So I start off by creating an int a, which I don't assign a value, and an int b, which I assign the value of 10. So I'll use these later on in the program. As well, I have double x and double y, where y is set to an arbitrary number 3.6742. So before I get into these variables, I start off with a couple of examples to highlight a basic operation. So basic statements like if I use the literals, say 2 plus 2, it will just evaluate and print out the result. So in this case, I do a cout, I pass the string 2 plus 2 equals and a space, and then I give it 2 plus 2. So that should output 4 when I run the program. So it just carries out this basic operation right here in place. Now, if we want to play with the precedence, we can come up with a fairly elaborate expression. In this case, an expression that uses all of our basic operations. So we have subtraction, modulus, multiply, addition, and division, and we carry this out. So if you know the rules of precedence, you'll know that we carry out the modulus first because it's the leftmost group 1 operation. So modulus, multiplication, then division, and then it will take those values, those intermediate values, and then apply the subtraction. So 120 subtract that value plus whatever this value is, 100 divided by 10, which is obviously 10. So if you wanted to, you could go through, I'd recommend just going through this calculation, figuring it out on pen and paper, what you think it would be, and then when I run the program at the end, you'll see the actual result of A. So I assign this expression 120 minus 5 modulus 2 times 10 plus 100 divided by 10, and I assign that to the variable A. And then we output the result here. Now, if you need to force precedence, if you want the subtraction and the addition to be applied before the other operations, then we can wrap them in parentheses, and that will see that they get applied first. So anything in parentheses gets applied before anything else. So it changes the expression, and it should change the answer. So here in parentheses, I have 120 minus 5 enclosed in parentheses, modulus 2 times, in parentheses, 10 plus 100 divided by 10. So it should give us a different result. And then finally, I'd like to mention implicit conversion. So this will take on the left-hand value or the left-hand values type. So A was defined as an int. So in this case, y plus b, y is a double and b is an int. It will get applied as an int. So what happens to the double? It gets truncated. So if there's a decimal part, you lose the decimal part and it just adds them as integers. Now, in the other case where the left-hand value is of type double, like this double x, y times b will be applied or be operated on as they're both doubles. So the int will get converted into a double and multiplied with the double y, and then we'll get our value x. So I just carry out this operation, so y plus b and y times b with int and double respectively. So I output their values here. So if you're curious, so B was 10, Y was 3.6742. So the result of A should be 30, and the result of X should be 36.742. So let's run the program and verify these results. So we get 2 plus 2 equals 4 in that first expression, that first cout. And then in this one, this expression with the precedence order, the actual result was 120. And the next operation with the parentheses gives, even though all the numbers are the same and all the operations are in the same order, with the parentheses, by changing the order of operations, we get a result of 11. And then A is 13 as expected as an integer, and X is 36.742 as a double as expected. And that concludes this demonstration on arithmetic operators. C++ allows you to compare the equality or inequality of variables using relational operators, like greater than, less than, greater than or equal to, or less than or equal to, and perform and, or, and logical not, Boolean logic operations. These are all binary operations except for the not operation, which is unary. So it takes a single parameter. In this video, I'll present how to work with relational and logical operators in C++. So I start out my program by including IOStream and using std:/cout. So we're using cout from IOStream to output some of our results. Now, the first part of the example in our main function are relational operators. So we have less than, greater than, equals. So equivalence is a double equal sign to say if things are equal to in a relational sense and not in an assignment. So if we're doing assignment, we use a single equal sign. If we're doing a relational comparison, we use a double equal sign. And then less than or equal to is just the less than with the equal sign, and greater than or equal to is greater than, and then the equal sign. So we carry out these, they return a type bool. So we have rstuv as variables, and then we have is 5 less than 4, 5 greater than 4, 5 equivalent to 4.01. Now, if we're comparing an integer type with a double, like this 4.01, there's an implicit conversion of types that takes place before it makes a comparison. Then we have 5 less than or equal to 4, and 5 greater than or equal to 4. So the result should be obvious. We should have false, true, false, false, and true. Then I take our variables and I output the comparison. So this relation 5 less than 4 with a colon, and then I output the result. Now, for the first one, I've done something different here. I actually put the numbers because I wanted to demonstrate something you might come across when using relational operators. So if I remove these parentheses, IntelliSense will show me that there's an error, and it'll have like a little red squiggly line under the less than. And if I tried to compile it, there'd be a problem. It says there's no operator less than that matches these operands, so it doesn't match this OStream. So cout is of type OStream from the standard library. It takes the double less than, and then it takes some value like a string or a numeric value, some type, to output to our command line when we run the program. Now what it sees here, it sees this double less than and then the value 5. But this is operating under cout's type and not under the numeric type. So then it sees the less than and it doesn't know what to do with it. So to ensure that this gets computed properly and it successfully, this relation, we have to wrap it in parentheses so it doesn't confuse it with the type of cout. So it takes the comparison and passes that value to this operand of cout. And then for the rest of it, I output the values, the Boolean return values of the relations s, t, u, and v. Now with the logical operators, we're carrying out a Boolean logic operation. So what we end up doing is taking some values that are true or false, and we use the double ampersand for the AND logical operation, or if we want an OR operation, we use a double pipe. So we could have true and true, which should return true. True logical and false, or true double ampersand false should return false. True or false, or true double pipe false should return true because it's one or the other, and it must be both. And not, the not operator, which is just the exclamation mark. In this case, if we do not true, it should return false. And we can also operate on numeric values, 0 being false and anything else being true. So if we had 1 or 0, it should return true. And another thing to mention is the precedence order. Not will be applied first in an expression with multiple nots, ands, or ors. Not, it will apply them left to right, but in precedence, in order of nots first, then ands or double ampersands, then the or double pipe. So I did a little example of this here that will output to our console. So that's the end of the example. Let's run the code and see the result that we get. So it'll take a moment to compile, and we should see the results here. So one of the things when we're passing the values to cout, then it returns the numeric representation. So it sees the bool as a number to respond with. So in this case, it responds with a 0 for false and a 1 for true. So 5 less than 4 is 0, 5 greater than 4 is true, so it returns 1. And then we get 0, 0 for false, 5 greater than equal to 4 is true, so we get 1. True and true, or true double ampersand true is true, so we return 1. And true and false is false, so we get 0. And the same with or, we have true or false, which is true. Not true is false, so we get 0. And then 1 or 0, and I forgot to put in the colon, so we get this is the result, 1, so 1 or 0 returns 1 or true. And then finally we have false or not false and true. So not false gets applied first, so that's true. Then the ampersand gets applied, so we have true and true, which is true. And then if we OR it with false, it's still true, so we get the result of 1. So that pretty much works as expected. And that concludes this demonstration on relational and logical operators in C++. C++ bitwise operators allow you to shift, invert, and perform logical operations on variables at the bit level. So when I started programming in C++, I enjoyed these bitwise operations. Being able to manipulate values by their bit representations seemed very powerful when coming from a base 10 world, a decimal world, and jumping into the base 2 binary world. In this video, I'll present the syntax of bitwise operations in C++ and how to use them. Now, we're going to start by including IOStream and bitset from the standard library. For these, we need to use cout to output our values, but we also want to output them in their bit representations. So for that, we use bitset from the standard library. So in our main function, I start with the unary operators. The left shift, or double less than sign, the right shift, or double greater than operator, and then the tilde, which is the logical not, or bitwise not, which inverts the values of all the bits in our number or character. So we'll start with an unsigned character b, which I set to this binary representation. So if you'd like to represent a value in binary, you can use the 0b prefix, which was available since C++ 14. So we do 0b, and in this case, my number is going to be 00001001, which in decimal or base 10 is equivalent to 9. So I start out by doing a cout on b, and then I give it a bit set with the parameter 8, so 8 bits, and then in parentheses our variable we'd like to output, or value we'd like to output. So we want to put 8 bits from b, an 8-bit character, and that's what we'd like the cout to show. So we don't want it to show the decimal value of b, but we might like to see its bits. So what makes up the character b? And then let's perform some operations on it. So then I output b left shifted by 2, and then b right shifted by 1. Now this won't modify b. This will just take the original value of b and represent it with after a left shift of 2. So here on line 11, when I'm doing the right shift by 1, I'm still working with the original b. And then the same on line 12 when I do a tilde b, which will invert all of the bits of b. So anywhere there's a 0, it will become 1, and anywhere there's a 1, it will become 0. Now the next part of the program is the logical operations, the binary logical operations. So we have and, or, and exclusive or ampersand, pipe, and caret. So what this will do is take each bit in a bitwise fashion. So it will compare the bits, it will do an and on the bits, and if they're both 1, it will set the corresponding value to 1. Otherwise, it will set it to 0. And for the or, it works as a basic logical or. If either of the bits are 1 or both are 1, then the resulting bit will be 1. And the exclusive or is one or the other is set to 1, but not both. So anywhere there's 2 1s or 2 0s, the result will be 0. And anywhere there's a 1 and a 0 in either of the bits, it will return a 1. Now I output a few of these operations here. So we take our variable c and we AND it with this binary representation. So 0 0 0 0 0 1 1 1. And then we do a c or 1 1 1 1 0 0 0 0, and the same with the exclusive or c exclusive or and the bit representation 1 1 1 1 0 0 0 0. Now since I'm doing exclusive or and the or on the same bits, you'll be able to see the difference between those two operations. And one last thing I'll mention before I run the program is the precedence of these operations. So the bitwise not comes first, then left shift, right shift, and exclusive or and or. So if you have a compound operation, so if you have a statement with using many of these, it will process them from left to right, but in this precedence order. So the tilde will get the greatest precedence when performing the operations, and the logical or will get the least precedence. So let's run the program and see what the result is. So we start out with our b as these 4 zeros, 1 0 0 1. If we shift it left by 2, then the 1 0 0 1, which was at the lowest part of the byte, will get shifted up by 2. So we'll have 0 0 1 0 0 1 and then 0 0. If we shift it right by 1, our lowest order bit that's set gets shifted off of off to the right, so we don't have it anymore, so we lose that bit. And then this one that was in the 4th position now moves over into the 3rd position. So we get 0 0 0 0 0 1 0 0. And then here, if you look at b at the top, so we have the 4 zeros, 1 0 0 1. All of those bits get inverted, so where we had 0, we get 1, and where we had 1s, we get 0. Now, this is why my counts were formatted the way they were, so I can show the operation, show the values, and show the results. So I see our value, our variable c, 1 0 1 0 1 1 0 1, and then I AND it by this particular value. So it's a 3 1s in the lower order. Now you can think of the AND operation, the bitwise AND operation, as a mask. So anywhere there's a 1, it's going to preserve that bit, and anywhere there's a 0, it's going to drop that bit. So here with the 1 1 1, it's just masking out the bits in our variable c and just showing the bits that were set in these first 3. And the rest of them get set to 0. So it's like we discard these, but keep these. So we keep the bottom 3 and discard the top 5. Then we do an OR. So you can think of this as setting bits. So anywhere in one of the operands where there's a 1, in the result, there'll be a 1. So I set these 4 to 1 and these 4 to 0. So anywhere there's a 0 in an OR, it will just keep the existing value, and anywhere there's a 1, it will get set to 1. So these 4 1s make sure that these top 4 are set to 1, and the bottom 4 bits stay the same. And you'll see that this answer is different, this logical OR answer is different than the logical exclusive OR, which anywhere there's 1, 1, so in this first bit, this high order bit, it's 1, 1, but the value is in the result is 0. So anywhere we have 2 1s, we get a 0, we get 0, 1, which is a 1, another 2 1s gives us a 0, so we get 0, 1, 0, 1, 1, 1, 0, 1. So it performs a either or, but not both, on each of the bits individually. And that concludes this demonstration on bitwise operators in C++. The C++ equal sign assignment operator assigns a right-hand side expression, an R value, to the left-hand side expression called an L value. In this video, I'll present how to work with the assignment operator in C++ and discuss the nuances you should be aware of. So let's look at our main program and see what we're doing with our R values and L values. So on this line 5, I have int L. So L is our L value. It's the value on the left-hand side of the equation. So it has to be a variable because it's going to accept the value of the right-hand side expression. In this case, the right-hand side to the right of the equal sign is just 2 plus 2. So this will assign this particular value, once it's computed, to L. Then we have a variable L2 on the next line, another int, which is our L value in this case. But in this expression, L from the previous line becomes part of our R value expression. So our right-hand side expression to the right of the equal sign. So L plus 8 is assigned to our L value, L2. We can also use two equal signs, so we can do a sort of double assignment. So in this case, I have int L3 here on line 8, so L3 is an L value, but as well, L2 is an L value, even though it comes to the right of this equal sign here, this first one. So L3 equals L2 equals 20. So 20 is our R value, and L2 and L3 are both L values. So L3 and L2 get assigned to 20. Then on the next line, if we assign L3 to 40, this has no bearing on L2 because we're only assigning values. We're not linking the two variables. So if you say L3 is equal to L2, that has nothing to do with these variables. They're still two separate variables. We're only exchanging values. We're not pointing or doing anything with their memory locations. They reside at two separate memory locations, and when you change L3 after this line, after line 8, it does not affect L2. So that's another thing to be aware of when you're working with assignment operations. And then finally, we do a cout. So I've included iostream and the standard cout so that we can call iostream to see the contents of our variables here on line 10. So I output L followed by a comma and a space, L2, another comma and space, and L3, and then I do a carriage return at the end. So let me run the code and verify that this works correctly. Now you may want to pause the video, do some mental math in your head, and figure out what the answers should be before you run the program or before I run the program, and then we can see, look at the results and make sure that they correspond to what we'd expect. So it's compiling now, and it should launch in a moment, and we can see the results. So if we look, we see that our values, L is set to 4 because L was only an L value assignment right at the start, and it wasn't reassigned. L2 is set to L plus 8, but it gets reassigned on line 8. It's another L value here, and it's set to 20. L3 was initially set to 20, but then it was reset here on line 9 to 40. So we get 4, 20, and 40 as expected for our values of L, L2, and L3. And that concludes this demonstration on assignment operators in C++. C++ compound assignment operators allow you to perform arithmetic or bitwise operations on a variable and assign the result to that same variable. It lets you avoid retyping the L value variable in the R value expression, i.e., anywhere you want to modify a variable based on its current value, you can use a compound assignment. In this video, I'll present some examples of compound assignments in C++. So in this example, I include IOStream for cout so we can display some of our results in our console window. So I'm including IOStream and using std:\cout to shorten the typing of our cout statements. Now in our main function, I start with the variable I that we're going to use in our compound assignments. So I set I initially equal to 10. And then I do a cout on i's initial value. So that should output 10 to our console. And then I do our first compound assignment on line 8 with a simple addition. So I do I plus equals 10. So I'm adding 10 to I and modifying I in the process. So this is equivalent to doing I equals I plus 10. So the shorthand for I equals I plus 10 is just I plus equals 10. So it's adding to i's current value 10 and assigning it to I. So I do a cout of I plus equals 10 colon and a space so we can see the value of I at this point. Now, instead of doing the compound assignment for each one of these examples and then doing a cout on the subsequent line, I'm merging those two into a single line. So on line 10, you can see I do a cout of the string I minus equals 2, a colon and a space. So I output what we're going to do, and then I output the result. So in parentheses here, I put our compound statement. And this is perfectly valid C++. So somewhere in a more complex statement or in a series of operations, in parentheses here, I could put I minus equals 2, and that will carry out I minus equals 2, or which is equivalent to I equals I minus 2. So we'll carry out this on I and modify it so it's going to decrement the current value of I by 2. And then the next line is a similar thing where with the multiplication. So I could do I times equals 4. So that's going to multiply I's current value by 4, which is equivalent to saying I equals I times 4. And then with division, I can do the same thing. I slash equals, so for divide is a slash symbol, so I divided by equals 2, or I equals I divided by 2. So that's the compound assignment for division. For modulus, so I percent equals 9, or I mod equals 9, which is I equals I mod 9. And then so I'm going to do a left shift by 2 bits, so I left shift equals 2, and then I do I right shift equals 1. So for left shift, it's the double less than symbol together, and for right shift, it's the double greater than symbol. So you can see the equivalence here, I equals I left shift 2, and I equals I right shift 1. And it's the same for other bitwise operations and exclusive OR and OR. So I and equals this bit of 00001111, or the integer 15 in its bit representation. So this is in binary, so I do the 0b prefix followed by a binary representation of what I want to and exclusive OR and OR. And instead of using bits, I can just use the integer as well. So in line 18, I have I OR equals 7, which is 7's the equivalent of the binary 111. So that's going to OR 7 into our value at I. So we're going to go through this whole thing. I'm going to run the program, and it's going to output the results for each one of these. So I'll use my Control F5 shortcut to build and run the program. So let's look at the results. So here I have 10, my initial value of I, and then I plus equals 10 brings it to 20, subtract 2, so then multiply by 4, 18 times 4 is 72, divide by 2 is 36, mod 9 is 0, because 36 is divisible by 9. So if I do a shift left or right, it's just going to leave me with 0. It's probably not the best value to pick. I should have picked something else that would have left a remainder here. And then we could have values. So the AND equals this is still 0. The exclusive OR actually gives me a value. And then ORing by 7 gives me 175. So it carried out all the operations. It computed them in place and returned the result with the updated value of I, and carried that value through all of the operations because we're using the compound assignment. And that concludes this demonstration on compound assignment operators. In C++, the if statement allows you to control the flow of your program and make decisions on what code to execute based on whether a given condition is true or false. In this video, I'll present how to use the if statement for branching in C++ programs. So I start off by including IOStream, as I do in many example programs, and using the std : cout. So we want to use cout to display some of our results when we execute the program, so we can see what's going on. Now in our main function, I initialize two variables, int I equals 10, so we're going to branch on the value of I, and we'll set bool b equal to true, so we can branch on some condition of b being true or false as well. So the first simple if statement I have is if, in parentheses, so the syntax for an if is if, and in parentheses the condition. So in this case, if I is equal to 10, so the double equal sign to compare I to 10, and if it's equal, it'll execute the line of code following this if. So cout I is 10 as a string. Now, when we're working with a single line of code in a branch, so if this is true and then there's a single line of code that executes, we can leave the code like this. But if there's more than one line of code, as you'll see below, we need to enclose this block between the if and the end of the if in braces. So we need to open and close the braces to execute more than one line of code. Now in this simple case with a single line of code, we can do it just like this. If I is equal to 10, in parentheses, execute this line, else, if I is anything else, other value, so if this is not true, execute this else, or what it follows this else. In this case, cout I is not 10, so we output that string instead, followed by a carriage return after each one of these strings. Now, another example is using else if. So we can have an if condition and any number of else ifs, so else space if, so we can check multiple conditions, and then at the end, we can do an optional else. So it's kind of a catch-all to execute if none of the conditions are met. Now you can leave the else off entirely, or if you only want to handle the specific condition and not the else, it's fine to leave it off. So I could delete these two lines of code, 10 and 11, this else and this cout, and it would execute just fine. So there's no requirement to have the else or to have an else if. You can just have an if statement on its own to execute a particular block of code or line of code conditionally. So let me run through this example here, starting on line 13. If I is greater than 0, I execute the cout that outputs the string saying I is greater than 0. Else if I is less than 0, I do the same. I cout the string I is less than 0. And then else, so if I is neither of these two things, the only other option is if I is equal to 0. So I cout else, and then put an ellipsis here, I is equivalent to 0. So that's the conditions. Like if I change this to be, say, I is less than some other value, say I is less than minus 10, then this would be true for any value of I from minus 10 to 0. But let's leave it the way it was so our code makes sense. So we have else, a condition, and then inside of any one of these if blocks, any one of these conditionals, or any one of these branches, however you'd like to term it. So we have a branch here if I is greater than 0, a branch if I is less than 0, and a branch if it's anything else, or in this case, it will necessitate it being 0. We can have another nested if statement within any one of these blocks. And then we have another if, and it executes separately from this one. So once we get into this branch of code, then we check if not b. So this is a syntax you'll see quite often where you have the exclamation mark for the not b. So if b is not true, i.e. if b is false, then you execute this. So not b is the same thing as saying b double equal sign false. So it's like comparing it to false, but it's a shorthand that we often see in C and C++ programs where it's just the exclamation mark. So you just read it if not b, i.e. if b is false, execute this, else, in this case, cout else b is true. So now let me run the program so we can see the result, and then we'll modify the variables to see some other branches. So in the way I have it set up here, I is 10, so we get I is 10 and I is greater than 0, so it executes the appropriate branches. Now if I change I to be, let's say, minus 10 or negative 10, I'll do a Control F5 to rebuild and rerun the program. And you'll see I is not 10 and I is less than 0. And the last thing to check is when I is equal to 0. I'll compile and run again. And you'll see I is not 10, and then it outputs else ... I is equivalent to 0, and then else B is true. So that's the case where B is set to true, and if I change B to false, this should let us see all of the possible branches of code that we have in this program. So the same thing, I is not 10, I is equal to 0, and B is false. And that concludes this demonstration on the if statement in C++. In C++, the for loop is the most common loop that allows you to perform a sequence of statements a specific number of times while a condition holds true. In this video, I'll present how to use the for loop in C++ programs. Now, I've started off including IOStream and vector in this example. So we'd like to output some of our results, so I'm using std:\cout from IOStream, and we're using std:\vector, so we can use vector from our standard library vector. So I'm going to show you how you can iterate over a vector using a for loop in this example. Now, to start out in our main function, I have a little comment here that says, informally, a for loop is of this format. So this is not the technical definition. This is an informal definition, how you should approach or think about a for loop when you're starting out with it. It can get quite complex, and there's lots of very fancy examples on how to use a for loop and how to use it in non-standard ways. But the standard way is exactly this. So we have a for, and then in parentheses, we have some initialization conditions. So some init, I call it. So we initialize some variables for our loop, followed by a semicolon, then the condition for stopping the loop. So this condition usually uses the initialized variables in some way, and then we have another semicolon, and then we have some increment or decrement or some modification of the initialized variable that steps it towards our condition. So the basic case for a for loop is just iterating a certain number of times. So if we have for, our initialization, or our init in this case, is int I equals 0. So we start with I equals 0, and we loop while I is less than 10. And then on each iteration of the loop, we increment I by 1. Now, the first time you enter the loop, this increment is not going to get executed. Only the initializer and the condition. This increment only happens after you've reached the end of the loop, and then you go on the next time. So the first time you enter the loop, the value of I will be 0. So what I'm going to do here is output the value of I followed by a space. So we'll see all the values of I for each iteration of the loop, delimited by a space. And then I do a double carriage return so to leave some space between this basic for loop and the next example. Now, in the first example, I had a single initialized variable. Well, we can initialize multiple variables, and we can have multiple conditions, and we can have multiple increments or multiple modifications of those variables. So the expressions don't have to be a single expression, we can have multiple expressions. So with multiple initializers, I have for, and in my initialization block or section, I have int I equals 0, comma, j equals 10. So I initialize two ints, I equals 0 and j equals 10, followed by the semicolon. But my condition in this case, I only want to check to see if I is less than 10. And then in my increment, or this expression at the end after the semicolon, so in this third part, I have I++, comma, j minus minus. So each iteration of the loop is going to increment I and decrement j by 1. And then I just do a cout of I space j, and then a semicolon, comma, and then another space. So this will leave a dangling comma at the end, but we don't really care too much about the formatting. I just want you to see the values of I and j as they're initialized and as they change until the condition is met. And then we'll leave another couple of lines before our next for loop. Now this one's a more recent development since C++11, I believe, is the range-based for loop over an array. So we initialize an array here, int a of ints, And I use this initializer with all these numbers 4, 3, 2, 1, 0, 5, 6, 7, 10, 9, 8, all delimited by commas, surrounded in these braces. So it initializes this array of 11 values from 0 to 10. And we have an array that we want to use a for loop over. Now, we could do this by using our first basic example where we take I is equal to 0 and go until I is equal to 10, or less than or equal, while I is less than or equal to 10, and we'll output the index of the array, but we don't have to do that. We can use a ranged base for loop. So we have 4 and we have int I colon a. So this is shorthand for taking the next value of the array a on each iteration of the loop. So this will loop over all the integers in a, and on each loop it will assign the current value to I, and then we can access it by just accessing I. And this will work for various types of arrays, not just integers. So you can specify int here or whatever type you need, or auto if that's appropriate. And here we'll just output the values in the order that they're in, followed by a space. And then finally we'll do another double carriage return, and then our last for example. So in this example, we're iterating over a container using an iterator. So we have a vector of ints, v, and we initialize it to these integer values here. So these are multiples of 10 between 10 and 100 in a mixed up order. And then we can do for, and then our initializer creates an iterator. So I use the auto keyword because iterators can be messy to type, and it's quite obvious from the context that when we're accessing v.begin, that we're accessing a vector iterator, so we just use auto to keep it simple. So I call the iterator itr, I set it equal to the beginning of our vector v, and then I loop while the iterator is not equal to v.end, and then I do ++ on itr to increment the iterator on each iteration of our for loop. And then I can access the value at the iterator by using star and itr, so I output the value followed by a space, and then I do that for each element of our vector. Now let's run the code and see that it works as expected. So I'll do Control F5 to compile and run. And let's have a look at our output. Now I'll move the output window to the side so we can look at the code and the output at relatively the same time. So our first basic for loop, it starts at 0 and it ends at 9. So the moment that I gets set to 10, it exits the loop and doesn't execute it for the last time. So while I is less than 10, when I equals 10, it won't execute this cout. It will just skip to the end of the block and continue on. So we get our values from 0, what we initialized it to, until 9, while I is... So we get the numbers from 0 to 9 outputted with a space in between each one. Then with our multiple initializers, we start with I0 and J10. So we have, in the output, we have I and J, so we have 0 and 10. Then I gets incremented by 1 and J gets decremented by 1. So we go 1, 9, 2, 8, 3, 7, and so on until I is equal to 9. And then when it's equal to 10, we exit the loop. And then the range base for, if you look at how I've initialized it, these numbers are in the same order as the numbers here in the output. So 4, 3, 2, 1, 0, 5, 6, 7, 10, 9, 8. All get outputted just fine, everything from the array. So this works as expected. And then finally, we have our range base for. So if I scroll down and look at our vector, so our range base for was fine. Now, iterating over a container using an iterator in our for loop, we can see the values. Now, if I move the window over as far as I can, you can see that the numbers that we initialize the vector with are the same as in the output and in the same order. So the iterator starts at the beginning and iterates through until it reaches the end. And once it's set to v.end, which is kind of an element off the end of the list, it exits the loop, and 40 in this case is our last number, and it corresponds with our output. And that concludes this demonstration on the for loop in C++. In this video, I'll present how to use the while loop in C++ programs. So I start out this program by including IOStream and using std:/cout. So we're going to use cout to output the results of our program. Now, the while loop is a very simple loop. There's only a single block inside of its condition, which we call the condition or the expression condition. So we need while, and then in parentheses we have some expression condition, and then we have a block of code. Or we just have a single line of code in which we can omit the parentheses. So let's look at a basic example. Now, if there's a while loop that has one line of code, we can declare it like this. So here I initialize a variable int I equal to 20, and then I do while. In parentheses, I put I is greater than or equal to 10. So this is a very simple while expression, and then we have a single line of code, which I just put here, which is going to get looped over. So we have cout I minus minus, so we make sure we decrement I. So I starts at 20, we decrement it on each iteration of the loop, we output it with a space. So we're going to start at 20, and then we'll loop until it reaches 10. So when we reach 10, it will decrement it to 9, and then the condition won't be met, and then it will continue executing our program. So we should get from 20 to 10 in this loop. Now, a compound statement, so a while block with the code block with the while that has more than one line of code, we need to wrap it in braces. So here we have our while I is greater than or equal to 0, and then I have an open brace, 2 lines of code, and a close brace. So here it does the cout I followed by a space, and then on the next line of code it does I minus minus. So this will continue until while I is greater than or equal to 0. So when the I equals 0 on the following line or the following iteration of this loop, I will be decremented to -1, and then it will check the condition and see that, wait, I is less than 0, it's no longer greater than or equal to 0, so we just skip to the end of our while loop and continue executing our program. Now, we can also have a declarative condition or an assignment condition on our iteration of the loop. So we can declare a variable that has to meet a certain condition. So here I initialize this int a, or an array of ints a, which is initialized to these values. So I have 5, 10, 6, 4, 4, 2, 1, 1, 20, and 0. So what I'd like to do is execute while the element of the loop that we're accessing is not 0. So I initialize j to be equal to 0. So this will be our index into the loop, j. So it'll first, a of j will be 5. So we start with that. So we initialize int I equal to a of j plus plus. So we'll increment j. So we'll be stepping through the elements of our loop until it reaches 0. So when this condition is not met is exactly when I is 0. So int I equals a of index j plus plus. And then we'll output the elements of I and see how it works. Now there's another statement we can use within our loop to kind of short circuit our loop, our while loop, and continue executing. In this case, I initialize I to 0, and I do while I is less than 10. I increment I, so I do I plus plus. And then if I mod 2 is equal to 0, so if I is divisible by 2, I continue. So what this does, it short circuits the loop, it goes back and checks the condition again and continues executing the loop, but it skips anything that comes after it. So it won't output I if it's divisible by 2 or if its mod of 2 is equal to 0. Now we can also break. So there's breaking out of a loop, which will exit short circuit like continue, but it will just exit executing the loop immediately. So in this case, I set I equal to 1, and while I is less than 10, I check if I mod 7, so if I is divisible by 7, it breaks out of the loop. And then otherwise, I output I, and then I increment I. So that'll go until I is less than 10, or if it reaches this condition, it will break out. So in this case, it should increment until it reaches 7, and break out at that point. Now let's run the code and verify what I've explained to you is actually what happens in practice. So I'll do Control F5 to run the program, and you'll see this while loop starts at 20, it executes until I reaches 10, and then it stops executing. So that condition was fine. In this case, I continue executing while I is greater than or equal to 0. Now you'll notice I here starts at 9. So that's because at the end of this loop, it had decremented I to be 9 and then exit out of the loop while I was 9, because that was the condition to quit the loop. And here it executes while I is greater than or equal to 0. And you probably know what value I will be after it finishes this loop. Well, it'll be -1 at that point. And then we have a new assignment for I, but in this declarative condition for the while loop, you'll see it starts at 5. So as I've initialized this array, and continues printing until it reaches 20. But when it reaches the value 0, that's the condition for it to exit the while loop, and it doesn't get printed. Now, this example where we're using continue, I'm continuing or skipping out on the cout, short-circuiting the loop and continuing to process it when I is divisible by 2. So I increment I, check to see if it's divisible by 2, and if it is, I continue. Otherwise, I print I using cout. So that should give me only the ones that are odd numbers. So 1, 3, 5, 7, and 9. And then when it reaches 10, it exits the loop. Now the break, as I've explained it, will break when I is divisible by 7. So if we're starting at 1 and running until while I is less than 10, when it reaches 7, it's divisible by 7, so it should break. So that's exactly what we get. So we output the value and increment it for each iteration of the loop from 1 all the way to 6, and then when it reaches 7, it short circuits and breaks out of the loop. And that concludes this demonstration on the while loop in C++. In this video, I'll present how to use the do-while loop in C++. So to begin with, let's look at our includes. So for this example, I'm including IOStream, vector, and bitset, and we're going to use cout, vector, and bitset from the standard library from these includes, respectively. Now let's look at our main function where we define our do-while loop. So it works like this. So we start out with the keyword do, followed by a block of code, usually enclosed in braces, and then we have while at the end of the loop block, some expression condition. So we're looping while this condition is true. Now the difference between this and the while loop is that we execute the code for the loop before we check the condition. So it automatically enters the loop, but then if it's going to execute the loop more than once, or it's going to check the condition at the end to see if it should keep looping through this loop. So with a while loop, if it starts with a while, it checks the condition before it enters. With a do while, it just enters and starts executing the contents of the loop before checking the condition. So it checks it at the end of the first execution. So in this simple do while example, I set I equal to this 10,390, this int, and then what I output is the bit representation of this number. So I output 16 of its bits, so all of its bits, because this number is smaller than or equal to 16 bits. So we output 16 bits, so we'll have 0 ones in binary representing I, and then we do a right shift by 1. So we output the value of I, its bits, we remove the lowest bit, so we shift it to the right 1, and then while it's greater than 0, we keep outputting the bits and shifting it by 1. So it shifts it by 1 on each iteration of the loop until it reaches 0. Now we can do while with an iterator or other conditions. So in this example, I create a vector of ints v to these particular values, so 55, 3, 1, 0, 0, 3, 343. Now I initialize an iterator to be at the beginning of our vector v, so auto itr equals v.begin. So the auto on the iterator just makes it quicker, so it gives us the correct iterator type based on v.begin. So what we do is output the current value at the iterator, so star itr followed by a space, and then we increment our iterator ++ itr. And then at the end of our loop, at the end of our do while, so we have while the iterator is not equal to v.end. So it will continue to execute, checking this condition at the end of each iteration of the loop until we reach the end, and then we'll exit the loop. So let's run this example and verify that we do get what we expected. So it's going to compile and run. And you see here our bit set. It starts here with our 00101 and all these bits. And then you'll notice you follow this 1 down. So on each iteration, it moves the bits over by 1, dropping the least significant bit. So on each iteration, this 1 moves over, pushing everything else off. And then eventually at the end, it gets down to 1, and then this bit gets pushed off, which sets I equal to 0, and then it exits the loop correctly. Here with the iterator, you'll see the values that we've outputted in this loop. So this cout outputs each value from our vector of ints. So 55, 3, 1, 0, 0, 3, 343, exactly the values we initialized the vector to. So everything gets outputted correctly. Then we reach the end and exit our do-while loop as expected. And that concludes this demonstration on the do-while loop in C++. In this video, I'll present how to use the switch statement in C++ programs. So in this application, I've included IOStream, and I'm using the standard cout to display some of our results. Now let's talk about the switch statement. So the switch is for switching. It's a branching conditional on integral or enumeration types. So you have to give it a number, an integer, or some type of enumeration. So the syntax looks like this. You have switch, then you have some expression condition or variable, and then you have a block of code which contains a case, a particular constant value. So if our expression condition is this constant value, then it executes some statement or series of statements. And when it reaches the end of the case, quite often we break, and we break out of the switch statements. Or we continue to execute until, or check other conditions, other cases, so we could have multiple cases. And then finally, at the end of our switch statement, we quite often put a default handler. So this default catches any expression or any condition that's not handled by any of our other cases. So this gets executed if none of the other conditions are met. And then we have a series of statements. Well, let's look at this in practice. So in my main function, I initialize an integer, an int I equal to 1. Then I do a switch on the variable I, and then I open my brace, which is closed down here on line 24. And my first case is case 1. So this is where I is equal to 1. And then I do a cout of the 1 as spelled out O-N-E. And then I do a break. And in this case, in this program, I is set to 1, so it will execute this, break, and get out of our switch. Now I can change this value and run it a few times so we can see the results. Now the other common way of using switch is with an enumeration. And in C++, we have enum classes. So I create an enum class direction, which has the values, this enumeration, north, south, east, and west. So I create an instance of our direction, myMove, so we're thinking of moving in one of these directions, and I set it to direction : north. So myMove is set to north. So what we do is do a switch on my_move, and then we handle the cases of the enumeration, direction north, south, east, and west. And here those are the only 4 possibilities, so we don't really need a default case unless we exclude one of them. And each one of these cases prints the direction we're going in. So we can say go north, then we break, go south, go east, and go west. Now, the break statement is very important because it will keep executing if it doesn't see the breaks. So I'll demonstrate that as well when I run the program, but let's go back up to our first case and we'll look. We should see cout of 1 and cout of go north. So let's run the program and verify these results. So here we have 1 and go north. Now let's see what happens if we remove this break. So I'll show you why that's important. This is a common error to make. We have case 1, we execute some code, and then we forget to put a break in. So let's see what happens in this case. So I'll do a Control F5 to compile it, recompile it, and run it again. And you'll see in this time it printed 1 and 2 because it didn't see the break, it kept executing. So it executes this line of code. This case doesn't do anything because we've already entered the switch of case 1, but it keeps executing until it reaches a break or it reaches the end of the switch statement. So in this case, it will see out 1 and 2 because there is no break. So really we want a break in there. So quite often we have case, some series of statements to execute, followed by a break, then the next case, and the same thing. So let's change I to something else. Let's change it to 3, which we don't handle, so it should get handled by the default case, which will see out some other number. And it does indeed print some other number. So that's the basics of the switch statement in C++ programs, and that concludes this demonstration. In this exercise, you'll create a basic C++ application. In this application, you'll use basic data types to perform arithmetic operations, and you want to do these arithmetic operations inside of a for loop. Now pause the video and perform the exercise, and when you've completed it, come back to the video and resume it to see how I did it. Now here's how I carried out the exercise. I've created a basic C++ application here in Microsoft Visual Studio. I've included IOStream to output our results and bitset because I'd like to show the bit representation of my basic data type. So in this case, I'm using std:/cout and std:/bitset. Now, my main function has a single for loop, and the basic data types I'm using are initialized in the initializer section of our for loop, so I'm creating an unsigned char c equal to 15. I'm going to iterate this for loop while c is not equal to 0. And the arithmetic operation I'm carrying out is a compound assignment using c right shift 1. So c double greater than symbol equals 1. So this will shift c by 1 bit to the right on every iteration. Now to see this working, on each iteration of the loop, I'm going to output the contents of c, or the 8 bits that represent c. And then each output will be delimited by a carriage return. So let me execute the program, and you can see what happens when we run this. So you can see 15 in bits is 1111, and the higher order bits are all zeros. So on each iteration, we shift by 1 to the right, so the bits get pushed to the right, and the lowest order bit gets dropped off. So it goes from 1111 to 111 to 11 to 1, and then this 1 gets pushed off the end of the loop, or the end of the character, and then the value is 0 and it exits the loop. And that concludes this exercise on creating a basic C++ application with loops and basic data types. In this video, I'll present how to define default arguments for a function in C++. So we're going to be using IOStream, which I've included here, and we're using standard cout. So this is going to output some things when we run our program at the end. Now I've defined a function f here on line 4 that returns an int, and it's defined with 3 integers as arguments, and they're all set with default arguments. So we have int a, and then we just put equals 1 to supply a default argument for a. B also has a default argument of 1, so int b equals 1, comma, int c equals 1. So each of our 3 parameters have default arguments. So we can call a function in a number of ways. So in our main function, we see that we call f. We can supply values for all 3 variables a, b, and c. So I have 1, 2, and 3, which will be set to the subsequent a equals 1, b equals 2, and c equals 3 when we call it with the 3 arguments. But we can also call f with no arguments. And that will say that we just want to use the default values for f. So a will be 1, b will be 1, and c will be 1. All the defaults. If we supply a single argument, let's say f called with 5, then a will be set to 5, and b and c will remain 1, If we call f with values 6 and 7, or 6, 7, then a will be 6, b will be 7, and c will be 1. Now, there's a few things that we have to keep in mind when using default parameters. Now, if I remove a parameter, let's say remove this one, the program is going to complain. You can see there's this little IntelliSense red squiggly line under f because we have a set to a default argument 1, but b doesn't have one. So anytime there's a default argument, wherever it is, every argument after that must have a default. So every subsequent parameter must have a default specified. So we can remove the default argument from a and b, and c is fine to have one because it's on the end. But if if b has one or a has one, then every parameter after must have one. So this is fine the way it's called here, with a and b requiring parameters and c having a default. The only problem is that we can no longer call f by itself with no parameter specified, and we can't call it with a single argument. So we'd have to comment those out for our program to work. Now in this case, f of 6, 7, it works the same way as it did before. So a will get set to 6, b will get set to 7, and c will remain 1. Now let me put those default parameters back. So b equals 1 and a equals 1. Now I'll save it and I'll uncomment these two lines, f called with no arguments and f called with 5. And I'll do a control F5. And we get some output so we can look at our solution. So in this case, let me move that down. So f gets called with 1, 2, and 3. So we get a is 1, b is 2, and c is 3. So 1 times 2 times 3 in our output. The second time we call f, we supply no arguments, so it uses the defaults 1, 1, and 1. So we get 1 times 1 times 1 in the output. F with 5, so a is set to 5, b is 1, and c is 1. And f of 6, 7 is 6 times 7 times 1. So everything looks and works as expected. And that concludes this demonstration on default function arguments. In this video, I'll present how to write an inline function in C++. Well, in C++, marking a function as inline indicates to the compiler to optimize the function, that taking the code from the function and putting it where the function call happens is preferable to requiring a function call wherever you see the function. So because there's a small amount of overhead needed to make any function call in C++ or C or basically any language, now there's a trade-off here, which usually results in a larger executable file size. So if you're replacing every function call you see, say every function f, with the actual code from the function, then putting that code everywhere results in a little bit more code, but it also increases the speed of computation. Now, even without the inline keyword, compilers that are set to generate optimized executables, like if you're passing optimization flags to the compiler, it may inline some functions anyway, even if they're not marked. Conversely, functions that are marked as inline might not always be inlined by the compiler, and the function calls may still be used when the executable is generated. So if the compiler sees that it's more optimal to actually have the function calls, then it will use them anyway. Now let's look at a couple of inline functions. One is implicitly inlined because it's a const expression, and the other is explicit because we mark it as inline. Now in this video I'm using the standard library IOStream, so we can use its cout to output some of our results. Now here I've created two functions. On line 4 I have a function f. Now it has a return type of int, but before the return type I label it as const expr or const expression, so const expr. So this tells the compiler to preprocess this function and replace the value, the contents of the function, wherever I see f. So this is done as a preprocessing step. So the compiler will generate code from this in an inline fashion. So all this function does is return the number 5, so the integer 5. Now the next function, g, it also has return type int, but this time we label it as inline. So that's all we need to do to label an inline function. And you don't want to use this too much. You only want to use it where you see a specific advantage to inlining the function. Now, if you don't, or you're not sure, just leave it as a normal function, and you don't always need to mark it as inline. You won't get a huge amount of gain. The modern compilers do a lot of work to optimize your code, to inline it if it needs to, and not to if it doesn't. So it's something that you should use sparingly, but if you see a specific advantage, if you think you're going to get a marked performance gain from inlining a particular function, you can always try marking a function as inline, compiling it, running some benchmarks against it, and see if there is an actual improvement. So this simple function g just returns the number 6. So for the sake of example, I've created two very simple functions. Now in our main function, I make calls to f and g. So on line 14, I do a cout calling the function f. So what the compiler will do, it'll see this function call f, and it will replace it with the number 5. So there won't be a function call that happens when the program gets executed. And the same thing for this cout of the function g. The compiler will most likely just see that, oh, this is a simple function that always returns 6. So we'll just replace this function call with the number 6. So when we execute the program, there's no function call that happens. So let me run the code. I'll do a Control F5 to compile and launch our simple application using our inline functions. And our results are, it just outputs the number 5 and 6, the function calls to f and g, which gets replaced because these functions are inline. And that concludes this demonstration on inline functions in C++. In this video, I'll present how to write overloaded functions in C++. So the basic idea is this. We have a single function, in this example the function f, that can take different numbers of arguments and different types of parameters. So by declaring multiple versions of f, we can accommodate these different types and different numbers of arguments. Now I start off in this program by including IOStream so we can get access to the standard cout to output some of our results. Now the first function f I define is of return type int, and it takes two integers as parameters, int a and int b. And it will return the product of a and b, so it returns a times b. Now we have another version of f that takes three parameters. So we have int f, and it takes the int a, int b, and int c, and returns the product of those three variables, so a times b times c. But we also want a version of f that can take on doubles and return a double. So if we need floating point precision in our product in this function f, then we can return a double from f and declare it as double a and double b instead of the ints. So we return a times b, that returns a double. And again, we can do the same thing with f where we want three doubles, double a, double b, and double c as parameters, and we return the product a times b times c. So let's look at this, how we call these functions, and what happens, what the compiler will see. So in our main function on line 22, we have a cout, and we pass to it the function f and two integers. Now in C++, or in Microsoft Visual Studio and C++, we can put our cursor over the f, and it will show us which function f it's calling, and it shows that there are different +3 overloads. So there's three other overloaded functions f, and the one we're choosing is the one that returns int and takes two int parameters. So I pass 2 and 2, which should return 4. And then the next call to f has f of int a, b, and c, so it takes the next version. And then if I pass 1.5 and 2.0, it will use the first version of f with doubles, and then f of 2.5, 2.0, and 1.0 calls our final function, our declaration of f, that takes three parameters, three doubles as parameters. Now, before I run the code, I want to note one problem that you might encounter when you're doing this. What if we mix and match integers and doubles? Well, I'm going to uncomment this last line of code, and you'll see right away Visual Studio with its IntelliSense picks up that f is a problem. So it has a little squiggly red line under it saying that, hey, this is not going to work because we don't know which version of f to use because we have parameters 5, 2.0, and 2. So we have an int, a double, and an int. Well, which one do we use? Well, we're not just going to keep declaring functions of f and mixing and matching all the possible combinations of doubles and ints. In this case, we might just say, well, we want this one to operate on ints because it's 2.0. So we'll just cast the 2 to an int, or whatever variable represents 2, and that fixes it. So it'll call, in this case, the version with integers. Conversely, if we still want a double returned, we can do the opposite. So we can take this 5, cast it to a double, leave the 2.0 as a double, and then cast the integer 2 at the end as a double. So that will call the version of f that takes 3 doubles and returns a double. So you don't have to declare every possible combination of f or the function that you want to overload. You can just do it for the main case, the most common case, and then just cast the input parameters when you know what you'd like f to be. So depending on the return type and what it's going to do with the variables, then you can decide which version to use by explicitly casting. I'm going to comment out this last version, and we'll just run it with these first 4 illustrating each of the versions of f that I've declared. So I'll do a Control F5 to compile and run the program. And we do get 4, 8, 3, and 5 as expected. Now if we close this window, we'll see that 2 times 2 is 4, 2 times 2 times 2 is 8, 3, and 2.5 times 2 is 5. So the results were as expected. Now note that there's another way to do this in C++ using function templates. So that might be an appropriate approach to what I have here, where we parameterize our functions by type. But that's a bit beyond the scope of this particular video. And that concludes this demonstration on overloaded functions in C++. In this video, I'll present how to pass pointers as arguments to functions in C++. So in this video, I start out by including IOStream, because we're going to be using the standard cout to output some values and addresses from our variables in our main function. Now I've created a function f that takes 3 arguments: a value in int a, pointer in int star b, and a reference to a pointer, so int star ampersand c. So there are 3 different ways to pass pointers, or in this case a value, a pointer, and a reference to a pointer, so we can look at how pointers are passed to functions in C++. So we need to differentiate them between values and reference to pointers. So all this function does is it changes the value of the int a. It sets a equal to 100. It sets the value that b points to, the value at b, to 200 in the pointer b. And it changes the reference to the pointer that c refers to. It changes its pointer to point to the same thing as b. So c and b will be pointers that point to the same thing. And then to show that the pointer doesn't change outside of the function, so the pointer that's passed into the function is passed through b, so we have a pointer b that points to the same thing as whatever is passed to this function. But if we change the pointer b inside of the function, it has no impact on the pointer that's in our main function that calls f. So this function f will illustrate a few common things in the behavior. So it'll highlight the behavior of passing by value, by pointer, and by a reference to a pointer. So let's look at our main function. So our main function declares 3 integers: int I, which starts out set to 10, j is set to 20, and k is set to 30. Then I declare 2 pointers, pointer y and pointer w. So these are integer pointers. The y we set to point to the same value as j, so we use the reference of j to say that y will point to j, the variable j. So it'll have the same address space, and if we look at the value that y points to, it will be 20. And then we do the same thing with w. We set it to point to k, which will be 30. So then we'll output all of our values and the addresses of y and w at the beginning before we call our function f, and output it after to see what changes and how it affects our variables and our pointers. So we output the values I, j, and k, the values pointed to by y and w, so star y and star w, and then the addresses, the memory addresses themselves that of the pointers y and w. And then we call our function f passing I, the pointer y, and the pointer w. Now w in this case is passed by a reference to a pointer. So what we'll do in the function, we actually change this reference to a pointer c to be set to b, the pointer b. So b and c will be the same, but c was passed in, or the pointer b was the pointer y from our main function. So after this function call, w, which is passed through c, will actually point to y. So y and w after the function call will point to the same address. Now you might say, well, didn't we change b as well? But b is only changing the pointer to point to inside of f. So the pointer b and the pointer y are two different entities, or two different variables. They're different pointers. But c is actually a reference to a pointer, so it's an alias for w. So you can think of a reference as an alias. So if we modify the alias, we modify the original. So w and y after this point will be the same pointer, or pointing to the same thing. So w will just be an alias for the pointer y after this function call. And I didn't talk about I, so we're passing the value I. So inside of the function, the variable a and I have no connection, because the contents, the value 10, is now the value 10 as the variable I. So calling the function just copies the value of 10 from I to a, and if we modify the value a, the variable a inside of the function, it has no impact on I. So after we call the function, we output the values and the addresses again to see what's changed and to see if it corresponds to our understanding of what's happening in the function f. So let me run the program and we can talk about the results. So do Control F5 to build and run the program here in Visual Studio. And if we look at I'll move this to the side in case we need to refer back to the code. If you look at I, j, and k, they're the original values 10, 20, and 30. Since y is pointing to j and w is pointing to the address at k, so y is the same value as j at the beginning and w is the same value as k. So we had 20 and 30 as expected. And the addresses of y and w are different pointers. So if we look at 00, F9, FE, A4, and then w, the difference is here at the last two digits are 98. So A4 and 98 are different between the two of them. So they're two different addresses. They're two different pointers. Then we call the function, and then what comes back? Well, I is still 10, even though we modified the variable a. Because they has no connection to I, it's just passed by value. The values are copied. Then I doesn't change, so it's still 10. We set to the pointer b what it points to. Because it's connected to y, which is connected to j, the value does change to be 200 because we change the value at b, which was passed in as y. So this pointer b is the pointer y, and its value points to the same thing. So j does get set to 200. After we call it, k doesn't change because we only change the pointer c. We didn't change what it pointed to, so k stayed the same. We only moved its pointer, so w was pointing to k, but we changed it to point to something else. So that doesn't modify k at all, so it's still 30. And then if we look at the values at y and w, since we changed the pointer, this reference to a pointer c, to point to what b points to, so which was passed in as y, it made y and w in our main function the same thing. So that both values are pointing to j, and they're both set to 200. And if you look at the addresses now, what the pointer addresses, they're both F9, FE, A4. F9, FE, A4. So they're the same thing. They're the same pointer. And that concludes this demonstration on pointers as function arguments in C++. References in C++ allow you to establish an alias for an existing variable. In this video, I'll present how to use references in C++ and some of the ins and outs when dealing with references and pointers. So in this code, in this program, I've included IOStream because we want to use the standard cout to output the contents of our variables and some of our pointers. So in our main function, I start off by declaring two integers, I, which is initialized to 10, and j, which is initialized to 100. Then I create a pointer p, an integer pointer, so int star p, which is equal to ampersand I. So the reference at I is what p points to. So p is pointing to the same address as I. So if we modify what p points to, then it modifies I. Then we create a reference. So the reference r, so int ampersand r, is equal to I. So r becomes an alias for I. And unlike the pointer, where I can point the pointer to another integer or another location, the reference I is fixed. So it will always alias I, so long as it stays in the scope of this main function. So after I've created these variables and initialized the pointer and the reference, I want to output their contents. So we want to see what they contain at the beginning of the program. So I output that on the first line, then I output the address of p and the reference of r. So we're going to see a hexadecimal address number for p and r. And at this point, because p points to I and r is a reference for I, their addresses should be the same. Then we'll see what happens if we modify I. So we change I, which is initialized to 10, we modify it and change it to 20. So what impact does this have on the values that p points to and r? So this should, if the reference and the pointer are valid, then they should all be the same. So I, since p points to I, it's if we reference the value at p, then it should be also 20, and r should be 20 as well, because r is an alias for I, and the address locations haven't changed. And then I'll demonstrate the same if we modify r. Then we'll output the values and pointers again. And then what happens if we modify the pointer p? So in this case, p now points to j. Well, p is a pointer, and if we change what it points to, it has no impact on the variable I, which it was previously pointing to, or the reference r, which still refers to I. In this case, only the pointer is updated, so it points to a new location. So it points to the reference at j, or the address at j, and p, if we look at what it's pointing to, the value, if we do star p and dereference the pointer, then we'll see that j is, it's going to be the value at j. So it should be 100. So at the end, p should be 100, which will differ from I and r. So let's run the code and see what happens and see if that corresponds to what I've just explained. So I'll do a Control F5 to compile and run the program here in Visual Studio, and we get our output window. So here we get I, star p, and r all set to 10, and the addresses of p and ampersand r are the same. Again, in the second example where we modified I and set it to 20, so all the values become 20, and there's no change in the addresses. And then again, if we modify r and we have the line where we said r is equal to 30, well, it updated I and star p to all be 30, and the addresses are the same. But then when we change our pointer p and point to the new variable j, it refers to something else. So I and r haven't changed, only the pointer p was updated. So the value that it points to, star p, is now 100, which was the same as j, and the addresses have changed. So you can see the address that p points to is different than the reference at r. So there are two different references now, two different addresses. So p is pointing to something else, but that has no impact on r or the address r or I. And that concludes this demonstration on using references in C++. In this video, I'll discuss how to use references as function arguments in C++ and why they're important to C++ programming. So at the beginning of my program, of my CPP file here, I include IOStream and string. And from those, I'm using cout to display some of the things that we're going to be looking at when dealing with references. And we're going to use the string object or the string class because I'd like to show what happens when you pass an object as by value or by reference in C++. So the first function I declare shows some of the differences between passing by value and two types of references. So this function f, which is of return type void, takes in an int a. So this variable will be passed by value. So whatever a contains will be copied to the variable a. But in the case of b, it's an int reference to b. So int ampersand b. So that's a reference to the variable b that's passed to this function. And then I'd like to demonstrate the syntax of passing a reference to an array when you're passing a reference to a function. So we have int, and in parentheses we put ampersand c, and then in square brackets we put 100. So in this function I'd like to demonstrate what happens to a when we set it to 100, b when we set it to 5000, and the first element of c, so c of array subscript 0, we set it to 5555. So I'm curious to know what happens to these variables that are passed into this function f when they're passed by value, passed by reference, and passed as a reference to an array. And then I've declared a function g here on line 13 of return type void that takes a reference but a const reference, so const double ampersand d. So this is a reference to d, but it's a const. That means we cannot change the value of d within this function. So we can reference it, so we can use it, we can display it, we can use it as part of an r-value expression, but we can't assign anything to it. So we can't change its value inside of the function. So this is very important when you're passing by reference, that if you're not going to modify the reference, then declare it as const to prevent any modification in case you do so by accident. So let me comment this out. We're not going to use this function. I just wanted to display that and show you what happens when you do try to assign something to a const reference. Now, passing by value and passing by reference when you're dealing with classes or objects, it's important to know what's going to happen. If you pass a big object, or let's say a really big string, and you pass it by value, it has to create a copy of that string. So you're duplicating the amount of memory required to store that object. So in this case, we're passing the string m by value. So it's going to create a copy of the string that's passed to this function. And then here I just display the memory location of m just to show you that it is indeed a copy and not the original object. And then we modify this string m to show that when you pass by value, it doesn't affect the argument, the variable that's in the argument of the function. So I'll show that below when I get to the code in the main function that actually calls this function. Now, by reference, it holds a reference to that object. So in this case, this function fr takes a string reference m. So it's going to have the same memory location as the string that was passed to it. And if I modify m, the string m inside this function, it will modify the variable that was passed to it. Now let's look at our main function. So I've got a couple of examples here. One dealing with our first function f that took the int by value, by reference, and the array of references, or the reference to an array. So we have int a is equal to 1, b is equal to 2, and I've created a variable c of 100 ints. So c, I just set the first element because that's all we're going to look at. So c of 0 is equal to 10. Then I call the function with f of a, b, and c. So a is passed by value, b is passed by reference, and c is referenced to an array. So then after I call the function, I look at the contents of a, b, and c. Then I create a string called ms that's set to hello world. I'm going to output the address of ms, so the reference to ms, so it's going to output some memory address. Then I call the function f with ms passing by value. Then I'm going to look at the contents of ms after I call the function. And ms should not be changed because it is passed by value, and whatever happens to ms in the function, it's happening to a copy of it and not the original object I'm dealing with here. But when I call fr with ms, since it's passed by reference, then if ms gets modified inside the function, it's going to be reflected here on this object ms. So if we change it, we should have a different ms. So this string will change, and we can see the results here. So just to recap, so f of abc will actually modify what's passed to it, but you'll see what happens in the end. So let me scroll up and let's run the code. I'll do a control F5. That should compile and run the code. And then we can see the results. So if I move this over so we can see some of the code while we look at the output. So A, B, and C, A is 1, B is 5,000, and the first element, the 0th element of C, is 5,555. So in the function, I set A equal to 1,000, but A was passed by value. So in the main function, it still retains its value 1, but B, since it was passed by reference, is modified, and C is modified as well because it's a reference to the entire array of ints where we've modified the 0th element, which does get changed. So instead of being 10, it got updated to be 5555. So that works as expected. Now, if we look at our string ms, the original memory location is this CFFA2C. So that's the reference to the string object. That's the memory location here. Now, from inside of f, when I pass ms to the function, this string m, since it was passed by value, m is a copy of ms. So m from the function f is a different address. So you'll see it ends in 924. So it's actually a different address than our ms from the main function. So it's a different string. So if I change m here, it has no impact on our string ms from the main function. So I changed it to high earth, and then when I output ms after the function call, it hasn't been modified. Only the copy was operated on. And then if I go down to our function fr, where we've passed the reference to ms, you'll see that inside the function, this reference m from our function fr has the same memory address as ms from our main function. So the strings point to the same string. So when I modify m inside the function, this reference, it actually modifies our string ms in the main function, and you can see it gets updated here in the output to high earth. And that concludes this demonstration on references as function arguments in C++. In this video, I'll present how to use references as function return values in C++. So I start out by including IOStream because we want to use cout to output some of the things that are happening in our code so we can verify our results and understand what's going on in the code. So I start off here on line 4 by creating an integer array, an int called g_array, which contains 3 values. And I'm going to initialize it to be 0, 1, and 2. So this g_prefix is to signal that this is a global function. So it's important when dealing with references that our reference that we're returning from a function is still in scope and that we haven't lost it when the function returns. So in this element ref function, so this int ampersand element ref, it takes an int I, which is an array index to this g_array. So it returns a reference to the element in the g_array. So it's important that when we return from the function that this variable is still valid, so this g_array. Now in this next function on line 10, it's declared in a similar fashion, so we have int reference called badref. And it takes an int I, but then it declares a local array, so int local_array with double brackets, and it initializes it to these values. So we have 10, 20, and 30. So it's a 3-element array, but it's declared as a local array. So this one is global, this g_array, and local_array is only local to this function. And then it returns a reference to an element from this array. Now, if you understand where this is going, so when this function returns, there's no guarantee as to what happens to local array after we return. Ideally, in a program, at some point, this memory gets freed and is no longer readily accessible, and it might be overwritten by some other function, by some other array or variable that's pushed onto the stack at some point. So there's no guarantee that this reference will be valid when we use it. So that's a very dangerous thing to do in a program, which is why I called bad ref. So this is an example of what not to do and what not to do when you're returning references from a function. And then I create this little helper function called output_array, which will loop over the elements of GArray in this for loop and output the element followed by a space. So since I'm going to be inspecting it a few times, I thought this little function would help instead of cutting and pasting this code in my main function. So we start out in our main function by calling output_array to output the contents of g_array. Then I get an element from g_array through the elementRef function. So this int v calls elementRef of 1. So that means the variable v has a reference to the element 1 from g_array by the way that elementRef is defined. And another cool thing with returning references, I can access elementRef2, and it could be an L value because it returns a reference, and I can assign the value 10. So this is perfectly valid because elementRef returns a reference. Then after these two lines, I output the contents of the array. Then I modify v, I set it equal to 555, and then output the array again. Now, in the second part of the example, using bad ref, what I do is try to set the first element, or call bad ref with 1, and set it equal to 5. So in this case, it's trying to set the element 1 from a local array to be equal to 5. But after that function returns, this local array is no longer in scope. So this is a bad idea. This can cause you all kinds of problems. And the same with this, even accessing an element from the local array, the first element set to the int w and then outputting the value w, there's no guarantee that w is going to contain anything, that it's still going to be valid, that it's going to point to what we expect it to, and certainly not, it's not going to be equal to 5 at that point. But let me run the program and we can look at these two parts of the example and see what happens. So I'll do a Control F5 to compile and run here in Visual Studio. And if we look at the results, you'll see some interesting things happen. So I've initialized GArray to be 0, 1, and 2. And when I call output_array the first time, that's exactly what we get, 0, 1, and 2. Then I set elementRef2 equal to 10. And that means the index at 2, this last element, is set to 10. But then, since int v is just a variable v, when it changes the contents of it, so when I said v equal to 555, it does not modify the contents of the elementRef at 1, which it got its value from. So v would have to be either a pointer or a reference itself to be an alias to this element, and not just a plain variable v. So it's actually a copy of the element and not the actual element, which is why elementRef1 did not get changed to 555 like v did. So that's working as expected. Now you'll see here when I call bad ref with 1, I set it equal to 5. But when it returns and I call it again, it reinitializes that local array, and that value, that index at 1, gets reset to 20 each time this function is called. So w contains that value, and it's perfectly fine to access it as w, and we get the value 20. But trying to modify it and it's local is a bad idea. So don't play with local variables or local arrays when dealing with return values or references as return values. And that concludes this demonstration on references as function return values in C++. In this video, I'll present how to use asserts for troubleshooting programs in C++. So I start off by including the header assert.h from the standard library, and we're also going to include IOStream, where we're using the standard cout to output some of our results. Now, first off, I start by declaring a function f, which takes a pointer, an integer pointer, or an int pointer j. So what I'd like to do is assert that j is not equal to the null pointer. So we want to make sure it's not equal to null. Otherwise, if it's fine, if it passes this assert, then it'll output the contents to whatever j points to. So it's very important that we're not trying to dereference a null pointer. And if our program's written a certain way, then this assertion is only checking something that should never happen or can never happen based on the logic of our code. Now in our main function, we're testing another assert. So let's say another common problem is a division by 0. So let's say I have this double I, which in this case is set to 1.0. Then I call an assert to make sure I is not equal to 0. Because when I call this cout, where I take 5 and divide it by I don't want it to be 5 divided by 0. So it's very important that we avoid this division by 0. But you see I have this little if statement. Now, in the case where it should never happen, or you don't think or if you think it's impossible that I is not equal to 0, but you're not really sure, and you want to test it, especially when you have a very large program, and you're troubleshooting errors in debugging it, you want to put some assertions in to make sure that none of these edge cases can happen. If you're trying to handle a real error, if the value of I can take on 0 in some logical way or some valid way, then instead of doing an assert, you should actually handle the case where if I is equal to 0, or in this case, if I is equal to 0, we want to handle it in some way. So we put the code in and we do something if I is equal to 0. However we'd like to handle it to make this division valid, or even to skip this division altogether might be part of your solution. So it's only for the cases that should be impossible you want to put the assertions in. On things that should have proper error handling, use the actual error handling and avoid the asserts. So that's just some words of advice at using asserts versus actually handling the cases that can happen. And this other example, I have this int k, this pointer k, that I'm initializing as a null pointer, and then I set k equal to new int, then I set the value that k points to equal to 10. I call the function f with this k pointer, so it calls this function f, it performs the code, and then after it's completed, it deletes k. So that should all work fine, and if I call this function as is, none of these assertions will happen. So let's just run it for the first time to make sure everything works as expected. So I did a Control F5 here in Visual Studio to compile and run the program, and I do get 5 and 10. So 5 divided by 1 is 5, and the value star k, which gets outputted in the function f, is 10. Now let's change it to make these assertions happen. So let's set this to be 0, and if I want to be proper, this should be 0.0. So now this assertion should happen when I run the code. So assertion failed, I is not equal to 0.0. It shows me the file this assertion happened in and the line it happened on. So that's very important to have, where we can pinpoint what assertion was called. So let's abort this, and the program ends. Then I can go in and fix my problem, and I can change this back to something else, let's say 2, so that it doesn't happen again. Now in this case, what I'm going to do here is I'm going to comment out k equal to new int, and I'm going to comment this out. So when I pass k to the function, it'll be set to the null pointer, and so this assertion should get executed. So I did a Control F5 to compile and run, and you'll see here I get the first result, 2.5. The division was fine that time because the double was okay. There was no division by 0, but I get an assertion failed here. J is not equal to null pointer, and it tells me where it happens, what file it happens in, and what line it happens on. Now, if I want to turn assertions off, because assertions should only be used when you're debugging your code. In production, you should not have these assertions. They should not be left in. So we do a define and debug to turn off the assertions. Now, if you're using a particular build system, you might have it in your build settings where ndebug is defined for your release build, but your debug build, it's not defined. So let me run it with ndebug and see what happens. So here it just hung. Let me hit cancel. It had a problem when it got to this line because the assertion didn't happen. And if I make one more change, I'm going to set double I equal to 0 so that this division is a division by 0, which should be a problem because the assertion is skipped because I've defined ndebug. And you'll see here it just shows INF because there's a division by 0 and the program stopped working. So it doesn't abort or shut down nicely if I skip over these assertions and I let the error happen. So if I let the program fall over in some bad code from some null pointer or division by 0, it's not quite as nice, and it's harder to track down where that problem happened compared to when I do the actual assert. And that concludes this demonstration on using asserts in C++. In this video, I'll discuss exception handling in C++ programs. So for this video, I'm including IOStream, and I'm including the standard exception class. So from IOStream, I'm using the standard cout to output some of our results. And from the exception class, I'm using the standard bad_alloc. So this is an exception class for handling allocation failures. Some of the other standard exception types, so we have the bad_cast for dynamic cast failures, bad exception for bad dynamic exceptions, bad type IDs, bad function calls for empty or invalid function calls, and bad weak pointer for invalid weak pointer with respect to its shared pointer. Now in our main function, I have two examples of handling exceptions. So handling exceptions in C++ use the try-catch paradigm. So we try some block of code, and if there's an exception thrown in it, we try to catch it. So we catch, and then we have to catch the particular type of exception we're looking for. Otherwise, if we're trying to catch any exception or an exception of some unknown type, we can use the syntax for catch. So we have catch, and in parentheses, we put an ellipsis, so period, 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 or dot, 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 and that'll handle any uncaught exceptions. And so this is kind of the default exception handler, this catch with the ellipsis. So in this example, it's a fairly pedantic example. I just throw the integer 5 so we can demonstrate it. And when I run the program, you'll see it catch this integer. And then the subsequent time that I'll run it, I'll change this throw to be something else so we can see the default exception handler in action. Now the second example is something you might need if you're in a memory constrained system, or if you're trying to allocate too much memory for the amount of RAM you have. So in this case, I create an int pointer myArray, which is allocated using new. So I do new int, and it's an int of size 10. Now, if this was a very large int, like much, much larger, and it fails to allocate, I could get a bad allocation exception. So I catch bad alloc, which is a reference to E, and then I can say here that I caught this standard exception or this bad alloc exception. And here the exception has a function called what, so it tells me a string of what that exception was. So let me run the code and we can see this in action. Now the second one, there's no chance that this system will fail to allocate an int array of 10, but just be aware that this is the code we use to catch these bad alloc exceptions if it were to fail. So I'll do a Control F5 to compile and run, and we can see that in the first try catch, we caught exception 5. So that's what we threw. We threw the 5, and it was an int I, and we've outputted it using cout. Now if I change this to something else, let's say 5.0, it changes it from an int to a double. So we're trying to throw a double this time, and it won't be caught by this int I exception. And in this case, we get handle exception of unknown type as expected. So these are fairly common or simple examples, but if you come from a language like Java, you'll be quite familiar with this type of exception handling. If you come from C, then this is quite new to you. In C, we returned return codes or handled global error objects or error structs, and we just pass things around by returning them and looking at return codes rather than throwing and catching exceptions. And that concludes this demonstration on handling exceptions in C++. In some special cases, such as with embedded systems or performance-critical applications in hardware, where timing is important, we may want to suppress allocation errors and handle it directly. Since throwing an exception when allocating or freeing memory is not an option, it needs to be handled differently. What we can do is suppress the exception and handle the error directly with no throw. In this video, I'll demonstrate how to use no throw with new and delete to suppress the exception handling in C++. So for this video, we're going to include IOStream to use cout. We're going to use string as part of our example. We're going to use exception for bad alloc, and we need to include the standard library new header so that we can incorporate no throw. So you can see here on line 8, I'm using the standard no throw in this example. So in our main function, I have 3 small examples. The first is the standard case. So we do a try, we attempt to allocate memory, and what we do when we allocate it, well, we just delete it. So this is a bit of a simple, trivial example, but what happens is, in the normal case where we don't suppress the error, we do a regular new and delete, and then we catch a bad alloc exception. So this will output e.what, the string for the exception, if it does fail to allocate this integer I've called with new int, or if it fails to delete it. So that's the usual case. Now the next case is where I want to suppress the exception. So here I'm allocating a string using new string, but after the new, in parentheses, I put no throw. So this no throw is a part of new, and what it does is it tells it not to throw the exception. So no throw is an object from the standard library that uses a different version of new and delete. So instead of throwing a bad alloc exception, no throw's version returns a C++ null pointer. So what we do in this case, if it fails to allocate, we just test to see if the pointer is null. In this case, if it's equal to null pointer, then we handle however we need to handle it in our program. In this case, I just do a cout saying there's a memory allocation error on the variable s. And then I return from our main function. And then if we call new using no throw, we have to call delete using no throw. So here we do delete, and in parentheses, our first parameter is no throw, followed by a comma, then the variable that we need to clean up. In this case, the variable we need to delete is s. So if we allocate with no throw, then we should delete with no throw. And the same thing with an array, using the array syntax. So here I create a character pointer C using new no throw, and it's an array of 100 characters. And again, if instead of trying to catch a bad alloc exception, I just test to see if C is equal to null pointer, then I handle the error, here the memory allocation error on C, and I return 1 from my main function because it had an error. If everything works out well, then I'll delete C, so I do delete with our double square brackets for deleting an array. I pass no throw in parentheses, followed by a comma, then the variable we need to delete using the array we need to delete, in this case C. So let me run the program and make sure that we don't get any allocation exceptions, and everything will work fine. So there shouldn't be any output in this program because all of our output only happens when there's a bad allocation. In the first case, if it throws an exception, and in the other cases, because they're suppressed, that means our variables that we've allocated will be null pointers, and that shouldn't be the case here. So we shouldn't see anything put to the screen. So do Control F5 to compile and run. And it just says press any key to continue, so no allocation errors happened. And that concludes this demonstration on suppressing allocation exceptions in C++. The C++ standard library string class is more than just an array of characters. In many respects, it acts like a standard library container, but a container of characters, with many of the same utility functions that containers have. In this video, I'll present some of the features of the C++ standard library string. So for this video, for this example, I'm including IOStream, and of course, since we're working with a standard library string, I include the string header from the standard library. And then I'm using cout so we can see some of our results and see some of the things about how the string class works. And of course, we're using the standard std : string. So we want to use string directly from the standard library. And one more thing I'm using is I'm using the namespace, the standard string literals. So std : string _ literals. This will give us a little handy utility when creating strings using auto. Now let's look at string creation. So how do we create a standard string? Well, one way to do it is to create a string. So we define a string s1, and we set it equal to some string of characters. Now, if we hover over this with our cursor, we'll see that it picks up a const char of hello world. So this could easily be defined in the C way, doing a const char star of s1, and it would work just fine. But if we want to be smart about it, let's create it as a string. So we're creating a standard library string from an existing set of characters. We can also use the auto keyword, so we use auto s2. Now this will create a string because we've put this suffix s. So this suffix s at the end of a string is part of the string literals that I've included, and that tells the compiler that this will be a string and not a const char star, like it would deduce by default without the s at the end. So these are two ways you can initialize strings or create strings, the standard library strings in C++. And then I just output the contents, so we should have hello world and then hi earth as our two strings, and then we have a carriage return after each one. Now we can concatenate strings, and it's not just strings that we can concatenate together, but we can also concatenate character strings, more C-style strings like this const char star sep for a separator, which in this case is just a space character. So we take our s1, we do a plus equals the sep for our separator, and then to that we add s2, our second string. So this will have hello world followed by a space and then hi earth, and it will be concatenated onto the string s1. And then I do a cout of s1 followed by a carriage return so we can see that result. Now at the end of the program, I'll run it and we can run down through all these couts and see what the output of the program is. Strings also support a find function, so we can specify a string to find, and it will return the location, the position in the string where it occurs. We can do substrings, so we specify a range of characters, so we specify a starting position and a length, and it will return the string from that starting position with that many characters. So in this case, we do s1.substr, and we give it argument 7 because I want to start at the 7th character and go for 6 characters. And then we'll output the contents of this new string created by substring. We can get the length of the string. Now the length supports two methods. We can call the size member function on the string, so s1.size function, or s1.length, but they'll return the same thing. Now, size gives us compatibility with other standard library containers. They typically use the size function, but when we're dealing with strings, quite often we think of the string as in terms of the length of the string. So size and length are both synonymous ways of getting the number of characters in the string. And like C++ standard library containers, we can iterate over a string one character at a time with a typical iterator. So I do a for loop for auto reference ITR as my iterator. Now I'm declaring the iterator auto, so I don't have to define the type of it, but it'll deduce it because we're starting at the beginning of the string. So s1.begin gives us a pointer to the first character, an iterator to the first character in the string. And then while the iterator is not equal to the end, we increment the iterator, and then we do a cout of star ITR, so this will return the character followed by a space. So we'll get the entire string of S1, each character one at a time with the space in between each character. And then I do another cout, carriage return, a \n, to put another line at the end of the file. So let's run the program. I'll do a Control F5 to compile and run, and we can verify our output and see that it matches what we have here. So let me move this to the side and we can run down the output. So we get our hello world, hi earth strings that we've created, the concatenation with the separator, so hello world followed by a space followed by hi earth from S2, so the concatenation looks fine. Our find finds the word hi, the location of hi in the string is at the 14th character, so if we count from hello world, exclamation mark, space, and then the hi, this will be starting at the 14th position. If we take a substring from the 7th character and we take 6 characters, so the 7th starts at the W in world, and then it takes 6, so the 5 characters from world and the exclamation mark. And that's what it outputs, so world, exclamation mark. The size of the string, or the length of the string, the size is 24 and the length is 24, so we have 24 characters in the string. And then finally, when we iterate over the string, putting a space in after each character, so this iterator sees the string as a container of characters and iterates over the characters one at a time, putting a space after each one, including the spaces. So you get a double space anywhere where there's a space because we're adding one in. And that all seems to work as expected. And that concludes this demonstration of the string class in C++. The C++ standard library provides a variant of its string class called wstring, which is used for wide character types instead of the basic character type. So we can support the widest variant of a character on our system, such as UTF-16 or UTF-32, instead of the basic UTF-8, if we need it. In this video, I'll present how to use the C++ wide string class. So for this video, for using wide strings, we just include the standard library string header, and since we're going to do some output, we include IOStream. Now the standard cout for outputting single byte characters, the standard char or the standard string, we use cout. But for wide characters, we need to use a variant of cout called wcout. So we also are using our string class, and we're going to be using the standard wstring. So we put using std : wstring, so we can use that from our string library to support wide strings. And I'm also going to be using the namespace std string literals. So string literals provides us with some prefixes and suffixes that we can put around strings so that we can determine their type. So in our main function, we start off by outputting the size of a single char on our system, and we output the size of wchar t, so the wide character type. So we want to see if it's going to be a UTF-8 or UTF-16 or UTF-32 character size. So it'll be 1, 2, or 4 bytes. And the char should be a single byte. Then let's create a couple of strings. So I'm going to create a W string S1, and the string, to signal that it is a wide string, we need to put the L prefix, so that tells it that this string literal is going to be wide, and the suffix S tells the compiler that it's going to be a W string instead of a wchar t pointer. So if I remove the S, changes what this sees. So if I highlight here, you'll see this const wchar t 14. So it changes the type. So if I put the s back, it will deduce it to be a string automatically. Now this is not always strictly important when we are telling our variable that we want a w string, but if we're using the auto keyword, letting the compiler determine the type, the uppercase L prefix on the string and the lowercase s suffix is very important. So this will signify that we do indeed want a wide string or a w string from the standard library. And then we'll just do a w cout on S1 and S2. Now if I try to do a regular cout, it will give me an error because it doesn't know how to handle a w string. The regular cout doesn't. So we need to use the wide variant or w cout. Now in other cases, if we're just outputting the size or the length of the string, which will be the same value, then doing a regular cout is just fine. So we look at s1.size and s1.length, and they should be the same because size and length. So the size is a carryover from container types that are inherited by string to say that, okay, this is the size or the number of characters in this string, and the length is how we commonly refer to string sizes. We refer to the length of the string. So let me run the program and we can have a look at the output. So we can see the size of a char in this system is 1, but the size of a wide character is 2. Then we output our hello world that we created and our variable s1 and our variable s2 hi earth. And the length of our s1 string, the hello world, is 13 characters. So the size and length are both 13 as expected. And that concludes this demonstration of the standard library wide string class. There are many instances where we find ourselves working with C code from C++, or converting C programs into C++, or using legacy code that had C-style strings that we want to incorporate in our C++ programs. It may not always be feasible to rewrite C-style strings into C++ standard library strings, and in many cases, if the code is robust, it's not necessary. But we should know how to work with it and interact with C-style strings. In this video, I'll present how to work with these C-style strings in C++. So, working with C-style strings and some of the functions around it, we'll be including C-string, C-standard.io, and C-standard.lib in our C++ program. So in our main function, we create our first string, in this case a const char star s1. So this will be a constant character string, and the memory set aside for this const char star will be based on this hello world. Now it's not going to be allocated like we would using a malloc. It's going to be on the stack, so it will automatically be released when we exit from the function. And then we'll do a printf star s so that we see the contents of it and see that it was allocated correctly. Then we can create another string from s1 using stirdup. So this will duplicate the string, make a copy of it, but stirdup allocates memory for the new string. So this char star s2 will be required to be freed at the end. So stirdup calls malloc internally, so it allocates the memory for s2. So we have to make sure once we create this s2 that somewhere at the end of our program, at the end of our function, we call free. So in this case, we have free s2. So what I do with s2 is we're going to modify it using stir copy. In this case, stern copy. So stir and copy s2. We're going to set it to the string. We're going to copy in the string this constant string hi world instead of hello world. And we give it one more parameter because it's the stir n variant of stern copy. We give it the length of s1 because that's the maximum size s2 can be based on how we created it. So this makes sure we don't go off the end of the buffer. So we're not going to get a buffer overflow with this. So it's going to force it, if we try to give it too many characters, then it will be truncated at this number of characters, at the length of s1. That's the maximum number of characters we can copy into s2. So that prevents a buffer overflow in this code. And then we do a printf on the string. So printf takes the %s as the place where we want to put our string s2. And then we're going to create another string s3 based on the lengths of s1 and s2, plus a bit of padding, so we add another 10 characters to give it a little bit of extra space on the end. So we create a char star s3, then we cast from malloc char star, so char star in parentheses, malloc, then we take the length and multiply it by the size of char. So we want this length, this many characters, to be allocated for s3, and then every time you write your malloc function or see a malloc, make sure you see the corresponding free somewhere down later on in the code or at the bottom of your function when it's cleaned up. So in this case, we have free s3. So we're fine. So I'm going to use stern copy and stern cat to give s3 some characters. In this case, it's going to start with the string s2. We're using the n variant, so the stern copy, so we provide the length, or the len variable, which is the length of the maximum length of s3. This will assure that we don't run into a buffer overflow. And then we do a stern cat to add a space, and then a stern cat on the string s1. And then finally, we do a printf on s3 to output the contents of it to make sure it contains hi world, followed by a space, followed by hello world. So let's run the program and make sure everything works as expected. And we get hello world, hi world, and hi world, hello world. So S1, S2, and S3, the strings all look okay. Now I'll make one quick modification. Instead of these stern copies and stern cats, what I'd like to do is do a sprintf. And this will give it our buffer, the format like a printf, so %s space %s, and then we give it the strings. So in this case, s2 and s1. So the space is part of the formatting, and then we can just remove these 3 lines because this single line, this sprintf, takes care of the whole thing. Now again, there's also the sprintf, or is it sn printf variant that will take a size, so we can specify the len. So sn printf, we specify a length. So again, we can avoid any buffer overflow because once it reaches len, it will stop copying characters or stop printing characters into S3, so we can avoid any buffer overflows. Now if I run this program again, do a Control F5 to compile and run again, we should get the same result, and we do as expected. So S3 still contains hi world, hello world. We just did it in a different way. And that concludes this demonstration on C-style strings in C++. In this video, I'll present how to work with null-terminated strings, C-style strings, in C++. So since we're using these C-style strings in a null-terminated fashion, we need to include the C string, the C standard IO, and the C standard lib headers to use these type of strings. So the first string we're going to create is just a fixed character buffer, char s1, of 100 elements. So in square brackets we put 100, so it's a character array. So this buffer we're going to populate with a couple of strings. We're going to pack the strings in with null terminated characters. So for this we do a sprintf, which will automatically put a null terminator at the end of our string. So I'll do a sprintf onto s1, and the formatting will just be %s in this string, and we want to sprintf, or put the string hello world into this buffer s1. And one of the neat things about sprintf, it returns the length. So when you can, you should always try to capture the length from sprintf. So I create this int len to hold the length of our string s1. Now this is important, and it lets us avoid having to call strlen on s1 later on. Instead of those extra calls, we just capture the length here in a variable, and we can reuse it. So what we use that for is to pack another string inside of this character buffer s1. So we do a sprintf on s1 plus the length, so the len plus 1. So this will S1 will give us the start of our character buffer S1, but we want to step to the end of our hello world. But since there's a null terminated character, we want to step past that. So we want to step past this the 0 character, so we go +1 past that. But then we can sprintf into that part of our character buffer, this %s, which gets populated with hi world ! And sprintf automatically puts in the null terminator. And here we capture len2. Although we don't use it, it's a good practice to capture the length from sprintf in case you need to use it later and avoid that extra call to stir len. And then here we do a printf on S1, which should just print out hello world ! Because there's a null terminating character that comes after it. But if we step past the null terminator, then we get our second string hi world, which should get outputted by this printf. So we printf S1 plus len plus 1. Now we can do something similar with another character buffer, but this one, for the sake of doing something different, we'll do this char star S2 that's allocated using malloc. So we do cast to char star malloc 100 times the size of char. So since we've allocated this, we need to make sure later on in our function or in our program that we free it. And in this case, down on line 19, we call free of S2. So it's good practice that anytime you do a malloc, you look to make sure that you have the corresponding free. Then here we do a sprintf onto S2, hello world. But in this case, what I'd like to do is split this string on the space. So what I'm going to do is insert a null terminating character, a \0 or 0 character, on the space after hello. So on S2 at position 5, I'd set the character in single quotes a \0. So this will split the string in two. So if I do a printf on S2 at this point, it will see a null terminator after hello, so it will only print hello. And then if I do a printf on S2 plus 6, which would put us to the W, it will print world. So we have two strings, two words packed into this character buffer S2. So now let's run the program and make sure that our results correspond to what I've just explained. And when I compile and run it, you'll see I get hello world and hi world in the first two strings as expected from S1, and then I get hello and world from S2 after I've put the null terminating character after hello. And that concludes this demonstration on null terminated strings, C-style strings in C++. In this video, I'll present how to declare a namespace in C++. So namespaces are important because we can avoid conflicts in variable naming or object naming by using a namespace. So if we have a namespace, ABC, and in braces, so everything that falls within this section of code between the braces falls under the namespace of ABC. So we have int ABC in lowercase, part of the namespace, the uppercase ABC. So if we want to access these variables, then we need to go through the namespace. And if these variables are declared elsewhere in the code, if int A, B, and C appear somewhere else, we can still get access to these ones in the namespace by specifying the namespace first. So we just declare a namespace, ABC, and in braces we put anything that we'd like to fall under that namespace. And it just doesn't have to be, we can do other things, not just these simple variables. We can do functions and classes and structs and enumerations, all under the namespace. I can create a second namespace here, namespace XYZ in uppercase, and I put the ints X, Y, and Z lowercase inside of these namespace. And then I'd like to show you how to declare a namespace of namespaces. So I'm calling this namespace uppercase ABC underscore uppercase XYZ. And this will be a combination of namespaces from ABC and XYZ. So it'll incorporate these two namespaces I declared first into this one single namespace. So inside of it, all we have to do is put using namespace ABC, followed by a semicolon, and using namespace XYZ. And everything that we have in ABC and XYZ are available in the namespace ABC underscore XYZ. And then you'll see in our main function, we have ABC double colon A. So this resolves to the A that belongs to ABC. And we can assign a value to it, let's say 1. And then we have our namespace XYZ, double colon, and Y. So the Y of XYZ is assigned 2. And then we can access Z from ABC XYZ, or ABC underscore XYZ, double colon Z, and we assign that 3. So if I went into the code and put another variable, let's say int B, well, there's 2 B's in our program. There's one in the namespace ABC and one in our main function int B. So if I do B equals 1, then it's guaranteed to be this one in the main function that we've declared. But if I do ABC double colon B, it refers to the one from the namespace. So these are 2 different variables, and we avoid a naming conflict by having a namespace to resolve our B's. And that concludes this demonstration on declaring a namespace. In this video, I'll present how to use a namespace in C++. So in this video, we're going to be outputting some of our variables to our console window when we run the program, so we need to include IOStream, and we need to use the namespace std double colon cout. So we're going to be using cout in this program. Now this right here, this using standard cout, is an example of using a namespace in C++. So we're ensuring that we're using the namespace, or we're telling our program that when we reference cout, we're referencing the one from the standard namespace, the namespace std. Now, in many simple programs, you might also see a using namespace std. This will bring in everything from IOStream that has the namespace std and make it all available. Now, having this kind of global, this broad cutting using namespace std opens it up for a more likely chance of a conflict. So I recommend just using std double colon cout. So we're just using the object or function or variable that we want to have access to in our program and nothing else. Now I declare another namespace, namespace ABC, with 3 ints, int A, B, and C. So in my main function, if I declare an int A, I have to specify which A I'm using. If I just reference A, then I'm using this local one. If I reference ABC double colon A, so if I prefix it with the namespace and the double colon, so if I resolve the namespace of A, I'm fine. But if I try to use using ABC A, that tells the program anywhere after this you see A, you want to use the one from the namespace. But this is going to cause an error because we already have an int A declared locally. So this will cause a conflict because they both can't be, we can't use both of them as A. So we'd have to remove this for it to work. And then I do another using. This one's fine because no B has already been declared. So we're using ABC double colon B. So anywhere after this using statement, if we reference B, we mean the one from the namespace ABC. So there's no ambiguity here because there's only one B. So I have B equals 10. And then I reference C because I'm not using it yet. So ABC double colon C. So we're using C from the namespace and I assign it 100. And then finally, I just type in a broad using namespace ABC, which will make all of our variables ABC available to the compiler. But if I compile and run it, we see that, wait, there was no name conflict. So you might have been thinking, if I close this, that there'd be a conflict with A and A if I type in using namespace ABC. Now, the conflict will only come up if I try to do something with A. So since I've only been using this local one, and I haven't referenced the one from the namespace anywhere in my code, this using namespace ABC is fine and doesn't cause any conflicts with A. So indeed, when we run the program, we see that our variables ABC, A is equal to 1 because it's referencing the local A, B is equal to 10, and that's B from our namespace, and C is equal to 100, which I've assigned here on line 14. So we get 1, 10, and 100 in our output. And that concludes this demonstration on using a namespace in C++. In this video, I'll present how to create a namespace alias in C++. So where namespace aliases come up is when we have very long namespace names. So if the namespace is very long and we need to reference it, then it makes it easier to create an alias, usually some abbreviation of it or some shorter name that we can reference. So we don't have to type out a very long namespace name everywhere in our code. So in this example, I create a namespace called a very long namespace name, delimited by these underscores, and this namespace contains a single function f, which uses cout and outputs a string, a function, followed by a carriage return. So in my main function, before I call this, I create a namespace alias, and all I need to do is declare a new namespace, so I type namespace, the new namespace name equals the old namespace name. And that's it. That's all there is to creating an alias, although we do have to make sure that our new namespace name is not included elsewhere in our program, and there's no other conflicts by using this shortened named. So then I can just call our function with a:\f and our parentheses for a function call. So now let's compile and run the code, and we can verify that it works as expected. And it outputs a function as expected, and that'll conclude this demonstration on creating a namespace alias in C++. In this video, I'll present how to create a C++ application that uses the standard namespace. So I'm including two headers from the standard library. I'm including iostream and string. So in this program, in this main function, I create a standard string. So I do std:\string. So I reference the standard namespace and the object, the string, and I create a string s, and I set it equal to hello world. And then on the next line, I'm using cout from iostream. So I use std from the standard library, :cout. And then I give it the variable s and a carriage return at the end. So that should just output hello world followed by a carriage return, and then that's the end of our program. So if I do a Control F5 to compile and run, that's exactly what we get. We get our hello world string. Now, if I'm using a lot of strings in my program and I'm calling cout frequently, having to type this std:\, can be a bit cumbersome. So in programs, quite often we'll see using namespace std followed by a semicolon. So that lets us remove all these std:\, so we don't need to resolve these standard library objects. But we could have a very large code base which has their own definition, probably not their own definition of cout, but it could have a different definition for string or for some other object we get from iostream or string, or from some other standard library, or from some other library that we're using a namespace for. So in the standard namespace, in a small example program, quite often we just do a using namespace std, and we can avoid all that extra std:\, typing. Now, what I'd recommend is not going this far. This is a pretty broad knife to cut with, a double-edged sword, so to speak, because when you have a broad using namespace like this, and you include other standard library headers, you increase the chance of running into a conflict. Now, I think you should always know which objects and which variables, which definitions you're using from particular headers that involve a namespace. So instead of using the entire namespace std, I recommend just using the elements that you're getting from the various headers. So in this case, we're using the standard cout from the IO stream. So we just type using std : cout, and we're using string. So we do std : string from our string header. And that accomplishes the same thing. So in this case, we reference in our code in a very specific fashion what elements we're using from our standard namespace. And I believe this is a safer way to go, especially when working with a larger code base. So I'll do a Control F5 one last time to compile and run to make sure we do get the same result as we did when we first ran it. And we do. We get our hello world result. It's just the same. And that concludes this demonstration on the standard namespace. In this exercise, you'll create a basic C++ application that includes functions and namespaces. Then use exceptions in this C++ application, use references as function arguments in C++, and perform basic operations on strings in C++. Now pause the video and perform the exercise, and when you've completed it, come back to the video and see how I did it. So here's how I carried out the exercise. Now you probably did something different, that's okay, and that's expected, but as long as you've gotten all of the elements from the exercise, that's okay. So I start out by including IOStream and string, because we're going to be using some strings in this application and doing a bit of string manipulation. And we like to output some of our results, so we're using IOStream so we get access to cout. Now I'm using the standard cout, so instead of referencing the namespace, we're using std : cout. So when we use a cout in our program, we're using this standard variant, and the same thing with string. We do a using std : string. Now the namespace I've created for this application, or in this application, is called ABC. So I have namespace, uppercase ABC, and in this namespace, I create a function that accepts a reference as an argument. So I have this const string &s. So this const reference, so that it guarantees that s cannot be modified inside of this function f. So it's not going to return anything, but it's going to output a string. So it's going to take the string parameter s and call cout, but it's going to take the string hello, comma, space, and then append our string s. So C++ will know that we want to append a string in this case. Now in our main function, I create a string in this try block. So in our main function, I do try, and then I open a brace, and inside this try block, I have string s equals world ! And then I reference the namespace ABC, so ABC : f, and I pass it our string s. So this will be passed by reference. And then to simulate an exception, I just throw the integer 5. So that will be caught by this catch block, so catch int I, and then it will cout, caught the exception, and the number that's in the variable I, in this case 5. And then I have the default exception handler, this catch with the ellipsis, so ... and some other exception caught. So this is an unhandled exception put in there for demonstration's sake. So let me run the program and verify that what I did was correct, and make sure my exercise is complete. So in this case, I get hello world printed from our function f inside of the namespace, and we also have caught the exception and the number 5 as expected. And that concludes this exercise on using C++ functions, exceptions, and strings. In this video, I'll present the basics of class creation in C++. So for this video, I've included IOStream, because we're going to be using the standard cout to output one of our results. So here on line 4, I define a class. So I use the class keyword followed by the name of the class I'd like to create, in this case line. So I'm creating a class called line. And then the class starts with an open brace. I define my class, and then I have a closed brace followed by a semicolon. So this semicolon at the end of the class definition is very important, otherwise it won't compile correctly. And then I declare the type of access I want to the members of my class. Now in this video I'm going to keep it simple, and I'm going to make everything in the class public. So all of the variables and member functions will be publicly accessible. That means whoever creates a class of type line will have access to the member variables and the member functions. So this class line is defined by the slope of a line and its y-intercept. So it's in slope-intercept form. So we have y equals mx plus b. So m is the slope of our line and b is its y-intercept. And then we can find some value of y given any value of x. So I've created my first member function called set. So it's returns of type void, and it takes two arguments, two doubles, I and j. So the first argument, or the first parameter, I, is the slope, and the second j is the intercept. So I set m, which is the local m, this member variable m, I set it to I, and then b I set to j. So you'll notice that this function, this set function, is defined right here inside the class. That's one way we can do it. Another way is what I've done with findY. So this function findY, which returns a double, takes in a double x. So it takes in an x argument and returns the given y value for that value of x. So let's look at my implementation of findY. So here on line 17, outside of our class line declaration, so our class line is defined between these braces and ends at this semicolon. Now if we go down to line 17, you'll see a function that returns double. It's part of the class line, and it is the function findY. So we have line double colon findY as our function name, and then it takes an argument double x, and we define our function body here. So all it does is return m times the parameter x plus b. So m and b come from our class members m and b, and x comes from our function argument. So quite often in C++ programs, we'll have our class defined, so our class definition in a header file, let's say line.h, and our implementation, our member functions are implemented just as I've done here in a file like line.cpp. So anywhere we need our class line, we include its header file, and all of the function definitions stay in the CPP files. So that's quite a common way of implementing a class like I've done here. But for the sake of simplicity and showing it all in a single file in this video, I have the entire class line defined here and its member function right underneath it. Now let's look at the main function. So I create an instance of line by specifying the line class. So I just specify line followed by the variable I'd like to create. So in this case, I'm creating a line called a. So this variable a, I can call any of the member functions or access any of the member variables by specifying a followed by a dot or a period, then the name I'd like to access. In this case, in line 23, I do a.set, calling the set function, and I pass it the values 2.0, comma, 10.0. So 2 will be the slope and 10 will be the y-intercept. And then I call findY inside of this cout statement. So I have cout, a string y colon, then I call a.findY, and I want to find y where x is equal to 5.0. So in that case, we'll get m, which is 2, so 2 times 5 plus 10, which will give us 20. So we should see 20 as the output for this findY call on a, and that's the end of our main function. So let's compile and run the program and verify that it all works as expected. So I'll do a Control F5 to build and run the program. So we get a value of y 20 as expected. And that concludes this demonstration on creating a class in C++. In this video, I'll present how to add a private member to a class in C++. I start off by including the IOStream header because we're going to be using cout in this program to display one of our results. I've created a class here on line 4, class point. So it's a point defined by coordinates x and y. So as member variables, I have int x and y. And then I have my public section declared after I've declared these member variables. So what this means is that x and y will be private members. So inside of a class, if we don't declare something as public, it's assumed private. So private is implied if we don't have a private section. If we want to be explicit about it, we can put a section called private followed by a colon. So anything that comes after private will be a private member, and it cannot be accessed from the outside. So if I tried to go down to my main function and type p.x equals p.x equals 2, it will give me an error. So as soon as I do that, you'll see IntelliSense here in Visual Studio puts a little red squiggly line under the x because the x is inaccessible from the outside because it's private. So we can't set it that way. Now, thankfully, I've created a public function called setXY. So that way we can set the values x and y through this setXY function. So setXY is in the public section, so it's publicly accessible. We can call it from the outside wherever we've declared a point and set the values x and y. So if we look at our main function, I create a point p, and then I call p.setXY, and I set the values to 1, 1. Now ideally at this point, we'd like to verify that x and y have been set. So quite often I'd like to do something cout, let's say x and y, so p.x and p.y. So I would do something like this and put a comma in between and do p.y and then a carriage return. But these are private members, so we can't do that. So let's add another function to this class point, and we'll call it print. So void print. We won't pass it any arguments. We'll create the function body right here in the declaration of point. We'll copy our code, our cout code here from the main function, into our print function. And now since I've moved it inside of our class, we don't need to specify this p dot anymore, so we just remove that because it knows the x is going to be its member x. So if we have a member function, so a function inside of point, we can access the private members. So public functions inside of our class can access private members. So any member function can access a private member of its class. So we can do the same thing here with p.y, and then we can print our results. So to call this, we go back to our main function, type p.print, and then we can see our results. So now I'll do a Control F5 here in Visual Studio to compile and run the program. And it prints 1, 1. Since we called xy with those values, 1 and 1, x and y are 1, and that was the result we expected. And that concludes this demonstration on adding private members to classes. In this video, I'll present how to add a protected member to a class in C++. So in this video, I'm including IOStream and using the standard cout to output one of our results. Now I defined two classes in this program, class X, which contains a private member int a, and two protected functions setA and getA. So since X has only private and protected members, it doesn't have a lot of functionality from the outside. So if we create an instance of class X, nothing is accessible because it's all private and protected members. Now this is a quite uncommon thing to do, but I've also declared a class Y, which inherits from class X. So class Y is a subclass or child class of class X, so we have class Y colon X. So this says that Y is a child of X. So Y has everything that X has, plus the things that it brings on its own. So y has an int b, which is private because all members are private by default, so we don't have to explicitly say private to know that b is private because that's the default in a class, so it's implied private. Then it declares a public section. So y has two public member functions, a print function which returns void, and a set function. Now you'll notice right away in the print function, trying to access a is a problem. So the variable a, which comes from class x, is private. So even though we inherit from x, since it's marked as private, we can't access it directly. Luckily, I've defined a getA function that's a member of class x, but it's protected. So since we inherit from class x, so since y inherits from class x, it can access the getA function, which returns the value of the variable a. So getA returns a. So if I save it, it no longer complains. And I put this comment at the end of the line that says error, but this error is gone away now. So our print function is fine. It will print the values of a and b, but for a, it has to call the getA function because it's a protected function and the variable itself is private. Now our set function, which takes two arguments into I and j. Now if I tried to set the value of a directly, if I said lowercase a equals I, there would also be a problem because I can't do that directly because, again, a is private. But I have access to the setA function because it's protected, so I can call setA and pass it the value I, and then up in our class x in the setA function, it sets a equal to I. So we do set the value in a roundabout way because because the member variable itself is private. So now in our main function, I create two instances, an instance of class x with the variable lowercase x, and an instance of class y with the variable lowercase y. Now, you'll see here, if I try to call x.setA directly, it gives me an error. So in Visual Studio, IntelliSense picks it up right away, and it says it's inaccessible because it has these squiggly lines, and if we look, oh, setA is a protected function, so we can't call it from the outside. It has to be called from a derived class internally. So we can't call protected members from the outside, or if there was a protected member variable, we also couldn't access it from the outside. So to get rid of this, let's just delete this x.setA, and we're not going to be using our class x, so let's remove that as well. So we're left with our class y and variable y, so we can call y.set, pass it two values, 2 and 1, and then call y.print to see the result. So I'm going to save this program as it is now, call compile using Control F5, so this will build and run the program, and we can verify our results. So our results for A and B are 2 and 1, as expected. And that concludes this demonstration on protected members in C++. In this video, I'll present how to add public members to a class in C++. So for this video, I'm including IOStream and string, so we can output our result using cout, so I'm using the standard cout, and I'm using the standard string because it's going to be one of the member variables of the class I define in this program. Now I define a class here on line 6, class sprite. So a sprite is a little character that we might have on the screen. Let's say we have a name, and this particular sprite has a name, so we have string name, and it has a position, x and y. So we have int x and y, and then it has a print function that'll print the name and its coordinates. So name followed by the @ symbol followed by x comma y in parentheses. But this program has a problem. The members of classes are private by default. So this is the same thing as if there was private : at the top of this class, at the top of its implementation, and everything were private. So in our main function, I create a new instance of class of sprite s, so a new instance of sprite with the variable s, And then if I try to do anything with s, it's going to give me a problem. So if I try to set a name, let's say I type s.name equals Bob. So sprite Bob needs a name. We try to set it to Bob, and right away, IntelliSense in Visual Studio picks it up and says, our member name is inaccessible because it's private. Well, we need this to be public. So if I go into my class and make a public section, let's make the whole thing public, then name is accessible. And the same thing with our variable x. So let's s.x equals 5, and we can do s.y equals 10. Now we can have mixed sections in our classes. So these could be public members, but if we had a private keyword in here and our print were private, then we'd have a problem. So if I tried to do s.print, call the print function, it's also a problem because I just made print inaccessible. So the same rules apply to member variables as member functions. Anything that's public I can access through an instance using the syntax s.name or s.whatever member I need to access or call. In this case, if I'm setting variables, I can do s.name or s.x or s.y. And it's not just public and private in terms of setting it. If I want to access one of these members, I can only access public members even if I want to display them. So if I tried to do a cout on s.name, that's fine as long as name is public. But if it was private, I still couldn't access it even just to see the variable. I can't see it, I can't set it, I can't do anything with it if it's private. But if it's public, I can access it, I can set it, and I can call the functions as long as they're public. So I'm going to remove the private section and let print be public, save it again, and now I'll compile and run it so we can see what it prints. Now I'll do Control F5 here in Visual Studio, and it will build and run the program, and we should see the name at x and y. So Bob is at 5, 10, as expected. And that concludes this demonstration of public members in classes in C++. In this video, I'll present how to create a class constructor in C++. So for this video, I'm including iostream and string because we're using cout and the standard string class. So I create a class called class sprite, and in its declaration, I have 3 member variables. I have a string name and 2 integers x and y. So we can think of a sprite as a character on the screen on some grid, defined by the integers x, y. So it has 2 member functions, or 2 public member functions, one called sprite. Now this one is named identically to the class sprite. So we have class sprite and member function sprite. Now the member function sprite is called a constructor. So this is what we use to construct a sprite when we're creating an instance of it. So when we create an instance of sprite, it's expecting 3 variables, or 3 parameters, string s, int a, and int b. So we have to pass these 3 values into sprite to actually create an instance of it. Now, I'm not defining what this function does inside of the class definition. I'm going to do that externally, so I just end it with a semicolon. And then I have a member function, a public member function print, that just prints the values, so we have name at x, y in parentheses. So we'll use that to verify the results at the end. Now let's look at our constructor. So we have sprite, our class, :sprite, our constructor function. So sprite takes a string s, an int a, and an int b. So it sets the name equals s, x equals a, and y equals b in the body of our constructor. So every time we create an instance of sprite, it calls this function. So we have to pass these parameters to create sprite. So in our int main, we have sprite s, so the variable s, and in parentheses, we have what we're passing to the constructor. So the string John, 1 and 2. And then we call s.print to verify the result. Now if we tried to create another sprite, so if I went down a few lines and typed sprite t, but I didn't pass any values to t, we'll get an error. So it complains that there's no default constructor. So there's no constructor that takes no parameters for sprite. So sprite can only be created if we can pass the parameters to call its constructor. So let me delete our sprite t because it's not going to work. Save the code. And we'll do Control F5 to compile and run the program to verify that our constructor did work and it prints the values correctly. So we do get in the output from our print function John at 1, 2, as expected by the way we've created our sprite s. And that concludes this demonstration on creating a class with a constructor in C++. In this video, I'll present how to create a class deconstructor in C++. I start off by including IOStream and string, which we're going to need in this program, so we're using the standard library cout and the standard string class. So I create a sprite class sprite, which I declare 3 private member variables, a string name, an int x and y, and a 4th variable, an int star p. So I have a pointer p declared in this sprite class. And then in the public section, I have a constructor, a sprite, which takes string s, int a, and int b, which will be used to set our name and x and y coordinates of our sprite. I also have a public member function print, so void print, which just prints the contents of name and the x and y variables. Now I declare a constructor outside of our class sprite sprite that takes a string int and then sets name, x, and y. So it sets these 3 member variables name, x, and y to s, a, and b respectively. But then it allocates space for our pointer p. So it says p equals new int and then sets the value at p star p equal to 0. Then in our main function, we create our sprite s with the name John, so string John, int2 and int3, and then it calls s.print. Now you may be thinking, hold on, you just allocated p with new int. Where are you deleting p? Well, if I went to my main function and I typed delete s, so our sprite s.p, so here's our variable p, and I want to delete it. Well, that's a problem, and IntelliSense picks that up right away and puts a red squiggly line under our variable p because p is private, so it's inaccessible. So we can't delete it that way, and that poses a problem. Luckily, C++ comes with something called a deconstructor. So we have our constructor that's called when we create a sprite, and a deconstructor that's called when we free the memory or when our sprite goes out of scope. So since we declare s as a sprite here, when it reaches the end of the main function, it goes out of scope, and then we can create a deconstructor to be called when that happens. So if we go to our public section, usually right under our constructor, we'll put a tilde, so a little squiggly line, sprite, so the name of our class. So we declare a function and a double parentheses followed by a semicolon. So here we've we have a definition for a sprite or a declaration for one, and then we can go under our constructor and we can implement it. So I'll type in sprite the class, tilde, sprite, and 2 parentheses, and then in braces, we'll put our function body. So we've declared our deconstructor, and the important thing to do here is to put in delete p. So our new in our constructor gets deleted in our deconstructor. So that's the general rule. Whatever is allocated in the constructor gets deallocated in the destructor. So we have new in the constructor and the corresponding delete in the destructor. So that's a very important thing to follow. Anywhere you have new, you have to have a corresponding delete. And to make sure it does get called in our program, I'm going to put a cout in our deconstructor, and I'm just going to write the word deconstructor tilde sprite. And then I'll put a \n so we get a new line character. So that way we know it is called, or when it's called, we'll see that this string is printed. So let me compile and run the program, and we should verify that our constructor for our sprite s works fine. We do a print, and then we let it call the destructor when it reaches the end of the main function. So I'll do Control F5 to compile and run. And we see that we get our print function from our sprite John at 2,3, just as we've constructed it. And we see that the destructor of sprite is called as expected. And that concludes this demonstration on creating a class deconstructor in C++. In this video, I'll present a C++ class with overloaded constructors. So I start out by including IOStream and string, because I'm going to be using the standard cout and the standard library string class. So I create my own class here on line 6, so I have class sprite, which has 3 private member variables, a string name, an int x, and y. So the name is the name of the sprite, and the xy is its position on some integer-based grid. So in my public section, I have a first constructor, so sprite, which takes string s, int a, and int b. But I also have 2 other constructors, so I just have another sprite with a different set of arguments, or a different set of parameters. So I have sprite, string s, and then I have a sprite constructor that just takes int a and int b. And then I have another public function, void print, which just does a cout of the member variables, the name, and the x and y variables, so that we can verify our results when we compile and run the program at the end of the video. Now let's look at our constructors. So the first constructor I've declared, so sprite double colon sprite, which takes our argument string int. So that sets the name and the x and y variables. Then we have our constructor with our string s, and that just sets the name. Now, if you have something like this, what I'd recommend is putting in a default value. So instead of just setting the name in this overloaded constructor that takes a string, we should put in something like a default variable for x and y. Let's say x equals 0 and y equals 0. So by default, our sprite, if we don't specify it, if we construct it with this particular constructor that takes a string, we want to set it to a default 0, 0, so at some origin. And then we have another sprite that we create, but we don't specify a name. So we just have the int a and this int b. And I set the variables x and y, but we should also set our name variable here. So we can set name equal to some string. Let's call it, in parentheses, let's put unnamed. And we'll put it in parentheses just to set it apart. So we have some anonymous or unnamed string for our name. And then in our main function, we test our 3 constructors. So sprite s1, we construct with a string, an int, and an int. Then we print the contents of s1. Then we create another sprite s2 with just the string Bob. So we specify the name, but not the coordinates. And then we do an s2.print to verify that result. And then we create sprite s3 with just the coordinates 10 and 10. So the constructor that takes 2 ints. And then we print the result so that we can see the coordinates of the unnamed sprite s3. I'll do a Control F5 to compile and run the program, and it successfully compiles. So we have John at 2.2. So let me move this console window over to the side. Bob at 0.0. So Bob was created without specifying the coordinates, so he's at the default 0.0. And then we have unnamed at 10.10. So since we didn't pass a string to this constructor, it goes as unnamed by default, but the coordinates were set to 10.10. So these results are exactly what we expected. And that concludes this demonstration on working with overloaded constructors in C++. In this video, I'll present how to create a class with a default constructor in C++. I start out by including IOStream and string in my program because we're going to be using the standard library cout and string class. So I create my own class called class sprite, which has three member variables: a string, which is the name of the sprite, and the coordinates, the int xy. So we have a string name and variables xy, which are private members of our class sprite. Now we have our public section where we specify a constructor that takes a string, an int, and an int, so that we can set our member variables. Then it also has a public function print, which returns void. That just does a cout of the name, the x and y coordinates, so we can see the contents of our sprite. And now we go down just below our class declaration, we declare our constructor. So sprite, sprite, with its arguments string, int, int. And then we set inside the body of this constructor, we set the name and the x and y coordinates. And then in our main function, we create a sprite s with the string, the name, Eamon, and the coordinates 1, 2. So we do s.print to see the contents of the variable s, the sprite s, to see that everything got constructed correctly. But suppose I wanted to create another sprite, t, but I didn't want to specify the contents, the name and the x and y coordinates. I just wanted to create an empty sprite so that we can set and use it somewhere else in our program. Well, for this, we need a default constructor. So just by specifying sprite t, what C++ will do is look for a constructor with no arguments. So to be able to do this, to be able to create a sprite this way without specifying our constructor, we need to create a default constructor. So in our class, I go to the public function or the public section of our sprite, and I'm going to type sprite with an open and close parentheses and a semicolon. So this declares or defines our default constructor, and then I need to implement it. So below our sprite class, I'm going to type sprite, sprite, and then an open and close parentheses, and open and close braces. And in the function body, I'm going to set name equal to an empty string, x equal to 0, and y equal to 0. So this will give some default values to our name, our x and y, so that we can start using our sprite, but without, so this is an unnamed or an anonymous sprite that we have that gets generated at the origin, and it doesn't have any information other than it's a sprite. So you'll notice that there was a red squiggly line, an IntelliSense error on our variable t because it didn't have a constructor specified. But now that there's a default one, we can create one just by typing sprite t followed by a semicolon, and it creates it using the default constructor. Now we can verify the default constructor is called by just calling t.print. As well, I'm going to go into our default constructor, and I'm going to do a cout and say default constructor. So I'm going to put that in just so we know that, just so that we can see that the function is indeed called. And then I'm going to do a control F5, which will build and run our program. So you'll see here, if I move this command window out of the way, we see Eamon at 1, 2, so that was our sprite s. And then we see default constructor, so that's when our line sprite t. It calls the default constructor. And then we have a space, so there's an empty variable, so nothing gets printed for the name at 0, 0. And that's exactly the contents of our default constructor. So that's what it sets name and x and y to. And that's pretty much what we expected. And that concludes this demonstration on working with default constructors in C++. In this video, I'll present how to create a pointer to a class in C++. So I start out by including iostream and string, because we're going to be using the standard cout and string class. So the class I'm working with in this program is class sprite, which has a string name and an int xy as private member variables. Then in the public section of our class sprite, we have two constructors. We have a default constructor with no arguments and a sprite constructor that takes a string, an int, and an int, which will set our member variables. And then we have a print function that returns void that will print the contents of our member variables, our name, and the x and y coordinates. And then we declare our sprite constructors, the default constructor, so sprite, sprite, and the open and close parentheses. And then we have a function body enclosed in braces, and then it does a cout of sprite, default constructor. So we want to know when our default constructor is called. Now this will be important in our main function, so that's why I've done a cout to say that it was called. But this function, this default constructor, just sets the name to an empty string and sets the coordinates to 0 and 0 for x and y by default. And then we have our constructor that takes our 3 parameters, so sprite, sprite, and then we have string s, int a, and int b, which we use to set the name and the x and y variables. Now in our main function, we create a sprite star s, so we have a pointer to a sprite. So s is a pointer, but we set it initially to new sprite. So we use our new function to allocate space for a new sprite, and we call the constructor with a name, in this case the name Eamon, and the a and b variables, which will set the x and y coordinates, 1 and 2. Then we call the print function, but we don't call it in the usual fashion. When we're dealing with a pointer, we use s and then hyphen greater than symbol, so we get this little arrow looking symbol, so it's like s arrow print, so it points to s's print function. So we call s, instead of using s.print, we use s arrow print. So remember, when you have a pointer to an object, you have to use this arrow syntax to call a member function. And then we call delete s because we've allocated it with new. So anywhere we create a new object, a new class, we have to delete it when we're done with it. And then I create another pointer, sprite star t. So in this case, it's an uninitialized pointer, and it's very different than just calling sprite t without the star. In that case, it actually creates a new sprite and the default constructor gets called. So if I just have sprite star t, it's a pointer of type sprite, but it's not initialized to anything. It doesn't point to anything, and it doesn't create any objects. So if you were previously thinking that this sprite star t might call the default constructor, that's not what happens. It won't do anything unless we actually allocate it using new, or we point it to a different sprite object. So let's compile and run it now. I want to show you that definitively that the default constructor won't be called in this program, but we'll only see it after we compile and run. So I'll do a Control F5. That will compile and run the program, and we can verify the results. So we see we just get Eamon at 1, 2 for our sprite pointer s that we've created previously, but the sprite star t doesn't do anything. If we wanted it to do something, we'd have to set it to new. So I can go on the next line and do t equals new sprite and just put a semicolon in. And since I haven't specified any parameters on the sprite, any arguments to the constructor, it's going to call the default constructor. Now, there's another problem that could have occurred if I had a sprite pointer t, if I tried to call t arrow print. Now, without doing a new sprite, or if t is an uninitialized pointer and I try to call a member function, it's going to end very badly and it will most likely crash the program. Now, if we'd like to test this, we can do a Control F5, calling a print function on an uninitialized pointer, and it gives me a build error. So we don't want to do anything. So we say uninitialized local variable t used. So it actually, the compiler complains saying we're trying to call this function on an uninitialized pointer. So let me initialize it by saying t equals new sprite. And then since we have a new, we need a delete. So we have to do delete t. And I'll save it, and we'll run it to make sure that our default constructor is called. And we see that we do get our previous result from our sprite s printed first, and then we have sprite default constructor as expected, and then we have nothing at 0, 0. So since the string is an empty string by the default constructor and the coordinates are 0, 0, that's exactly what we expected to get. And that concludes this demonstration on creating pointers to classes in C++. In this video, I'll present how to create a struct in C++. So for this video, I'm including IOStream because I'm going to be using the standard cout. Now, I create a struct called circle, and the circle has a double radius and a double in x and y. So it has a position and a radius to define the size of the circle. And then it has a print function which returns void, which just does a cout of the contents of our circle. So the x, y, and radius get printed, so they're x, y, radius. So we print the contents so we can verify our result. Now, the main difference here is between a struct in C++ and a struct in C is that a struct in C++ is just a class. Now, for a class in C++, the member variables and the member functions are private by default. If you declare something as a struct in C++, well, it's the same as a class, so internally a class gets created, but the members are public by default instead of private. So creating this struct circle is identical, or effectively identical, to creating a class, and then in that class specifying public. So I do public colon, and that's the same as a struct in C++. So I can remove the public and create this as a struct. And then in our main function, I create an instance of circle C. So the variable C is a struct circle, and then I can call c.x and set it to a value, let's say 1.0, c.y is 1.0, and c.radius is 5.0. Now, another difference between a C++ struct and a C struct is that we can have member functions. So the struct circle has a function called print, which we couldn't do in this way in just C. So in C++, we can have member functions in our struct, and we have c.print in our main function to print the contents of our circle. So let's compile and run the program to verify that we do indeed get a circle with the x, y, and this particular radius. So I'll do a Control F5 to compile and run the program, and we can verify that it does work as expected. So we get an x, y, and radius, so the x and y are 1 and 1 as we set them, and the radius is 5 as expected. And that concludes this demonstration on creating classes defined with struct in C++. A C++ union is an object whose members are allocated in the same space. So the amount of space a union takes up is only as big as its largest member variable. So they're usually used for compacting data. In this video, I'll present how to create a union type object in C++. So for this video, I'm including IOStream, and from it, I'm going to use the standard cout, and I'm also going to use the standard hex. So this is for outputting hexadecimal output using cout. Now I create a simple union in this program called int bytes. So it declares an unsigned int I and an unsigned char b of subscript 4. So it's an array of characters of 4 characters. So since an int I in this program on this system will be 32 bits or 4 bytes, and an unsigned char b, an array of 4, will be also 4 bytes. So this union is 4 bytes in size, and we can access it either through its unsigned int I or its unsigned character array b. So in our main function, I create an instance of the union int bytes using ib. So it's basically a class in C++, or it functions much like a class or a struct would. And then I can set its member variable I, so ib.I equals 65,000. But since the array B and I take up the same space, what I write into I also affects B and vice versa. So after I set I to 65,000, I do a cout of ib.I. So we can see that it indeed is set to 65,000. But I also want to output its hex value so we can compare it to its character representation. So we do a cout hex of ib.I, so our I member variable. And then if we look at the bytes, the unsigned characters B, that array we've declared in our union, we can see how that array was affected. So if we do a cout on ib.b3, so of index 3, but we want to cast it to an integer because we are looking at the value of the bytes and not the actual characters. So if we didn't have this int here, it would output the character and not the actual byte value, the numeric value that we want to see. And since we did this hex inside the cout, so we cout, we pass hex, which is the standard hex, so we can get the hexadecimal output. Now this will carry over into the next cout. So not only are these unsigned characters being represented as integers, they're going to be displayed in their hexadecimal format. So we have B of 3, B of 2, B of 1, and B of 0. And I do it in order like this so we can compare it to our unsigned int I. Now I'll compile and run the program, and we can see what our I contains in our union and our array of characters B. So I'll do a Control F5 to compile and run the code. So you'll see here our unsigned int was 65,000. That's what we set it to. 65,000 in hexadecimal is FDE8. And if we look at the individual bytes, our array of 4 bytes, the contents are 00 FDE8. So it's basically FDE8. So it's the exact same as the contents of our integer. So whatever we set the integer to, we get our array of bytes or array of unsigned characters B set to, and vice versa. So if I go back into the code and let's say I set ib.b subscript 0, if I set that equal to something, let's say I set that equal to 10, and then I do another cout of ib.I, followed by a carriage return, it will actually modify the contents of the integer as well. So let's compile and run it again with this change. So we see that we get 65,000 FDE8, which sets the 4 bytes in our character array to 00 FDE8, but then we change the byte 0 byte, so this E8 gets set to 10, but 10 is A in hexadecimal. So our int I is FD0A. So the 0A part, so 0A is 1 byte and the FD is another byte. So 0A is the hexadecimal equivalent to 10. Exactly what we set I.B of 0 to. So that's a pretty neat result, and hopefully this gives you a greater understanding of what's happening inside of a union. And that concludes this demonstration on creating unions in C++. In this video, I'll present how to create a class with overloaded operators in C++. So for this video, I'm using iostream and string from the standard library, and we're going to be using cout and the string class. So I create a class called myString, and it's going to have a member variable string called text, and then it's going to have a few public member functions. So it has a constructor, which takes a string, so it can set its internal string by using a C++ standard library string, but it's also going to define a couple of operators. So our first operator, which we define as void operator, so the operator won't return anything, but it will accept a parameter. So we specify the operator keyword, so we say operator, then the symbol or the combination of symbols. So the double less than symbol is treated as a single operator in C++. So we have double less than, so you can think of it as kind of an arrow or a double arrow pointing to the left. And if we're dealing with a string, we can think of it as a double arrow pointing to the beginning of the string. So in this case, our double arrow operator to the left takes on a string. So it takes a string as an argument, and it prepends or puts this string argument to the beginning of our text. So our text becomes this new string that's prepended plus the rest of our text as it already is. So whatever it is currently, it prepends whatever we pass to this operator. So this double less than operator. We'll do the same thing with the double greater than operator. So we have this void operator with a double greater than symbol, which you can think of as an arrow pointing to the right or to the end of the string. So this will append the given string to our text. So text equals text plus some string C. So it appends it to the end. So we have a prepend and an append or an append to the end. And then we have a print function just to print the contents of our string class, which just prints our text followed by a carriage return. Now let's look at our main function where we create our string, our myString s. So our class myString s is created with the constructor, the string hello, world, ! Then we print the contents of this string s, so we verify that we do have hello world to begin with. Then we prepend using our operator, so we take our class s, the operator, the double less than symbol, or the arrow that points to the right. So we want to prepend the string, the text, one period space. So we kind of put an enumeration on our hello world. So it's going to be the first hello world, so one dot. And then we print it. So we do call s.print again to verify the change, that our operator did work as expected. And then we use our next operator, the double greater than symbol, or the arrow pointing to the right. And what we would like to append to our class is the string with a space, by, comma, world, ! And then we do another print on s to verify this change. So we want to verify that by world was indeed appended to the end of our text. So we call s.print again. Now I'll compile and run the program using Control F5 here in Visual Studio. And we can verify the result. So we see in the result, we get our first print after we've constructed hello world. I'll move the window to the side so we can look at our main function and the results at the same time. So it starts out as hello world, and then we prepend using our overloaded operator, so it becomes one dot space hello world ! And then we append by world using the operator that points to the right. And then we get one dot space hello world ! Then our space, and then by world. And that's exactly what we expected, so our overloaded operators worked correctly. And that concludes this demonstration on overloading operators in C++. In this exercise, you'll create a C++ application that includes classes. Now in these classes, you'll use private and protected access modifiers, and you'll create a class containing both a class constructor and a deconstructor. And then you'll use a pointer to a class in your C++ application, ideally in your main function somewhere. Now you can pause the video and perform the exercise, and when you've completed it, when you've carried out these 4 elements in your C++ program, then you can resume the video and see what I did. Now here we are in my C++ program. No doubt you've got something a little bit different, but you should have some of the same elements that I have. So I start out by including IOStream because I'd like to use cout to output some of the contents of my program to see what's going on. Now the first class I create is called class A. It has some protected members in this protected section, so I have protected in colon, and then it has an int a, and then a getA and a setA function. So getA just returns the value a, and setA sets the value a to whatever is passed as an argument here. It has a private member, an int pointer p, so it's a pointer to an int. And then it has a public section which has a constructor, so this a parentheses that sets the lowercase a member variable to 0. and it allocates a new int for our pointer p. And then in the deconstructor, the tilde a, it defines a function that does a cout of our deconstructor a, and it says we're done with a, and then it deletes p. So it's very important that if you allocate memory in your constructor, that you free it or delete it in your deconstructor. And then we have a class B, which is derived from A. So class B colon A, that has a private member int b, lowercase b. It has a couple of public functions, print function that returns void, that outputs the contents of b. It outputs A and B. So since A, that's inherited, so the variable a, the lowercase a, is inherited from the parent class a, I can get access to it and output it here. And the b is a private member to our class b, so we can output that as well. And then I have a set function, which calls set a from our parent class a, so it sets the value, and then it calls b equals j. Now I don't necessarily have to call the set a function. I could just set a by saying a equals I right here, because b has access to the variable a, but I can do either or. And sometimes it's preferable, especially if there's some other checks or some other functionality going on inside your set function, to call the set function directly. So now in our main function, I create a pointer to a class. So b, the pointer b to our class b, so lowercase b, is equal to new b, so the uppercase b of our class b. So then we call our set function using the arrow syntax, so b arrow or hyphen greater than symbol set, and then I pass 5 and 8, and then I print the contents of b, calling the print function, and then I delete b. So if you have a pointer to a class that you allocate with new, make sure you delete it as well. So anytime you have a new in your program, you should see a delete, just like we had in the constructor and destructor for a itself. And that concludes this exercise on working with C++ classes. In this video, I'll present how to overload operators in C++ custom classes. So we'll start out by including the IOStream header, which we're going to need the standard cout from so we can display some of our results. Now I've created a custom class called circle, so I have class circle, which has a few private member variables, so a double radius and a double x and y. So we can think of it as defining a circle by its coordinates in x and y and its size in terms of its radius. Now in our public section we have a constructor which takes 3 doubles, so this will be set to our x and y and our radius. So we initialize our circle with an x and y coordinate and a radius. Now in this video we're talking about overloading operators. So to overload an operator, well, we're going to overload the plus operator. So the way this is going to work is we're going to add the radius of another circle to our current circle. So given a plus symbol dealing with our circle class, we want to return a circle, a new circle, and as a parameter, we want to take a const reference to another circle. Now, a const reference because we don't want to modify this parameter, so it has to be const, and it has to be a reference because we don't want to copy the other circle. So when we're adding it, if we copy it, then we're doing a little bit of extra work that doesn't need to be done. So we're just going to pass a const reference to this plus operator. So we have circle, our class, our return value, operator, the literal word operator, and then the symbol, in this case the plus symbol. And then as an argument to this operator function for the plus operator, we have const circle ampersand b. So a const reference which we call b. And then we just return a new circle, so return circle, and to this constructor we pass x, y, so that's our x and y. So the current circle's x and y radius. So we're not doing anything with the coordinates, we're just taking the destination circle, the current circle's x and y coordinates, but we take the radius and then we add the radius of the other circle, this b circle, so b dot radius. So we're just adding this radius to the current circle. And then we also overload the minus operator. So in this other operator overload, we have circle as our return, then we have operator minus, and then const circle reference b. So again, we pass the same parameter, but this is the case where we subtract another circle. So we create a temporary circle t with the x and y coordinates of the current circle, and then we subtract the radius of b from the current one, so radius minus b dot radius. And then if the current radius is temporary radius t, so t dot radius, if it's less than 0.0, if it's less than 0, then we set it to 0. So we don't want any negative radius to show up. And then we just return t, this temporary circle we've created, to be the return value of this minus operator. And then we have a print function, another public function void print, that just prints the member variables x, y, and radius. Now in our main function, what we're going to do, well, we're going to demonstrate how this works and verify that we can indeed add and subtract one circle from another. So we have our circle B, which I've initialized, circle C, and circle D. And then I print the contents of B, C, and D. Then I perform a C equals C plus D. So I'm adding the circle D to C, and then I'm overwriting the value of C. Then I print the new value of C and the new value, or which will be the current value of D. So what I'm doing, I'm printing D again just to show you that D actually doesn't change. And then I do a B equals B minus C, and then print the new value of B. So let's compile and run the program and verify that the operator overloading works as expected. So I'll do Control F5, which will build and run our program. And let's look at our results. So our contents of B, C, and D are the x, y, and radius. So with B we have 0, 0, 1, with C 1, 1, 5, and D 2, 2.5, and 12. So when we do C equals C plus D, we should get the x and y coordinates of C, so 1 and 1, and then the radius should be 5 plus 12. So if we look at the new value of C, we get 1, 1, and 17 as expected. And if you notice D, it hasn't changed, so it's still 2, 2.5, and 12 in both cases. And now we perform a minus, so we take our circle B and set it equal to B minus C. So this should change B and subtract the radius of C. But if we look at the original values of B and C, you'll notice that the radius of C is actually bigger than B. So 1 minus 5 is negative 4, but in our overload for the minus symbol, if it's less than 0, we set it to 0. So that's what we get. So B, the coordinates are 0, 0, and the radius is now 0, so we have an empty circle because the radius of C is bigger than B. And that concludes this demonstration on operator overloading with C++ custom classes. In this video, I'll present how to pass objects as function arguments in C++. So we'll start out at the top of our CPP file by including IOStream and string, for which we're using the standard cout and the standard string in this program. So we'll start off next by creating a class sprite, which is going to consist of 3 member variables, a string name, and an int xy. So we can think of it as a sprite or character on the screen that has coordinates in some grid identified by x and y, and it has some name. So our public section has 2 constructors, a default constructor, which sets the name to the empty string and our x and y to 0, and another constructor for sprite which takes a string and 2 ints, and then initializes our name and our x and y coordinates. And then finally it has a print function that prints out the contents of the class, the member variables, the name, and the x and y coordinates. So that defines the sprite we're going to be using to pass to our function. Now to see how we pass objects as function arguments, I've created this function sprite output. So this takes 3 arguments. One, sprite A, so this will be a pass by value, a sprite pointer B, so sprite star B, which passes an object B as a pointer to the function, and then sprite ampersand C, or sprite reference C. So it's going to pass C as a reference to a sprite. So this will get passed, called by our main function, and we'll pass 3 sprites to this function in 3 different ways. So in the main function, I create three sprites. Sprite A, which is set to the string Steve for the name and the coordinates 0, 0. The sprite B, which is set to Bob 1, 1, and C, which is set to this name Alice 2, 2. So I output not the contents of our three sprites, but their memory locations. So for this, I see out A, B, and C, and I output ampersand A for the reference of A or its memory location. So we look at the memory address of A, B, and C because we want to compare it to what our sprite output function contains. So as you may already guess, since we're passing A as a value or A by value, so we call sprite output, we pass A. A will get copied into the function, so a new instance of a different sprite will be created inside the function. So in the sprite output function, when we look at the address of A inside the function, it should be different. We pass B by pointer, so we need a reference to B. So I do ampersand B, which gives the sprite pointer B in the sprite output function a pointer to that variable B. So when we output the pointer B, it should be the same address as the B from our main function. And finally, we pass C by reference. And then in the function, we output the memory address of C, which should be the same because it was passed as a reference from our main function. And then we print the contents of our variables inside this sprite output function. So let me run it as is so we can look at the results and make sure it compares or to what we expect based on this code. So I'll move this output window to the side so we can have the code as well as the output at the same time on the screen. So if we look at our addresses, so the first 4 or 5 numbers in the address, the 0, 1, 2, FF, are the same for all of our variables. But if we look at the last 3 digits, so the E54 for A, and then we look at it what it is in our output from inside the function, we have CBC. So E54 gets changed to CBC. So there's a new sprite. So the object is actually copied when it's passed to the function, and it's not the same sprite. So if A was modified in our sprite output function, it would not affect the sprite A from our main function. And then we output the contents of our sprite. So Steve adds 0, 0. If we look at B, we see that the last 3 digits are E28, and in the function, the pointer B is still E28. So it's the same object. And if we modified B inside of the function, then B in the main function would also be modified. And the same goes for C. It's passed by reference, so that reference refers to the same variable or the same sprite C, and the addresses are the same, so DFC and DFC, and we output Alice at 2, 2. So if our variable C was changed inside the function, then so would our variable C from our main function. Now it all works as expected, but I can make some changes. Another thing you should be aware of when passing objects as function arguments is that you can specify them to be const. So if I put const sprite A, const sprite pointer B, and const sprite reference C, it will tell the calling function or tell the program that these objects will not be modified by the sprite output function. But the minute I do this, I have problems with calling print. So a.print, b arrow print, and c.print all cause problems. So IntelliSense in Visual Studio picks it up, puts a little squiggly line under these variables and says, hey, you're calling print. Well, print is a member function inside of sprite. And that member function can definitely change or has the ability to change our member variables. And because it does have that ability, it complains because it might not obey the const property of these variables, of these parameters. To allow this to extend our const correctness to our print function to say, hey, print's not going to modify these, so you don't have to worry about it, we go up to our print function in the sprite class, and so we have void print, and then after our function name and the argument, so after these parentheses, we put in const. So this says that this function is a const function and it's not going to modify the contents of our sprite. So once we put this const in and save it, then all of our problems go away and we can run the program again and it will work fine. And this works because sprite output doesn't modify any of these arguments, so we can declare them as const. And this function print also does not modify the contents of our sprite, so we can also declare it as const. So this is another property you should be aware of when passing objects as function arguments. And that concludes this demonstration on objects as function arguments in C++. In this video, I'll present how to create C++ virtual functions. So I've created a small program here without a virtual function. So I'll demonstrate the need for virtual functions first, and then describe how they're used. So I start out by including the IOStream header so we can output some of our results using the standard cout. Now I first start by creating a class called A, so this uppercase A. It has a single public function, so I have a public section here, public colon, and then a function called letter, which returns a character, so a single char. So it does a return with the character A, uppercase A. And then I declare a second class B, which derives from A, so we have class B colon public A. So by saying public A, this means all of the public functions in A are accessible through B. Then B, as a public function, also declares a function called letter. So the char letter in B returns the character B. So there's two letter functions, one implemented in B and one implemented in A, and they're called the same thing, and they return the same type. Now if I go to our main function, what I do is create an instance of B with a lowercase b, so uppercase B, our class, with the lowercase b, our variable. And then I create a pointer to A, so our class A with a pointer lowercase a is equal to a reference B. So A will point to B. And then I create a second variable, this alias through A, so this A2 reference, which is equal to B. But this is of type A. So the pointer A and the reference A2 actually point in some sense to B. But if we call the letter function on any of these A types, it's going to return the letter from A and not what it points to. So we test this by outputting A arrow letter, B dot letter, and A2 dot letter to see what we get in our results. So if I do a Control F5 and run the program, we can verify what this is going to do. So if we look at the letter from A arrow letter, it returns A, even though it's a pointer to B. And then a B dot letter, of course, returns the character B, and A2 dot letter, a reference to B, also returns A. So this might not be exactly what we want. Now, what we'd probably prefer is if our class A implemented letter as a virtual function. So if we do virtual char letter, it will say that this there's an implementation here in A, and if we have a class of type A, then we should output the letter A. So we return the character A. But it's a virtual function, so if any derived class of A implements its own letter function, then we should use that one instead. So what this does is say, use the one of the most derived base class. So in this case, class B implements letter. So even if we have a pointer of type A, if it's pointing to an instance of B or a reference to B, it will output the letter function. It will call B's implementation of letter and not A's, because A's is declared as virtual. So let's do another Control F5. This will rebuild our current program with our letter function in A declared as virtual. and we should get a different result. And in this case, all of our letter functions return B. That's because A is a pointer to a B class or a class created using B, and A2 is a reference to B, so it also outputs B. So the virtual function changes these. Now, if we declared a class C and our function in B was virtual, so we could do that just the same. So these virtuals carry down the hierarchy of derived classes, and it will output the one at the bottom of this derived class hierarchy. So it doesn't matter if we have another class B and C and D, and if we derive it a bunch of times, if they're all virtual, it will always call the last one. And that concludes this demonstration on virtual functions in C++. In this video, I'll present how to create an abstract class or interface class in C++. So I'll start out by including the IOStream header so we can output some of our results using the standard cout. Now, I create a abstract class or interface class called L. So this class L has a public virtual function. In this case, it's called a pure virtual function because our virtual char letter function is equal to 0. So L has no implementation of this letter function on its own. And it's virtual, so that means any derived class can implement this class letter. And moreover, because it's equal to 0, any derived class must implement this letter function, otherwise it's not valid. Now, because L has only a pure virtual function, or because it has a pure virtual function, it is abstract. That means there's no concrete way of creating an instance of L. So if we go down to our main function, right here on line 30, I have L, uppercase L, and lowercase l as the variable. We have an error here by IntelliSense telling us that, hey, you're trying to create an instance of an abstract class. You can't do this because there's no implementation of our function letter. So I'm going to comment this out to get rid of that error. But there's also an error on this variable B. Now the problem with B, now before I describe our class A here, I'm going to describe B. So class B : public L. So class B derives from L, so it implements the interface L. But the problem is that L declares a virtual char letter function that's a pure virtual function. So for B to be a valid implementation, it must implement our char letter function. So let's do that now. I'll do char letter, and I'll just return the character B. And that fixes the problem. So if I go back to the main function, you'll see that there's no longer a red underline under the variable B, and we fixed that problem. Now if I go down in my main function, I do a cout from a.letter and b.letter to verify A and B. Then I create a pointer. Well, it's perfectly fine to create a pointer of L because it doesn't actually create an instance of a class. So I have L star LP. So LP is a pointer of type L. So that LP can point to our class A because there's an actual instance of A, and it can call the letter function, which we'll call A's letter function. LP can also point to B, so we can change LP from pointing to A to pointing to B anytime we'd like, and we can call LP letter. But even though A and B both implement a function called number, so if I scroll up and you'll look at our implementations of class A and class B, they both implement this number function, so number returns int, in A it returns 1 and B it returns 2. And even though it derives both from L, if I try to call the number function from L, I get an error because the class L must implement its own function number or its own virtual function number, or in this case, if we created another pure virtual function called number, it would be fine. And I think I'm going to make that change. I'm going to do virtual int number equal to 0. So when I add this other virtual function, this pure virtual function in class L, and I scroll down to where I called number, it works. So I can remove this comment that said error, and everything's fine. So now let's compile and run the program and verify that it does work as expected. So here in my output, I'll move the output window to the side so we can look at the code at the same time we look at our output. So our a.letter, as expected, returns the character A, this uppercase character A. B.letter returns B. When I set our L pointer, our LP, to call our letter function when it's pointing to A, it returns A. Then I change the pointer to point to B, and it returns B. And then since it's still pointing to B, when I call LP number, it returns 2, the value that B returns. So that all worked as expected. And that concludes this demonstration on abstract and interface classes. In this video, I'll present how to use the this keyword in a C++ class. So in this video, I include the IOStream header from the standard library, so we can use cout to output some of our results. Now, I create a class called X, this uppercase X, and it has 2 public members, a public member variable called I, and a public member function called start, which takes an int as a parameter. So what this start function does is set the I member variable to be j, the parameter that we've passed to the function, and then it loops over this variable I, so for int I equals 0, while I is less than 10, I++. And then in this, I do a cout of I times the local I, so the class is I. So I is our loop variable, and I is also a member variable of our class X. So if I'd like to multiply the two, there's a bit of ambiguity here, or potential ambiguity, because how do I know, or how do I reference the class member I versus the loop variable I? Well, we use the this keyword. So this is a pointer to the current class X. So this is an X pointer const to this class X. So this arrow I says that we're multiplying by this member variable I. So I times this arrow I. And then we put a space in between each one. So it's going to multiply whatever value we pass to this function, which sets our I member. And then we multiply that by the loop value. And then we put a carriage return at the end of start just to put some spacing in it. Then in our main function, we create an instance of our class X called X, a lowercase x, and then we call x.start with the value 5. So that will multiply 5 by each of the values from 0 to 9 in this case. So I'll do a control F5 to verify that our function does work, and it does reference the this I, which in this demonstration should be set to 5. So we should count by 5 from 0 to 9 times 5. So 0, 5, 10, 15, 20, 25, 30, 35, 40, and 45, which is 9 times 5. So that covers each iteration of the loop, and it works as expected. And that concludes this demonstration on using the this keyword from a class in C++. In C++, static members of classes are not expressed in the instances of the class, but from within the class itself. In this video, I'll present how to create a C++ class with a static member. So I start out the program by including IOStream and string, which we're going to use the cout to display our results, and the string class for our demonstration. Now I create a class called X. So X has a private member variable, this string name, and in the public section, it has a static int count. So this is our static variable for the class X. So what happens when we create the class using the constructor? So we have X, and the constructor takes a string name. And then it sets the name member to the name parameter we passed to the constructor. So we have X, and in parentheses string name, colon, name, and in parentheses name. So this is a shorthand initializer for our class. And then in the body of the constructor, we increment count by 1. So we do count++. And then we have a destructor so this tilde x, and in the body of the destructor, we do count minus minus. So when an instance of class X is created, it increments the count, and when it's destructed, it decrements the count. So count will contain a count of every instance of X that our program contains. Now, one thing we need to do with our count is to initialize it. So on line 19, I have int X, so the class X, double colon count equals 0. So here we're referencing count from our class X. So the count variable only exists as a member of X, but it's not a member of any one instance of X. It's like a global value of X that's accessible to everyone. And then in our main function, we have our class X, and we create three variables, lowercase x, lowercase y, and lowercase z. So each one of these is set to the string hello, hi, and bonjour. And then we have a cout of one count of X. So at this point, we see what the count value contains. So since we've created three instances of X, of our class X, so this X, Y, and Z, then count should be 3. Then we have another X to this X star T, so we have a pointer T, which is equal to new X, and we pass LO. And then we output the count again after the new, so after we create a new instance of X, we output the count, which at this point should be 4. Then we do a delete on T, so the T's destructor will be called, so that should decrement count by 1. And then here, the count after delete, well, we're subtracting 1 from it, so it should be back to 3. So we should get 3, 4, and 3 in our output. Now let's compile and run the program to verify that's exactly what we get. And if we look, our count starts out at 3, after the new it becomes 4, and then after the delete it's 3 again as expected. And that concludes this demonstration on static members of classes in C++. Marking a C++ function with the friend keyword gives that function permission to access a class's private member variables and private methods. In this video, I'll present how to declare a friend function in C++. So we'll start by including iostream and string from the standard library so we can use cout and the string class in our example. So I start out by creating a class, this custom class X, that has a single private member, a string name. And then for the public methods, we have our constructor, which takes a string name and initializes the private member variable to whatever we pass in as this parameter. Now we declare our friend function. So we have friend void output name, and that takes a reference to an object of X. So X ampersand lowercase x. So since we're declaring this function as a friend, it's saying, okay, wherever this output name function is declared, he's a friend, so he can access our private member variables and our private methods. So down below this class, I declare a function void output name. So it's specified in the same way it's defined here in the class. So we just have void output name, a reference to our class X. And inside this function, we can access or change our private member variables. In this case, we reference x.name. Now, you'll notice that this output name function is not part of the class. So we don't have to specify x:::. So it's not within the scope of the class. So this friend function just declares a separate function, something separate from the class, that's a friend. So this friend can access the private members. And that's exactly what we do in this cout inside output name. So we do cout x.name, and then we follow it up with a carriage return. So we put this into practice in our main function. I create a new instance of x, the variable a, and I pass it the string, the name Alice. And then I create one called b, and I pass the string Bob. And then we call output name on a, and output name on B, which should output Alice and then Bob. So let's compile and run the program and verify that our friend function does indeed access the private member of X. And in our output, we see we get Alice and Bob as expected. And that concludes this demonstration on declaring friend functions in C++. A class marked as a friend class makes it so that it can access the given class's private member variables and private methods. In this video, I'll present how to declare a friend class in C++. So we start by including iostream and string at the top of our CPP file so that we can use cout and string from the standard library. Now we get into our custom code. So I've created a class sprite that has 3 private member variables, a string name, and 2 ints x and y. And then it declares its friend class. So we specify friend space class space the class name. So sprite has a friend class called forest. So forest will contain some sprites, and it has access to sprites' private members because it's declared as a friend. Now the public section of sprite implements 2 constructors, a default constructor that initializes name to the empty string and x and y to 0, and an overloaded constructor that takes string s and 2 ints that sets the name x and y accordingly. And then it has a print function, a public print function that outputs the name and the coordinates of this particular sprite. Now let's look at our friend class. Now one thing to note is that nowhere in our class forest do we describe that or say that it's a friend of sprites. So it's an asymmetric relationship. We have to rely on the class sprite to declare forest a friend. And the inverse of this, or the converse of this, is not true. So forest can access sprite's private members, but sprite cannot access forests. So it's a one-way relationship. So if we wanted sprite to be able to access forest, then we have to declare a friend class sprite inside of forest. Now what forest implements is an array of sprites. So it has this private member variable sprite a, which is an array of 10 sprites. So in the constructor, if we look in the public section of forest, it creates a character C of the single character A, which I'm going to use as a way of populating the names of the sprites by just giving them a letter as a name. So I have this loop for int I equals 0, while I is less than 10, I increment I by 1, so I++. And then in the body of this for loop, I access A of index I, so the 0th element on the first iteration of the loop, dot name. Now, the reason I can do this, accessing the dot name property of the A class of this sprite, is because forest is a friend. If it was not marked as a friend, so if I go back up and I comment out friend class, immediately Visual Studio picks up the problem and shows that these are inaccessible because they're private methods. So the friend class is essential. So then I initialize the name to the single character C plus I, so that will be A, B, C, D, the first 9, 10 letters of the alphabet just by incrementing it. And this constructor for a string, or initializer for a string, takes a single character, which is specified here. And then I just set the coordinates to whatever the value of I is. So the X and Y will start out at 0, 0 and go 1, 1, 2, 2, and so on. So we have this basic initializer for forest that sets these values to some default value. Now our forest also implements a print function. So it will loop over all of the elements of our array of sprites and output the name of each one delimited by a space, and then gives a carriage return at the end. So what the main function is going to do is create a forest and run forest's print function. So this first line, this forest f, will call the default constructor, initialize our array of sprites, and then call print to print out all of the names. So now I'll do a Control F5, the shortcut key for compiling and running our program. And we see we get the first 10 sprites, we get their names printed as expected. And that concludes this demonstration on declaring friend classes in C++. Encapsulation is the grouping of data and methods into an object and how a program interacts with that object. In C++, this is done through the class object, with its member variables and member functions, and its public, private, and protected access modifiers. In this video, I'll present how to create a class in C++ that takes into account encapsulation. So I start out in this program by defining useMathDefine. So it's _use_math_defines, and all of the letters are in uppercase. So this signals to the CMath header, which I've included here, that we want to use some of the predefined math constants, like the m_pi we'll use to calculate the circumference and area in our custom class circle. And then I include IOStream, where we're using the standard cout to display some of our results. Now in this class circle, I start off by defining a private section. So the private section has some member variables that define the circle, namely the radius and the x and y coordinates, and it also has two doubles, circumference and area. So this will define the position, and the size of our circle. Now, from your math education, from geometry, we may know that the radius defines the circumference and the area. But we may not want to recalculate our circumference and area every time we want to get that value from the circle. So we may want to keep them pre-computed by updating them whenever the radius gets updated. So in a case where the class is not updated frequently, so if the radius is pretty static, if it's only set when it's created or only changed infrequently, but we need to access the values of the circumference and area quite frequently in relation to that, then we should probably pre-compute them and just access them when we need them without having to compute them every time. So that might speed up our program if that's how things are working. Now, so we have this update function, which I've declared as private. So the reason this is private is because I only want it called when radius gets updated. And another important thing is that the circumference and the area are indeed private members, because if they were public members, it means they could be changed from the outside and they could become out of sync with the radius, or they could become invalid and not even correspond to the radius if somebody sets them to an invalid value. So this update function computes the circumference 2 times pi.radius, and the area is pi r squared, so mpi times radius. So let's look at our public section. We have a constructor for our circle that takes 3 doubles and sets the x, y, and radius of our circle accordingly. But then this constructor, once it's initialized these values, it calls the update function. So that will give the initial values of the circumference and area based on the radius that was used in this constructor. And then the other important function, very important function, is the change radius function. So this updates the radius, but then immediately after updating the radius, it calls the update function so that it can update the circumference and the area of our circle. We also have a change position function, which will move the circle. And then we have two functions, getArea and getCircumference. Now, since area and circumference are private members, they can't be accessed directly from the outside. They can only be accessed through these two getter functions. Now, you'll notice there's no set functions for area and circumference because these cannot be set from the outside. They can only be set internally based on the radius of the circle. And then we implement a print function so we can print the contents of our circle. So we print the x, y, and radius on one line, and then the area and circumference on the next line. Now in the main function, we create a circle C with the coordinates x and y, 1, 1, and the radius of 2. Then I call c.print so we can see the initial values of our circle and make sure that the radius or the area and circumference are computed correctly. Then we call it change radius, so we change the radius here to 5.5, and then we call print again to verify that the radius, the area, and the circumference all changed accordingly. So let me compile and run the program, and we can verify the results. So we see we start out with, let me move this window to the side. So we start out with x, y, radius, so 1, 1, and 2, and the area and circumference are 12.5664. And then we change the radius to 5.5, and then we print again. So we get x, y, and radius to be 1 and 1. So we haven't moved it, but we've changed the radius to 5.5, which gets reflected here. And you can see the area and the circumference have changed accordingly. And that concludes this demonstration on encapsulation in C++ classes. In this video, I'll discuss creating C++ classes with inheritance. So I start out by creating a class animal. So this animal is defined by its age, so the number of years, and its Latin name, which is a string. So it has these properties that are common to all animals in our program. And then it has some public methods. It has a constructor and a deconstructor, and then it has functions that the animal carries out, namely eat, sleep, and drink. So this gives the basic idea of an animal. Now you may notice that there are some green squiggly lines under these functions. Now I haven't gone through and implemented these functions specifically, but I've only declared the class so we can get a high-level sense of what we're talking about when we're talking about inheritance. So we can have a class animal, then we can think of things that derive from an animal or that have all the properties of an animal but implement some of their own. So we have particular animals like a dog, so that can inherit from animals. So class dog inherits or public animal. So public animal, this is a traditional inheritance way of deriving a class. So we get all of the properties of animal accessible through our dog. But the dog also implements some of its own properties. In this case, we have in dog age. So this is the dog's age. So a particular dog's age in number of years times 7. So if an animal's age is 7, then a dog in dog years would be 7 times 7 or 49. So we'd say the dog is 49 in dog years. And then it implements a method that's particular to the dog. So in this case, we know that not all animals bark, but a dog does, so it needs to implement a method for barking. So that's just one way we can extend or inherit from a particular class and then extend it so that it makes sense for that particular implementation. And then we have a class bear. So this is also an animal. So class bear extends from animal and has access to all the properties of an animal, but then implements some of its own. So in this case, a bear has a type like black, brown, or polar, and it has methods that are particular to bears, like hibernating and growling. Now, of course, our dog could also growl, and we could implement a method there, but not all animals growl, so we have to implement particular features in the class that we're extending. So we're extending animal, but in this derived class, we have to implement these particular features, these types, or these particular member variables and member functions that are particular to this class, but don't apply to all animals. Now, another important thing is how we reference and access these types. So we can create an instance of a dog, so this dog, which specifies the type or the class, and the variable d. So we create an instance of dog in the variable d. We do the same thing with bear in the variable b. But the neat thing with these derived classes is that when we go to the base class, the animal, and create a pointer, this pointer can point to any type of animal. So anyone who derives from animal, so whether it be a dog, a bear, a human, a cat, etc., this animal can point to any one of those. So in this case, it's pointing to the dog. We can also create an alias or a reference. So this animal A2, so this reference, can also reference a dog. So we have this A2, which is defined as an animal reference, can reference a dog, or a bear, or any other class that derives from animal. Now the neat thing about our pointer, so this animal pointer A1 starts out pointing to our dog D, but here I define it, on line 36 I say A1 equals $B. So this moves the pointer from pointing to the dog to the bear, and that's perfectly okay. So we could have an entire list or array of different animal types. They could be implemented as dogs or bears or something else, and we can move that pointer to point to any one of those. So the base pointer is quite an important and powerful feature that we get when working with inheritance in C++. And that'll conclude this demonstration on creating C++ classes with inheritance. In this video, I'll present how to create a C++ class with multiple inheritance. So the class I've created for this demonstration is the class Circle, which inherits from Position2D and Measure2D. So these are two classes that are implemented above, which have their own member variables and methods. And when I inherit this circle, when I create this Circle class, it inherits those methods and properties from Position2D and from Measure2D. So let's scroll up and look at these implementations. So I start this program by defining useMathDefines and including CMath. So this is to get our definition of pi, a constant for pi that we can use in our calculation of our circle. And I include IOStream so we can output some of our results using cout. Now the first class I create is called Position2D. So it's a two-dimensional position, so it's defined by its x and y coordinates, which I've defined as double, but these are protected members. Now the reason they're protected is because I want our circle class to be able to access them. So anything declared in the protected section is accessible from any derived class. So that's important to label these as protected. Now in the public section, I have a constructor, a Position2D, a default constructor that initializes our x and y to 0, and a Position2D constructor that takes two doubles and initializes our x and y accordingly. I also have a move2 function that will move our position to some new coordinates that are passed, so it takes two doubles a and b and sets them to x and y respectively. And then I have two getter functions, a getX and a getY function, so that we can get the x position and the y position independently. Then I define the class Measure2D. So this defines a measurement of a shape, of a two-dimensional shape. So in its protected section, we have an area and a circumference. But we also have this virtual void update equal to 0. So this is a pure virtual function. So in our derived circle, it must implement this update function so that it can update the area and circumference based on the particular properties of a circle. So our Measure2D is an interface into some measurement properties that are defined by area and circumference. And since we can define a circle by these properties, or a circle has these properties based on its radius, then we can implement this and implement our update function according to how we measure area and circumference of a circle. And then we have a public section for getting the area and getting the circumference from the outside. So since area and circumference are protected members, we need some getters to be able to retrieve them if we want to be able to access them from elsewhere. And then our class Circle, which extends or implements Position2D and Measure2D. So it has all of those properties, but then it implements its own. So the circle has a private member, a member variable radius that defines the radius of the circle, and an update function, which this is the virtual function that it got from Position2D. Now, since it was a pure virtual function, so virtual void update equals 0, we must implement it. And so our circle implements this update function, which calculates the circumference and the area of a circle. And then in our public section of the circle, we have two constructors, both initializing our values. You'll notice here it calls the parents constructor, so the Position2D constructor, to set its values. In this default constructor, it sets them to 0, including the radius set to 0, and calls the update function. And then our other constructor also calls the update function. Now, with the way this is implemented, it's very important that anywhere that the radius is changed or set, that we call the update function so that it gets the calculation for circumference and area. So this change radius function also calls update after it updates the radius. And then we have a print function for our circle that prints x, y radius and the area and circumference. So in our main function, I create two circles, C1 and C2, with different values. So C1 has 1, 1, and 2 for its position and radius, and C2 has 2, 2, and 5.5 as its position, x and y coordinates, and radius. So we print the values from C1 and C2, and then we call change radius on our circle and change the radius to 10, and then we call C1.print again to print the updated values. So I'll do a Control F5 to run the program, and you'll see here when I move it to the side, our first circle C1 has x and y of 1 and 1 and radius of 2 with the corresponding area and circumference of 12.5664. And our circle C2, you can see its values 2, 2, and 5.5 and its calculation of area and circumference. And then we update C1 to have a radius of 10, and with the area and circumference get updated accordingly. So anytime that the change radius is called, the area and circumference get recalculated. And that concludes this demonstration on using multiple inheritance in C++ to have a single class inherit from more than one class. In this exercise, you'll create a C++ application that incorporates the use of objects as function arguments, then create a C++ class that demonstrates data encapsulation, and create a C++ class that uses multiple inheritance. Now you can pause the video and perform the exercise, and when you've completed it, come back to the video and see how I carried it out. So here's the application that I came up with. So I start out by including IOStream and cout so we can print some of our results, and I create a const expression double pi that has a simple approximation of pi at 3.14159. So pi to only 5 decimal places. So I'm going to have a shape that's a circle, and we're going to use pi to calculate its area and circumference. Now, the first class I create is printable. It has a single public method called print. So anyone who implements printable or derives from printable must implement this print function. Then I have a class shape. So shape has a couple of sections, a protected section and a public section, and its protected variables are area and circumference, and it also implements a pure virtual function, this virtual void update equal to 0. So anyone who derives from shape must implement this update function, which the intent is that the particular shape will update the area and circumference accordingly. And then the public methods are getArea and getCircumference. So you'll notice there's no way to set the area and set the circumference other than through the update function. So the area and circumference should not be changed from the outside, so it's very important to encapsulate these members this way so that there's no discrepancy in the shape in terms of its area and circumference based on its particular measurements. And then finally, I create a class that uses multiple inheritance. So class circle inherits from shape and printable. So it also implements some of its own properties, like radius and the x and y coordinates. So these are all doubles to specify where the circle is and what is its radius. And since we have a radius in the update function, we can calculate the circumference of the circle using 2 times pi times radius, and the area of the circle using pi r squared or pi times radius times radius. And then in the public section, we implement a constructor to initialize our values and update our circumference and area based on the radius. And we implement the print function as required by our printable interface. And you'll notice that the print function was declared as const. So this const correctness is another important property that we have to be careful of, because since print is declared as const and implemented as const, when we access the getArea and getCircumference functions from our shape, those must also be const. So these ones say that we're not going to modify anything as part of the class in these functions. So when we call our print function, we output the x, y, and radius values, and we output using cout the area and circumference, and for these we call the getArea and getCircumference functions. And then since one of the objectives of this exercise was to use objects as function arguments, I've created this print circles function that takes two circles, a reference to a circle and a pointer to a circle, and outcalls their print functions. So with our circle A, the reference, we could just call a.print, and the pointer B, we have b arrow print or b hyphen greater than print. So we can call its print function using the appropriate syntax for pointers. And then in the main function, I create two circles, C and D, and then call the print circles function. Now let's compile and run the program to verify that this exercise is working as expected. So if I move our output window to the side and compare it to the circles I've created, C and D, so the X and Y's are 1, 1 for our circle C, and its radius 5. So if we look at the output, we have 1, 1, and 5 as expected, and the area and the circumference calculated. And our second circle D, which is 2, 2, and 10, we see that we get the X, Y, and radius as 2, 2, and 10 in the output, and its area and circumference calculated accordingly. And that concludes this exercise on working with object-oriented programming in C++. C++ templates are a generic programming mechanism, giving us type safety, type-independent abstractions, and flexible parameterization of classes and functions. In this video, I'll describe the key features of C++ templates, including when they should be used, and I'll share some examples. So one of the first uses for C++ templates is type safety to avoid unnecessary casts. This allows type errors to be caught by the compiler and not crash our program at runtime. They're also a way of providing abstract containers and algorithms that are type independent, and they benefit us in reusable code for different types through flexible parameterization. Now, I've created a type independent linked list as an example with parameterized data at each node. So I introduce my class as template, and inside of angle brackets I have class T. And then I define my class, so class my_node. And if you look in the body of the class, in the private section of the class, I have T, so my parameterized type T data. So this is the data type, or the data at each node of type T. And then it has a myNode pointer to the next node. So we're building a linked list where each node points to the next one, and each node has a parameterized type of data. So we can create it with any type. But there's a few caveats to this, which I'll get into below. And then we have our public section where we have our constructor for myNode, which takes parameter T data. So that's our data of type T and a pointer to the next node. So we initialize our data and our next node pointer. And if we're creating the first one and we don't have another one to point to, we could just set this to be the null pointer. And then we have a getter function just called get, which returns the data at that particular node, and the return type is T. So we use T anywhere we want to reference our parameterized type. And then our myNode pointer function, so next_node, returns the next node as a function because next is declared as private. So that's our myNode function for our basic parameterized linked list class. Now we have a parameterized function. So this template function, so we have template and in angle brackets class T. Then we have void swap. So our swap function will take two variables of the same type, of whatever type they are, type T, and it will pass the references to them. Then it will swap their values using this auxiliary variable Z, also of type T. So it does a naive swap of the variable's values. Now if we look at our main function, I start out by creating two variables. Now I have int a equals 1, int b equals 2, and double c equals 3.0. Now if I call swap on a and b, it'll swap the values fine. Then a will contain 2 and b will contain 1. And if we do a cout of a and b, the values, we should see 2, 1. Now I have this swap a, c, and if I look at it, it's going to give me an error, or IntelliSense in this case picks up the error right away because A and C are of different type. So this swap function, with the way it's defined, enforces that both parameters, both arguments to the function, are of the same type. So if I try to call it with two different type of variables or classes, it'll throw up an error saying the compiler will, if we try to compile it, the compiler will pick it up and will type check this call. So that's an important type safety that we get when we're dealing with parameterized functions. So I'll comment that out so we can avoid this error. And let's look at our creation of our nodes. So I have my node, and then in angle brackets, I have int. So this says that my node, the data type, is of type int, so we're parameterizing our class node, my node, and I'm creating a variable n, which I pass the value a, our int a. So this node n is parameterized by an int with the value a, and the next pointer will be initialized to null pointer, at least to start with. Then I create a my node int m with the value b, and it points to n as its next node. Then I create another my node of type double with c as the value. So we take our double c, and I create this variable p, and it's set to the null pointer as the next. Now, one thing I'll try to do is set it to n. So ampersand n, so the reference to n is going to be the next node. But when I do that, I introduce an error. It's a type error because we're trying to mix a double node with an int node, and it won't allow me to do that. So the compiler is smart enough, and in this case in Visual Studio, IntelliSense is smart enough to pick up this type clash, and it's not going to let us create this node with type double and mix it with type int. So that can be very important to the type safety of our program. So I'll comment this out to get rid of that error. So the important thing with templates is to avoid indiscriminate use. So if you're overusing templates, this can result in harder to debug code, and it's harder to read in some cases. It can result in much longer compile times and even larger executable sizes. So use templates carefully and only when necessary. So I have a single cout in this main function, which shows the results of the swap of A and B, just to verify that it worked correctly. So I'm going to compile and run just so we can see the output of our variables A and B. So we do get the values 2 and 1. So this was after the swap, and that was opposite of how I initialized them. So the swap did indeed work. And that concludes this introduction to templates in C++. In this video, I'll present how to declare and use a function template in C++. So we start our function template by using the keyword template and then our class parameterization. In this case, we have in angle brackets class T. So anywhere in our function where we want to reference the class of type T, we just use T. So we have a return type of T, and the function is called doubleIt, and it takes a parameter of type T. So T with the variable x. And then it just returns x plus x. So it's doubling it by adding it to itself. Now, this supposes that the type we're using supports the plus operator. If there's no operator plus overload, or it's something that doesn't make sense to call plus on it, then it's going to fail. And quite often, the compiler is going to pick up this problem and not let us proceed, not let us compile the program if we pass it a type that won't support the plus operator. Now, if we look at our main function, I pass some different types. So the first line of our main function, line 12, I do a double of 5. So double it, and I pass the integer 5. Then the next line, I pass the double 1.5. Then I pass the Boolean value true. And then in line 15, I pass the const char star, this character reference to this string, this fixed string hello. And then finally, I create a string s called world, and then I pass the string, this standard library string type, the string class, to our doubleIt function. So it's going to pass s to the function and call s plus s on this string. So let me compile it now and you'll see what happens. So I get a build error. Well, if I look over at the output or look at my error list, I see cannot add 2 pointers. So what's the problem here? Well, this const char star that I'm passing, this hello string, is being passed to our class as a pointer, and it's trying to add the pointer pointing to this string. It's trying to add it to itself. So it's a problem, and it's good that the compiler caught this and told us that, well, we're trying to add pointers, and we can't do that. This is a very unsafe operation. So let me comment that out, and I'll clear this error list. And now let me recompile and run it again to see what we get in the output after running these different types through the doublet function. So I'll do Control F5 to build, and it should run shortly. Now let me move this to the side so that we can see the output with the respective lines. So doubling 5, the integer 5, gives us 10. Doubling the double value, this floating point number 1.5, gives us 3. So 1.5 plus 1.5 is 3. Now if we're dealing with Boolean and we do a Boolean value true, so if we do true plus true, we get back true. And the string, I pass the string world, so it's passing the actual string object. It returns world world. So the plus operator is a concatenation operator. So the plus doesn't have to be defined in some traditional sense like we think of in numbers. As long as it's overloaded by the class that we pass to the function, it should return correctly. And that concludes this demonstration on declaring and using function templates in C++. In this video, I'll present how to declare and use a class template in C++. So we introduce our class with the template keyword and our parameterization. So I have template, and then in angled brackets I have class T for my parameterized type. And then I declare my class, so class position, and it has the T and X and Y. So we'll have a position, an X and Y position, with the idea that it can be parameterized by different integral values. So an int or a double, depending on the precision of the position that we want to use. And then in the public section of this class, we have a constructor position with tx, ty. So whatever type we create the class with, we have to pass to this constructor, and then we initialize the private values, so the member variables x and y. And then we have a print function to print the coordinates surrounded by parentheses. So we have x, y in these parentheses. And then a carriage return at the end. So in our main function, to use this class template, we do position, and then in angle brackets the type, so in this case int, then our variable name, and then the constructor, the values we want to pass to the constructor, in this case 1 and 1. And then I'll do a p.print on this class. Then I create another position of type double. So this object q gets initialized, gets constructed with 10.0 and 2.2, and then I call q.print on this position parameterized with a double. So let's compile and run the code and ensure that it prints 1 and 1 and 10, 2.2. And if we look at the output, we do have 1, 1 for our int parameterized position, and then we have 10, 2.2 for our double parameterized position. And that concludes this demonstration on declaring and using class templates in C++. The standard library sequence containers are the generic storage containers for sequential data. The standard ones are vector, list, forward list, and dec, or the double-ended queue. If the order of elements is important, and if you only need to look up elements by array indexing rather than key-based lookups, then sequence containers are likely what you want to use. In this video, I'll give you a brief overview of the standard library sequence containers we have available in C++. So as you can see, I've included them all here, these first four: vector list, forward list, and dec. And I've also included array, which is kind of a sequence container, but I'll get to that in a moment. And since I'm using strings in some of the examples, we're going to include it as well. So let's go down to the main function and see the sequence containers I've created. So the first one, I have a vector of strings. So a vector should be your default choice if you need a sequence container for general use. So if you're not sure what to use or what you need, and if you don't need it for any specific purpose, then choose a vector by default. The allocation of vector is contiguous in memory, and when inserting or deleting in a vector, elements may be moved, and it will grow and shrink in size as needed. Then I have a list, so in this case a list of ints. Now the underlying structure of a list is a doubly linked list. It's more fragmented than a vector in terms of memory, but elements do not move when you insert or delete them. Only the internal pointers get updated. Now a forward list, in this case a forward list of strings, it's a forward list, you can think of it as the closest approximation to a singly linked list. Under the hood it's sort of implemented that way. So it only has a forward pointer. So it's optimized for empty and short sequences. And under the hood, you're going to get a little bit more performance, but it has no back pointers. So you can only traverse it in the forward direction if you're iterating over it. And for performance, there's also no size function implemented for the forward list. So you can't query its size. Now the double-ended queue, or dec, in this case I have a dec of doubles. So it's implemented as a doubly linked list on a contiguously allocated sequence. So it's basically half list and half vector. The standard library uses a dec as the underlying container for its priority queue implementation. And finally, I have the array, which I think of as a partial sequence container. You'll notice here I specified a type, so I have array int, but I also specified a size. So this one has 10 elements, and it can't grow, so it's fixed in size. So not all of the standard container features are implemented for the standard library array. For instance, it doesn't support inserting and removing elements. So that's why I think of array as more of a partial container. Now, a few more interesting properties about these sequence containers. Array, along with vector and dec, all support random access or index-based lookups. List supports bidirectional iteration, and forward list only goes in the forward direction for iteration. And that concludes this introduction to sequence containers in the C++ standard library. In this video, I'll present some of the features of the standard library list in C++. So we use list from the standard library by including the list header. So I just have include list. And then since it's under the standard library namespace or std namespace, we're using std:\list so we can have direct access to it without specifying the namespace prefix every time we use it. Now in our main function, I create a list of ints. So list, and in angle brackets int, so we can parameterize our list by ints. So that's the type of object our list will contain. And then I call this list li. Now two of the main operations are insertion operations. So we have push back, push front, and insert. So the push back pushes a value to the back of the list. So here li.push_back, the int 1. And I can also push front, so li.push_front, the value 10. Or I can insert, but inserting, I can't insert by a particular index number. I have to get an iterator first. So what I do is I create an iterator to our begin, or the start of the list, so li.begin, and then I increment the iterator by 1, so ++itr, and then I call insert. So insert takes an iterator and a value. So at the current iterator location, so the beginning +1, in this case, I insert the value 5. So the C++ standard library list is generally better at performing inserts like push back or push front, or inserting based on an iterator. It also performs better at deleting and moving elements around inside the container when you have the appropriate iterators set, because it doesn't have indexed access. So we can't access by an index element or position or offset inside like we do with an array or a vector. With a list, we have to have an iterator. So we trade off performance for faster inserts for slower indexed access. We can also iterate over a list. So in this case, the for loop iterator looks something like this. So we have for, then I use auto on the iterator itself, just because there's a lot of typing when you're creating iterators into standard library containers, because if you look at the full description of the iterator, having to type out the list, how it's parameterized, and accessing the iterator, it's a lot of typing, and it's quite obvious what we're doing in this case by creating this iterator. So we have auto-reference IT as our iterator, and it starts pointing to li.begin. So the begin function returns an iterator of the correct type based on the li variable, and then we run this loop, this for loop, while we're not at li.end. So the end will cause this loop to terminate once we reach past the end of the last element in the list. And then we do a ++ IT for incrementing the iterator on each iteration of the for loop. And then I do a cout, and then I use this star operator, so star IT, and then we put a space. So I'm going to output each element in the list and put a space in between each one, and then I'll do a carriage return at the end. So we can verify the contents of the list when we run the program. And now a few of the properties for getting values from a list are the front function, which will return the first element, the back function, which returns the last element, and the size, which returns how many elements we have in our list. Now I put this other cout in to try to access it by an index value. So if I save it, so if I try to do li and in square brackets put the value 1 like I would with an array or with a vector container, I get an error because we don't have this kind of indexed access to a list. So we can't do this operation, so I'll comment it out again. So I just wanted to show that you can't use a numeric based position or offset into a list like you would with a vector or an array. So we'll just comment that out. And then we have the removal functions. So we have pop functions, pop front, pop back, or if we have an iterator to a particular element, we can call the erase function. So this will delete the element from the list. So I get an iterator to the beginning, to the first element, and then I erase that element. And that's how I erase from a list. I have to have an iterator first. And if I call li.clear, it will remove all elements. It will erase everything in the list. So let me compile and run, and we can look at what these cout statements give us in our console. So I'll do a Control F5 to compile and run, and we can verify the results. So if we look at the for loop, the output of the values, we can see we have 10, 5, and 1. So if you look, when we started, we did a pushback of 1, so that the list will contain 1 at that point. Then a push front of 10, which at this point the list contains 10, then 1. And then we get an iterator at the beginning. We increment it to the second element, and then we insert. So the 5 gets inserted before the 1. So we get 10, 5, 1 as expected. So the front is 10, the back is 1, and the size is 3. And that's what we expected in the output based on this code. And that concludes this demonstration on the standard library list. In this video, I'll present an example of using the standard library vector. So we include vector at the beginning of our program, so include and vector from the standard library, and then we're using the standard vector so we don't have to retype the namespace every time we use it. So the std : is implied because we're using it here in our program. Now in our main function, I have vector of ints, so parameterized by ints in angle brackets, and the variable is v. So I have this vector v that I can use in our program. Now some of the operations it supports, the first one is push back. So I can push an element onto a vector at the back of the vector. So push back the value 1. But then if I try to do a push front with 10, it gives me an error. So IntelliSense picks this up. Now the way vector is implemented, it's implemented in memory in a contiguous block. So it's almost like an array in memory, and this gives us access to index elements very quickly. But it doesn't let us just push elements to the front, which would require every element in the vector being shifted forward or shifted back. So instead of push front, we can do a push back. Now, if you need the push front functionality and you need to be able to insert elements quickly, you should be using a list as a container instead of a vector. So vector is optimized for indexing speed, but not for inserting speed. So if I need to insert inside the list or at the front of the list or at the front of the container of elements, I should be using a different container. So I'll change this from push front to push back so it will compile correctly. But I can get an iterator to some particular location in our vector. So this auto ITR is an iterator pointing to v.begin. Then I increment it by 1, and then I call insert. So insert ITR, the value 5. So that'll insert it at the second position in our vector. And this will be, if the vector was very large, this would be a slow operation because it would have to shift elements inside the vector. So vector is slow at inserting new values inside the container or the list of items. We can iterate over elements in a vector. So here I take auto reference ITR. So it's a reference to the beginning. And then I run until the iterator has reached the v.end. And I do a ++ ITR so that we can increment on each step of this for loop. And then I do a cout of star ITR. So I dereference ITR like a pointer, and I look at the value at that particular iterator position. And then I put a space. So each element in our vector will be gone through this for loop and put to the screen with a space in between each one. And then after the loop, I give a carriage return or a \n. And then accessing values, well, I have the front function to get the first element, so v.front. I can index it like an array with the square brackets. So it has very fast lookups. So I can look up an element very fast like I would indexing an array. So in this case, I get the first item. So it's 0-based indexing. So this will be the second item in the vector or the 1th element. Then we do v.back to get the last element and v.size to get the number of elements in the vector. Now to remove elements, I can pop elements, but I can't pop from the front. So v.popFront is not supported by vector like it is in list. So I'll comment that out, but I can do a pop back, or I can get an iterator to a particular location and call erase on that iterator for the vector. So it'll remove an element from inside the vector, but beware, this could be a slow operation if you're removing elements from inside your list of elements. And then we call v.clear to delete all of the elements from our vector. So we'll end up with a vector of size 0 or an empty vector. So we'll be back to no elements in our vector at that point. So let me compile and run this, and we can verify that we do get the expected results for these cout statements. Now, if we look, we do get the values 1, 5, and 10 in this vector. The front element is 1. The 1 element is 5, so it's index 0, 1, 2. So at position 1, we have 5. And the back contains 10. And at that point in the program, the size of the vector is 3, because we have 3 elements. And that's what we expected. And that concludes this demonstration on the standard library vector. In this video, I'll present how to use the standard library dec in C++. So we call it a dec, or double-ended queue. It's a type of container that's very versatile. It's implemented as a doubly linked list on a contiguously allocated sequence. So it's basically half list and half vector. The standard library uses a dec as the default underlying container for its priority queue implementation as well. So it's a very versatile container which contains many of the functions both available from the standard library list and the standard library vector. So we include it by including dec, D-E-Q-U-E. And then I'm using std:/deque or dec so that we can access it without specifying the namespace on each when we create our dec. So in the main function, I have dec parameterized by int, so int in these angle brackets, and I'm calling the dec dq. So the letters dq is our variable name. Now it has functions like push back and push front. So unlike the vector where we can't push to the front, in the dec we can do both. So we can do push back or push underscore back. So I push the value 3 at the back. I do a push underscore front and the value 1. I push back 4 and then push back -10. So in the comment here on the side, I have the contents of the dec at that particular point in the code. So after this last push front, we have -10, 1, 3, and 4 in that order. So I'll iterate over the contents of our dec in a standard for loop. So for auto-reference itr equals dq.begin. Then I do this for loop while itr is not equal to the end of our dec. And then I do a ++ itr on each iteration of this for loop to advance the iterator. And then to output the value, I just do star to sort of dereference this iterator like a pointer. So star itr, and then a space after each element. And then after this for loop, I do a \n to put a carriage return in. Now a dec also supports reverse iteration. So it has an rbegin function and an rend function. So this is the reverse beginning, which starts at the end of our dec, so the end of the list of elements, and then it iterates until it reaches the reverse end, so past the front of it. So you think of flipping the contents in reverse order and then iterating it forward, but in the reverse direction. So it's a bit to think about at first, but you're just flipping it around, and the rbegin is the end of the list and the rend is sort of past the front of the list. But we still increment in the forward direction with the iterator. So it's still ++ itr. And then we output the value, so star itr with a space after it. So the first for loop will put our elements in forward order, and the second one will display them in reverse order. The standard library dec also supports the front function, array indexing on a value, so we can, in square brackets, we can specify an element number, so a position or an offset. And then we have the back function. So the first element, the element at position 1, and the back element of our dec, we'll output here using cout. We can also pop back to remove the last element, so pop underscore back to remove the last one, pop underscore front to remove the first element, or we can get an iterator to a particular location, so this auto itr, so this iterator that points to the begin of the dec, we can call erase on this iterator. So if you have an iterator that's valid, you can call erase. Or if we'd like to remove everything from the dec, all elements, we can call the clear function, which is also supported in many other standard library containers, like the list and the vector. And then at the end, I output the size, just to verify that the size is indeed 0 after we call clear. So let me compile and run, and we can have a look at the output. Now here's the output, and if I move it to the side just so we can see the code along with the contents of our output. So our first loop that iterates in the forward direction, we have -10, 1, 3, and 4, just like what we'd expect after our final push front of -10. So at this point, if you look at the code, in the comment I had -10, 1, 3, 4, exactly what we have in the output. And in the reverse direction, 4, 3, 1, -10. So just this sequence of numbers flipped around in the reverse order. And the front element is -10. The 1 element, the index of 1, since it's array index, it's 0-based array indexing, so at 1 will be the second position element, so element, the value 1, because it's 0, 1, 2, 3, so -10, 1, 3, 4 in that order. The back element is 4, and then after we call clear, the size is 0 as expected. And that concludes this demonstration on the standard library double-ended queue, or dec. The standard library array container is a lightweight wrapper around the typical C-style array. This provides us with many of the standard library container functions for added convenience, consistency, and for safety. In this video, I'll present how to use the standard library array container. So we include array from the standard library, and we're also using the std : array, so we don't have to specify the namespace every time we use array. So in our main function, I create an array. So we have array, it's parameterized by int, but unlike other containers, we also have to specify a size. So we have int, 5. So we're creating an array of ints of size 5. I call this array A, and I use an initializer list. So in braces, I put the values 1, 2, 3, 4, 5. So we initialize the values to these particular values. Now we don't need to initialize the values right from the start, but if we know what our values are, then we can use an initializer list like this. Now for accessing elements, well, there's a.size, which will never change in the life of our array. So a.size is fixed. It will always be 5. We can't grow the array or we can't shrink it dynamically like we can with other containers. There's a front element like other standard library containers, so it'll return the first element. We can index it like an array with the square bracket syntax, and it's zero based. So a of 1 is the second element, or in this case number 2, and back returns the last element in the array. We can iterate over it with the typical standard library iterator. The array supports the a.begin and a.end functions. So in this for loop, we create an iterator that goes from the beginning of the array to the end of the array, and it increments by 1 on each iteration of the loop. And this iterator, we dereference it with the star like we would a typical pointer, so star itr, which will give us the value at that point in the iterator, followed by a space. So we output the contents of array with a space, delimiting each element with a space. And then we do a carriage return. We also get a fill function in the standard library array, so it will fill all the elements with a particular value. So a.fill2 will set all the elements in the array to the value 2. It also supports typical pointer arithmetic through the data function. So I have an integer pointer, so star I, which is set to a.data. So this gives us a pointer into the underlying elements directly. So I can do typical pointer stuff. If I do I plus 2 and I set the 3, so I have star, and in parentheses I plus 2, I set that equal to 3. So plus 2 would actually give us the third element in the array if we're looking at I as an array. So if I save this, then this element here should be set to 3. So let me compile and run the program, and we can look at the output. This will verify that our array is working as we'd expect. And now if we look at the size, it's 5. The first element, the front, is 1. The element at index 1 is 2. So the second element, the back, is 5. And the values are 1, 2, 3, 4, 5. Then we call the fill function, and we set them all to 2. And then at I plus 2, I set it equal to 3. And at that point, it should be 3. So I think I was right the first time. And I'll change this back to 2. And that value should be 3. So I'll compile and run it again to reflect that change. And if we look at index 2, so we have to be careful with the pointer arithmetic. It's easy to mistake if we're using zero-based indexing and we're just using direct pointer offsets directly. We have to be careful if we're switching from this kind of pointer syntax to the indexing syntax. It's easy to get confused. I would avoid using this type of pointer arithmetic if possible. If you're mixing with legacy code and converting to standard library arrays, you might need to have this in place in some of your code, but avoid it if you can. But know that the functionality is there if you absolutely need it. And that concludes this demonstration on the standard library array container. A queue is a container adapter, so it's not a container on its own. You can think of a C++ container adapter as views into container functionality, but for a specific purpose, like a queue. So the elements of a queue follow the first in, first out approach for adding and removing elements, which we refer to as pushing elements into the queue and popping elements off of the queue. In this video, I'll present some of the features of the standard library queue container adapter. So we include it from the standard library by just placing include queue at the top of our program. So include QUE UE. And then we're using std:/queue so that we can access it without specifying the namespace. So in my main function, I create a queue of ints. So queue, and in angle brackets to specify the type parameter, we place int. So we're just creating this variable, the letter q, the lowercase letter q is the variable name of this queue of ints. Now to add elements to a queue, we just push them onto the queue. So in this case, I push 1, then push 2, push 10, push 20. And then we'll call some of the standard functions. So q.size will give us a number of elements. q.front will give us the element at the front of the queue. q.pop will remove the element at the front so that when we pop an element, the front gets updated. So whoever's at the front of the queue, so at the front of the line, gets removed first. So first in, first out. So the first one that was pushed was the element or the number 1, so that will be the first one to get popped. And then we can query whether the queue is empty by calling the empty function, which returns a Boolean value. We can pop any number of elements until we reach the end. So if you look in this program, I call push 4 times, and then I call pop 4 times. So after I've called pop 4 times without any subsequent pushes, the queue should be empty. So when we query the empty status before calling these 3 pops, there should be 3 elements on the queue at that point because I've already called it once. Then I remove the 3 elements that are remaining, and then I call empty again, and it should be empty at this point. So this should demonstrate some of the basic and essential functionality of this standard library queue container adapter. So let me compile and run this so we can verify the output. So I'll move this output window to the side so we can look at the results alongside of our code. So when I call size, I've pushed 4 elements onto the queue, so the size is 4. And the front element, the first element, the element that will get popped when we call popped, is the element 1. So front 1 is at the front of the queue. After the pop, 2 is at the front of the queue because that was the next one added. And at that point, it's not empty. But if I call pop 3 times, to remove the remaining 3 elements, and then I call the empty function, it is empty, so this last line of the output's true because we are empty at that point. And that concludes this demonstration on the standard library queue sequence container adapter. Try that again. And that concludes this demonstration on the standard library queue container adapter. The standard library priority queue is a container adapter, a variation of a queue in which elements are sorted on insert so that the priority element is always on top. In this video, I'll present how to use the standard library priority queue in C++. So we get the priority queue from the queue header, so I've included queue at the beginning of my program. Now I've included some of these other standard library headers, but I won't get to those just yet. And if we'd like to use the standard priority queue without specifying the std namespace, we can just put in the line using std:/priority_queue. And that way we can access it without this standard prefix. So in our main function at this point, I create a priority queue. So priority_queue parameterized by ints. So it's going to be a queue of integers. And I call the variable pq. So to add elements, I call a push function. So we push elements onto our queue, so push 1, push 10, push 100, and push 50. So at that point, if I look at the size, so if I call pq.size, it should be 4, And the top element, in this case, is going to be 100. By default, it will sort it from greatest to least, and when dealing with integers, that will put it in descending order from largest to smallest. So at the top of our queue will be 100, then we pop it off, and then if we look at the top after that pop, the top element will be 50 at that point, because that's the next biggest. So we should see 4, 100, and then 50 in our output, and then we're going to loop over all of the elements of our priority queue in order. So we have a while loop. While the priority queue is not empty, I output the top element followed by a space, and then I pop that element and then loop until the priority queue is empty. So we'll have the space delimited list of elements in the priority queue, excluding the first one we popped off higher up in our code here on line 26. And then at the end, I put a carriage return just to put a space at the end of the output. Okay, now I'll compile and run and we can see what the program gives us as it is now. So I'll move the output window to the side. And if we look, we get a size 4 because we pushed 4 elements onto the priority queue. The top element was 100, the largest integer. And then after we pop it off, the next one is 50. So at that point, we have 50, 10, and 1 in our queue, in our priority queue. Now I'm going to make a minor modification. That has to do with how we construct the priority queue. Now we can give it a few more parameters. By default, priority queue has an underlying container type of vector, and it's sorted using the less comparator. So if we're sorting based on less, it puts it in order from largest to smallest. So let me give it a few other parameters. So in our priority queue, in the parameterization after int, we specify vector of ints. So that's the underlying container, and the comparison, we're using less int. So if we look at the top of our program, I've included the vector header and the functional header. So these come from the standard library. Vector gives us the vector container, and the functional gives us the comparators less and greater. So as I have it set up now with the priority queue of int, with the underlying container a vector of ints and the comparator less int, this is the default. So without specifying these further two parameterizations, it's the same. So that's the default we get when we're dealing with priority queues. So if we look at it, the default here, priority queue int, that's the same thing as specifying it with vector int and less int. So that's the default. So if I compile and run this again, we do get the same output. So we get size 4, top 100, we pop the 100 and get 50, and we're left with 50, 10, and 1. So exactly the same thing. So now let me change this a bit. We can also build a priority queue with an underlying container of a double-ended queue or deck, which is why you'll see at the top of the program, in the top of this source file, we include deck, and we're using the standard deck. But I also want to change the comparator. So I want to use the greater comparator. So we can change the priority of the ordering so that the highest priority element is the smallest value. In this case, we flip things around so that 1 is the priority element in this program and 100 is the least element, at least in terms of priority. So a reason why we'd like to use a deck, if our priority queue grows very quickly at times in our program, then we might want to use a deck because it does tend to grow more efficiently than a vector. So we can use the deck if we want. So if we compile and run this again, we'll see that our elements come out in the reverse order of what they were before. So I'll do a Control F5 to recompile this and run it again. And I'll move the output window to the side, and you'll see right away the size is still 4 after we push 4 elements, which is a good thing. But the top element with this configuration is 1. So since we've switched the comparator from less to greater, our top element becomes 1, and then after the pop, the top element is 10, so the next smallest element. So at that point in the program, we're left with 10, 50, and 100 left in our priority queue. And that concludes this demonstration on using the standard library priority queue container adapter. the C++ stack container adapter adds and removes elements in a last-in, first-out fashion, abbreviated LIFO or LIFO for short. So adding elements to a stack is usually called a push onto the stack, and elements are removed by a pop from the stack. In this video, I'll present some of the features of the stack from the standard library in C++. So at the top of my program, I'm including stack from the standard library, and I'm using the standard stack. So we have using std : stack to say that when we reference a stack, we're talking about the standard library version. So in my main function, we have a stack of ints, so it's parameterized by ints in these angle brackets, and the stack is called s. Now what I've attempted to do here is not quite right, so I've set it equal to this initializer list. Now for many other containers this is valid, but with a stack it's not. So what I have to do is wrap it in parentheses. So this will let our C++ compiler deduce that this initializer list is for the underlying container of our stack. So the underlying container of our stack, since stack is a container adapter and not a container itself, it needs an underlying container to store our elements. And in this case, it's a DEC or double-ended queue from the standard library. So what happens here is the underlying double-ended queue gets initialized by this initializer list, and that gets passed to the constructor of the stack, and everything works fine like this. So here we've created a stack with these 5 numbers, this 5, 8, 11, 74, and 101. Now if we want to check the stack, the top of the stack, and push more elements onto the stack, we can do so like this. So we have our cout of the current top of the stack. So we call s.top. So in this initializer list, the last one that would be put onto the stack is this 101. Now if we push another 20 onto it, the top of the stack is 20. So if you think of piling up a stack of books, if you stack up the books from bottom to top, when you take one off, you take one from the top again to take books off of the list. You don't try to take it from the bottom, otherwise your stack of books falls over. So that's essentially what's happening with a stack here, except we have integers. So here I demonstrate it by checking the top, pushing something on, checking it again, then pushing another number, say 200 onto the top, and then I check to make sure it works correctly. Then I can see how we're going to remove our integers from the stack by looping over the stack by checking the top, which I want to call as a function. So s.top followed by a space. Then I pop that element off the top of the stack, and then I continue this way, so putting the next element and then popping it, delimiting it by this space, and then proceeding until the stack is empty. And then I do a cout of the carriage return, a \n, and then I output empty, which is the empty function, so s.empty will tell us if the stack is empty or not. It will return true or false, and I just want to verify that this loop proceeded correctly, and at that point, at the end of the program, the stack is indeed empty. So let me compile and run to verify that everything I've described here is what we get in our output. So I'll move the output window to the side, and we'll look at the results. So at the beginning, the top is 101, which is what we expected because that was the last element in this list. Then we push 20, and then 20 is the top, push 200, and 200 is the top. So if we look at the entire list, looking at the top element, then popping it off, and then so on until we reach the end of the list, we have 20 or 200, which was the last push, then 20, then 101, 74, 11, 8, and 5 as expected. So after that happens, after this while loop, the stack is indeed empty, and when I call the empty function at the end, just before the return at the end of the main function, it returns true as expected. And that concludes this demonstration on the standard library stack container adapter. Associative containers are containers that are indexed based on a key value rather than just a numeric offset into an array. There are 2 main types of associative containers. Ordered associative containers, like sets and maps based on a balanced binary tree like a red-black tree data structure, Then there are unordered associative containers with lookups based on hash functions. So for the ordered case in a binary search tree, the search complexity is big O of log n, so it searches in logarithmic time. Now in unordered containers, it uses a hash function which has a fixed number of steps, so the search complexity is big O of 1, what we call constant time lookup. So it's much faster to look up an element in an unordered variant rather than an ordered variant of an associative container. Now in this video, I'll present how to describe the key types and features of standard library associative containers, including when they should or shouldn't be used, and I'll show you a small example. So for the ordered ones, we get set and map and multiset and multimap. So the set versions, the set and multiset, both come from the set header, and map and multimap come from the map header. And then for our unordered containers, we have unordered set and unordered multiset, which come from the unordered set header, and then we have unordered map and unordered multimap. Now for multimaps and multisets, this just means that there contain multiple values for a given key. Whereas in the regular variant, if you override a key or insert an element in a particular way, it overrides what's already there instead of just adding to it. So it loosens the constraint of uniqueness for keys and values. Now, creating and initializing associative containers is done in much the same way as other standard library templates. We parameterize it according to type, and it provides us some type safety. So here we have ints and strings parameterizing these sets and maps and unordered sets and unordered maps. So if you look at a map versus a set, the map has two parameterized types. A map takes a key and a value corresponding to that key, so it has to have these two type initializers, the key type and the value type, and the sets only have a single index, so just the int or just a string in case of the unordered set. So we just specify the type, and it knows the type of elements we can store in the container. If the order of the elements is important, then we use the ordered variant because there is no guarantee of the order of elements that are placed in an unordered associative container. But if you don't need the order and you want a fast lookup, then use the unordered variant because it is indeed much faster to look up a particular element in an unordered associative container. And that concludes this introduction to the standard library associative containers. In this video, I'll present some of the features of the C++ standard library set. So at the top of our program, I include set. And then we're going to be using the standard set, so using std:/set, so we can refer to set directly without having to invoke the namespace every time. And you'll notice I'm also using cout, and this bool alpha, this is a modifier for cout so that we can output Boolean values as true or false instead of 0 and 1. So now on to our main function where we create a set. So this set is going to be a set of integers, so set, and in angle brackets we parameterize it as type int, and the set is called s. Then we set this equal to the following initializer list. So this list of numbers surrounded by curly braces. So we start it with 1, 2, and 400 as our values. Then we insert some more values using the insert function, so s.insert 20 and insert 250. Now notice if I do an insert, let's say the value 1 again, this is a duplicate, so it won't get added to the set, so we won't have two instances of 1. We'll just have the single one in the set. So the uniqueness of a set, uniqueness of elements is enforced, so if it sees a duplicate, it won't add it again. We can iterate over a set like other containers. So I have this auto reference to itr to s.begin, so that's the beginning of our set. And then we loop until we reach the end of the set. And then we do a ++ on our iterator on each iteration of this for loop. And then to output the value at the current iteration, we just do a cout on our *itr. So we dereference it like a pointer to get the value, and then we put a space after each element. Then after this for loop, I do a carriage return, And then we look at the size. So if we query the size function of our set, it will tell us how many elements are in that set. We can also look for a particular element. So we're looking for the existence of the value 10, which in this case should be false because we haven't inserted 10 anywhere in our code, so it should return false. Or what it does return, the find function, it returns an iterator, so this itr. So if we want to see if it exists, we see that it's not equal to s.n, otherwise it points to the element it finds. If we call find on 20, which we did insert into the set, this iterator will point to the element 20, and when we compare it to s.end, it will return true. So itr not equal to s.end is true when we do a find on 20, and it's false when we do a find on 10. So let's compile and run the program and verify that these set operations work as expected, and we get the desired output. So I'll do a Control F5 to compile and run the code. Now I'll move my output window to the side so we can look at the code and the output at the same time. And we see the values we get in the set are 1, 2, 20, 250, and 400. So the 1 only occurs once in our set because of the uniqueness constraint. So the size at this point is 5. So we have 5 elements in the set. If we call find on the value 10, it returns false because it's not there. And calling find on 20 returns a valid iterator, so it's set to true in our output. And that concludes this demonstration on the standard library set container. In this video, I'll present some of the features of the C++ standard library map. So at the top of our program, we include IOStream, map, string, and utility. So IOStream will give us cout, map will give us our map container, which we are demonstrating in this video. String is included because we want to have a map with strings in it. And the make pair comes from utility because map comes in a pair, so it has a key and a value. So we can use the make pair utility function to create a pair that we can insert into a map. And I'm using the namespace standard string literals, so we can use the s suffix for our map strings. Now in our main function, we'll create a map. So here we parameterize a map with 2 types. So we have the key type, in this case an int, and the value type, a string. So what this is going to do is map a particular port number to the string describing the port. So this map port starts with a curly brace, and then it has pairs of values inside of curly braces themselves, delimited by commas. So we have 80, the int, comma, HTTP, the string literal. So this will construct a map with these 3 entries, these 3 pairs, so the int string pairs of 80 HTTP, 443 HTTPS, and 22 SSH. We can call insert on a map. So after we've created a map and it has some values, we can insert more values, and the map will expand accordingly depending on how many values we put into it. So it can accommodate inserts. It's not fixed in size. So we'll do an insert, so port, and I can index it like an array or just a basic array using square brackets. So I give it 993, and then I set that equal to the string imap, IMAP. We can also call port.insert, so we're inserting into our map a pair. So I call make pair, and I provide the number 25 and the string SMTP. So it makes a pair that we can insert into the map. Accessing elements from a map is just like array indexing. So looking at port 80, so if I port and I specify the index 80, it retrieves the string HTTP. And we'll output it here just to verify that we do get the expected string. We can iterate over a map. So I have a const auto pointer s. So for const auto s colon port. So I'm using this abbreviated for syntax that will loop over all of the pairs of values in our map port. So then we output a cout, s.first, colon, s.second. So s is a pair with int and string based on port, which is a map of ints and strings. And then at the end, I output another carriage return. Now let's run this program and verify that our map behaves as expected. So I'll move the output window to the side, and we can look at the results. So on line 23, I do a cout of port 80, and that returns HTTP as expected. And then I loop over all of the elements, all the pairs in our port map, and it outputs all of the results that were inserted into the port. And you'll notice that numerically they're all in order. So we have 22 SSH, 25 SMTP, 80 HTTP, 443 HTTPS, and 993 IMAP as expected. And that concludes this introduction to the standard library map. Most of the built-in types or standard library objects in C++ work very nicely with standard containers like sets and maps. In this video, I'll demonstrate an example of using a custom class with set and map. So I include iostream, string, set, and map for this demonstration so we can use cout, string, set, and map from the standard library. Now the custom class I've created for this demo is class record. So this record has some public members, two member variables, a rank and a string value. So we have a constructor which accepts a rank and string value as parameters and initializes our member variables accordingly. Now our records need some sense or some measure of order, which is why we overload the less than operator. So this is required by map and set so that it can insert the records accordingly. Remember that set and map are both ordered variants of set and map. So it needs this comparison. So we have bool operator less than, and then its argument is const record reference r. And then it returns const. So it's not modifying any of the objects, both the current class the current object we're working with, which we reference as rank, and the variable r that gets passed as an argument. We're just returning the comparison of the ranks. So rank is less than r.rank. So it returns bool whether the current object is less than the one we're comparing it to. This will also ensure that we sort it in ascending order inside of our set or map. Now in my main function, I've created a set of records S and a map that has the key as a record and the value as a string. Now in the first part here, I create two records, one with rank 3 and one with rank 1. I've put in the one with rank 3 in first and then the one with rank 1 in second. So after this gets inserted into our set, it should be rebalanced into ascending order. So when we loop over it, we should get the elements in order. So 1 first and then 3 second. If I'd like to insert things into my map, one of these records, well, the record is the key of the map. So we take M and in square brackets, we put the key, let's say R1, and the value is some other string. In this case, I've literally called it another string. So it works a bit differently in a map where our record is the key, so it acts as an index into some other set of strings. Now after we do the inserts on the set, so we loop over all of the elements of our set S, and the value is the record. So this const auto reference rec is each record in the set S. So we can output rec.rank and rec.value. So that's the member variables of our records. So I'd like to compile and run it now to make sure that this is the case. So in our output, we should have the record with 1 first, rank 1 first, and rank 3 second. So Control F5 will run the program because it's already been pre-compiled. And if we look in the output, we see that the cout returns in the for loop, we get 1 OK first and 3 tests next. Now the reason I can do this, the reason I can put it into a set is that my record has implemented this comparator operator. That's the key. So the comparator of less than lets me rank or put some ordering on my custom structure, which is required by the map and set implementations. Now if I removed this operator, I would get a few errors if I tried to compile my code. I'm going to do that quickly. So I'll put a comment block around this operator, and if I try to compile and run it again, it should give me some compiler errors, which we'll see in the output over here. And it says there were build errors. And no, we don't want to run it. So it needs an operator, this less than operator, to compile. Otherwise, there's no way that set and map can understand how to order the records. And that concludes this demonstration on working with custom objects in sets and maps in C++. In this exercise, you'll create a C++ application in which you will create and use a function template, create and use a sequential container, create and use a sequential container adapter, and create and use an associative container. Now pause the video and perform the exercise, and when you've completed it, come back to the video and see how I did it. So here's how I carried out the exercise. So for my container, I've used a vector. For my container adapter, I've used a stack. And for my associative container, I've used a map. And I'm also using a string in this video for some of my objects, namely inside of my map, it's a map of strings. And the function template I've created is down here. It's called output container, which is templated by a class T. So output container expects to get a C++ standard library container as an argument, whether it be a vector or a dec, or something I can iterate over, and it outputs the contents of it. So it has template class T, and it returns nothing, so it's void output container T of reference X, so it passes the container as a reference. And then for each element, so for auto reference R, colon X. So X is the container, it outputs the value of each element in the container delimited by a space, and then when it's done, it outputs a carriage return. So in my main function, I create a vector of ints v, so vector, and in angle brackets int v equals this initializer list, these values 1, 2, 3, 4, 5. And then I call output container on our vector v. Then I create a stack of ints called si, and I push these four elements, these four integers onto the stack, so 10, 20, 5, and 100. And then I loop while our stack is non-empty. Then I output the current top element followed by a space. Then I pop that element. So this should output each element from our stack from top to bottom, delimited by a space. And then at the end of it, our stack will be empty. And then for my associative container, I've created a map of strings. So string is as the key and string is the value. I've used these initializer lists. So I have hello, hi, goodbye, and see you later as my keys and values. And then after I've created the map, I add a subsequent key or subsequent map entry with the key bonjour and the value salut. And then I output by indexing one of my elements. So I output by indexing the key goodbye, and we'll see if that works in this cout in the final line. Now let me run the program and we can see the output. So my vector of ints that I pass to the output container function, I see the values 1, 2, 3, 4, 5 delimited by a space, as I'd expect from this function. And then with my stack, I push the values 10, 20, 5, and 100. And remember, stack is first in, first out. So the most recent element I pushed onto it will be the first one to come off. So they'll come off in reverse order. So if we read them back up, so 100, 5, 20, 10 is what I get in the output. So it popped off the stack as expected. And then finally, my map, when I output the map entry at goodbye, it returns see you later. And that concludes this exercise on working with containers in C++. In this video, I'll introduce some of the key features of the C++ standard library. Now, the standard library consists of the following core components: containers, algorithms, iterators, and functors. The containers offer more functionality than just basic arrays, so you have very powerful sets of elements that are tailored for the application that you need them for. So you get things like vectors, lists, double-ended queues, sets, maps, etc. And there's a consistency across the interfaces of these containers. You have functions like the size function that'll return the number of elements in a container regardless of the container you're using. And the algorithms we use on containers also have a consistent interface, so that we could even change the underlying container we use with a particular algorithm, and it will continue to work without needing re-implementation. This is done through the use of iterators and functors, or sometimes called function objects. Now, containers are just objects that contain other objects. We have things like vector, list, double-ended queue or deck, set, multi-set map, and multi-map, to name a few. These offer more functionality than working with just basic arrays or basic linked lists. And we have the standard library algorithms to work with, and to work with this data in the particular containers. So it's very powerful, and there's a lot of tools in the standard library that let us work with these different containers. So the standard library algorithms fall into three main categories: modifying algorithms, non-modifying algorithms, and sorting. So the modifying algorithms, we get moving and rearranging elements, copying and replacing values, or changing values. So these perform a variety of powerful operations and some basic and essential operations that we need with containers. Some of the examples are find if we're looking for a particular element, search n, count, mismatch, copy, and replace, to name a few. So we don't need to write our own methods to perform these common operations. Now, iterators allow us to cycle through a range of values, such as container elements. Some examples of the iterators in the standard library are the advanced iterator, distance, begin, end, reverse iterator, and move iterator. And there are 5 different types of iterators: input iterators used to read values, output iterators used to write values, forward used to read, write, and move forward inside of a container or a set of elements, bidirectional, which allow us to read, write, and move forward and backward, and random access, which allows us to move freely and index elements from wherever we'd like inside of a container. So iterators give us a consistent and safe way of working with sequences of elements, especially when using standard library algorithms on containers. Iterators act as pointers to elements in containers, and we can even get iterators pointing to elements of a basic array. These iterators are safer than just using naked pointers like we would in C. Now, functors are sometimes also called function objects. They're used in conjunction with the standard library algorithms in many cases, or you can use them on your own in your own implementations. They provide a convenient and consistent syntax that allow us to pass objects as parameters without resorting to verbose syntax like we would in C when passing around function pointers. To implement them, we just overload the operator function call or the double parentheses operator inside of a class or a struct. So they create objects that look like a function, and they perform a function usually on a set of on a range of values using a standard library algorithm with a standard library iterator. And that concludes this introduction to the standard library containers, algorithms, iterators, and functors in C++. In this video, I'll present how to use the standard for each expression in C++. So for this video, I'm including IOStream so that we can use cout to output some of our results. I'm including vector because that's the type of container we're going to use for each to iterate over. And I have included algorithm, which contains the standard for each expression. So to use this standard for each expression, I'm using standard for_each. So this will give us a type of loop that uses iterators instead of the typical C++ for loop syntax. So let's look at our main function. Now I've created a vector of ints v set to the following integers. So there's a small handful of integers, 42, 128, 995, 443, 9000, 345. So I just randomly put some in there so we have something to work with for this example. And then I do a cout, a for loop with iterator. So the first one is a typical for loop that you would write using an iterator. So it has for auto reference itr. So I created an iterator using an auto, and then I set it to v.begin, the beginning of our vector. And then I run it until we reach v.end. And on each iteration of the for loop, I do a ++ itr to advance it to the next element. And then we do cout star itr to get the value at that particular location, followed by a space. So I output it space delimited using this for loop. Then I use a for each function. So I have, or a for each expression with a function. For each, so for underscore each. Then the first parameter is the start, so v.begin. This is the iterator we'd like to start at, and we want to run until v.end. And then we pass a function we'd like to use for each element in the loop. So it uses the vector, and it uses the vector iterators to step through, and then it passes each value to this output val function, which I've created above. So this is just void output underscore val, and it takes an int as a parameter, and it just outputs the int followed by a space. So it does exactly what this first loop does, but with a very different syntax. And the final version of for each loop is with a lambda expression. So I do for each, for underscore each. Again, I start at v.begin as the first argument, v.end as the second argument, and the third argument, instead of passing a function, I give it a lambda expression in line. So we have our capture list, which is empty, so it's just this double square bracket. And then in parentheses, the parameter we're passing is int v. So this int v parameter is the same as our output val, so we're just passing the value v, which is an integer from each iteration of the for loop, wherever it is in this range of iterators. And then we have an open brace in line, and then a closed brace. So this is our lambda function. And then we close the parentheses at the end, which matches up with the start of the for each. So inside the lambda expression, all I do is a cout of v followed by a space. So these three loops are equivalent, but the syntax varies between each one. So you have three ways of doing it. So let me compile and run, and we can see the results and see that it matches up with what we'd expect. Now when we run it, we see that the output for each one is identical, which is what we expected, but the first one is with a basic for loop using an iterator directly. The second one is a for each loop, which passes the value to it in a function declared outside, and then a for each loop with an inline lambda expression. Now there are some pros and cons to each approach. The cons of the for loop is that we do have to declare an iterator, and it does simplify things if we can hide this like we do in the for each loop. And unless we need some special control over the iterator, if we're just going through the entire list, like in this case the vector, one element at a time, the for loop is a bit simpler, so it depends on what we want. In the second case, the for each loop, this is the least amount of code within our main function. If we're going to be doing this for each many times, maybe with a bunch of different vectors, and we are reusing this output value function quite a lot, this is a nice concise way of doing it. In the third way, the lambda expression method, we again avoid the iterator as compared to the for loop at the beginning. And if this is a one-off for each function, if we're only ever doing this once, the lambda expression is a nice inline way of doing it, where we don't hide the output value function somewhere outside our function, and we can see what's happening right here in our code. So in summary, for each is one of the obvious use cases for lambda expressions. From what I've seen, it seems to be the canonical one. So if you use the lambda expression inside of a for each loop like this, it's quite a common way of doing it. Now, there are different ways of doing this and different methods, different approaches, and it should all depend on your needs and what you want your code to do, what you're trying to solve in your code. But at least now, after this video, you have a few options to work with. And that concludes this demonstration on using the standard for each in C++. In the standard library, iterators provide a window into container elements that we use our algorithms on. Very seldom, if ever, do we perform algorithms on the container directly. In this video, I'll present how to use the standard find iterator on a vector of integers in C++. So to get our find function in C++, it's part of the algorithm header. So we include algorithm along with iostream and vector in this video so that we can use cout, find from our algorithm header, and vector from the vector header. Now, in our main function, I create a container vector of ints. So I parameterize it by int, and I set it to the following integer values. Now what I'm going to do is find a particular element in this vector of ints. So what you want to think of when you're finding an element is it doesn't return the element itself, its value, nor even an index that numerically provides some offset to that element. It returns an iterator. So here we have a vector int iterator itr equals find, and find takes three parameters. The first one, the beginning, so this is the iterator pointing to the beginning of the list, the end of the list, so v.end, and the value we're trying to find. Now find operates on a half-open interval, so it looks at the beginning interval, so it includes this element, but end points one past the end of the list. So it's like there's an empty element past the 5 here in this vector of ints. And that's what v.end points to. So it's the end of the list, but one past the end. So we have to think of this as a half-open interval we're looking in. So from the begin, including the beginning, up into the end, but not including it. So the iterator will return the pointer to our element that we're looking for. And you can see that this element 443 that I'm looking for does exist in the list. So it'll return an iterator to that location in the list. Now, one other thing, I've completely specified the type of iterator. Quite often, where it's obvious that find will return an iterator, instead of putting all this extra typing in and possibly making our code a little more verbose, it's easy just to make this auto. And I recommend with iterators, just making them autos, just because it's quite obvious from the context what we mean. Now what I do in this video is I find the element, and then I have a while loop that'll go from the iterator that find returns until the end of the list. So it will output all the values from the value we find, in this case from 443, until the end of the list. So we see out the value at the particular location of the iterator, then we increment the iterator to the next element, and we do that till we reach the end. So let me compile and run the code, and we can verify that the results do give us the 443 and the rest of the values until the end of the list. And if we move our output window to the side and compare it to our list, we can see that we did indeed find the 443, and then we also printed 9,000, 3, 4, and 5. So that's what we expected. And that concludes this introduction to iterators using find in C++. In this video, I'll demonstrate a number of ways you can use the standard library findIf in C++. We'll use a standard library function, a custom function, a lambda expression, and a function object to perform a findIf. So findIf comes from the algorithm header, and I've included some other headers here including iostream, vector, cctype, and string. So what we're going to do is define a few functions that we're going to use with findIf. So findIf is a way of searching in a container to find if a particular condition is met. So let's scroll down to our main function first, and then we can go through some of the examples. Now I start out with defining a string, so a string s equals, this is just the test, period, space 1. And then I have a vector of doubles, si, which is set to the values 1, 2, 3, 3.14159, 5, 6, and 100. And now I'm going to perform 4 different findIf functions. The first one is with a built-in function. I'm using the isDigit function from the CC type header. So what findIf returns is an iterator. So if the iterator returns the end iterator, then what we're looking for was not found. If it returns anything else, it will be the location of where that value is in the container, including a string, so we can treat a string as a container because it has a begin and end iterator, which is what I'm doing in this particular example. It will return where it finds the digit. So if we do findIf from the beginning of the string to the end of the string, and we pass it the isDigit function, it will return if there is a numeric digit in that string. And if we look at the string, I've kind of manufactured a digit in the string. I've put a 1 on the end, so this should return a valid iterator. And what I do is I compare it to s.end, and if it's not equal to s.end, it means we find it, and I output the value. So I output the value of the digit. Then I do the same thing on a user-defined function. I do a findIf from the s.begin to s.end, so that from the beginning of our string to our end, the whole string, and then I pass it the isSPC function to the isSPC function. It's the isSpace function. So if it finds a space, it will return a valid iterator to the location of the first space it finds. So if I scroll up to the isSPC function, all it does is take a single char value, so this character C, and compares it to the space. So it will return true if it finds a space character. And again, I output true or false whether or not it finds the space. So if it does get to this part of the code where it outputs the value at the U iterator, it will output true or false, because if it outputs a space, we won't actually see it. Then a lambda expression is just doing the same thing with an inline function. So I'm doing another findIf on our string, so from the beginning to the end of our string, and then I use the double brackets and in parentheses our parameter, our character, and then I return is if C is equal to the character X. So it's going to look for the character X in our string. So if we scroll up and we look at the string, we see that there is no character X. So this should not print anything. So this if statement should be false. So it won't print V and the value because it won't find the character X. And then finally, doing this with a function object. Now I'm looking at this SI from si.begin to si.end. I'm passing the function object is_approx_pi with the double brace because it's an object. So it uses this isApproxPi object to look to see if a number in this list, so this vector of doubles, there's a value approximately pi. So how do we define this function object? Well, if we go up to where I've defined it as a struct, so struct isApproxPi, we could also do it as a class, as long as this operator double parentheses, the open close parentheses, is a public method, then it's fine. So this function object does bool operator, open and close parentheses, and it takes the double D as an argument, so a single double, and then it returns whether true if D is greater than or equal to 3.141 and less than 3.142. So anything in this range we consider to be approximately pi. So we go down to our function object version of findIf, and we see that it will find one value approximately pi, this 3.14159. And then it will output that value, so it uses the iterator z, it compares it to si.end, and then it outputs that value. So now let me compile and run to make sure the results compare to what I've just described. So I'll move the output window to the side, and looking for the digit in this particular string s, there is a 1 at the end, so it does return the 1 value that it found. The user-defined function looked for a space, and it did find one in our string, and it returned true. The lambda expression was looking for the character x. it didn't find an x because there's no x in our string, so it doesn't output the v colon and the value because there is no x, so it skipped over that in this conditional. And then finally, our look for the isApproxPy function object version of our findIf. It did find one value that we considered approximately pi, and it outputted the value z colon 3.14159 as expected. And that concludes this demonstration on using findIf in C++. In this video, I'll share a list of some of the non-modifying algorithms that we use with the standard library containers in C++, and I'll demonstrate the use of one of them. Now, the list of the non-modifying algorithms I've put here in this code inside of this comment block. So we have the for_each, count, countif, find, findIf, findIf not, find first of, adjacent find, and find end. We have equal and mismatch, search and search n, and all of, any of, or none of. So these are all non-modifying algorithms that just inspect the values of a container, but they don't actually modify any of the contents of a container. Now we get these from the algorithm header, and in this video, I'm using the following objects from these standard library headers. So from IOStream, algorithm, and vector, I'm using cout, vector, the begin and end iterators, any of, so any of is the non-modifying algorithm I'm going to use, and I'm including the standard bool alpha so that we can output the result of any of as a true or false string. Now let's go down to our main function. Now I'm going to demonstrate two versions of this code. We're going to do the first looking at the vector v. So this vector of ints v is just set to the values 1, 2, and 3. And the iterators that we can use on this array of ints a, so a of 10, so it has 10 integers, the numbers 1 to 9 and 0, we can get an iterator using the iterator begin and end functions that I've included at the top to get a standard library style iterator so that we can use these algorithms, these non-modifying algorithms, on a basic array in C++. So we can treat this basic array as a container if we use its iterators. Now, the iterator for vector is just begin, v.begin or v.end. So what any of takes, what these non-modifying algorithms take, are iterators. So they usually take a range from some beginning iterator to the end. So in this line 38, I have bool b equals any underscore of, and then the arguments I pass to any of are the beginning of the container as an iterator, so v.begin, v.end, the lambda expression or function object I want to use. In this case, I have a lambda expression. So this is the function I want to use with any of. So what this is going to do is run this function with the int a as an argument, and so in braces. So this is a inline function as a lambda expression that returns if a is greater than 5. So if any value in this range specified by these iterators is greater than 5, it will return true. Otherwise, it will return false if it doesn't find any. And then we output the bool alpha b so that we can see the true or false whether or not any of has found it. So I'm going to run this now, and if we take a quick look at our vector v, we notice we only have the values 1, 2, and 3. So this should return false because none of them are greater than 5. And it does return false. Now let's do the same thing on the array of ints a. So to do this change, I'll remove the v.begin and just put in begin and pass it a, and then change v.end to end with a. So I'll save it and run it again, and you'll notice that it works just the same, but in this case it does find a value greater than 5 because it's a different set of values, and if we look at our array of ints, we have all of these values greater than 5, so it does return true as expected. And that concludes this demonstration on using non-modifying algorithms with standard library containers, including just a basic int array. The standard library provides a number of helper functions to efficiently move elements from one container to another using iterators. In this video, I'll present how to use iterators to copy and move in C++. So for this demo, I'm including iostream, string, list, dec, and iterator headers. So we're using the standard cout, list, string, dec, back inserter, front inserter, and make move iterator in this demo. So let's have a look at our main function. I start off by creating a list of strings. So list string ls equals this following list of strings. So 1, elbow, blue, toad, galaxy, and socks for no particular reason other than having a random list of words to use to demonstrate our copy and move. Now in this first part, I'm going to copy a list of strings to a double-ended queue of strings, or a deck of strings. So I have dec, parameterized by string, and I'm calling this deck of strings ds. So when I call copy, so I do a copy from ls.begin to ls.end, so we're going to copy the entire list of strings to our ds, our deck of strings. But we're using the back inserter to do so. So all the elements that get copied will be inserted to the back of our deck of strings. So we do back underscore inserter, and in parentheses, we provide our ds, our deck of strings. Then we're going to create another list of strings called ls2. But we're going to move the values from our deck to our new list of strings. So to do an actual move and not a copy to this ls2 constructor of list of strings, we do a make underscore move underscore iterator. And this make move iterator takes a beginning iterator or any iterator as an argument. So in this case, we're giving it ds.begin, the beginning of our deck of strings. Then we make another move iterator and we provide ds.end. So this provides a range, an iterator range to construct our list of strings. Now, since this is a move iterator, when values are copied to our list of strings, they're actually removed from our deck of strings. So then we output the contents of our list of strings ls, our deck of strings ds, and our second list of strings ls2. Then after our copy, then our move, our deck of strings ds should be empty, and the contents of ls and ls2 should have the following strings, so the list of strings. So let's compile and run the code to make sure it works as expected. So if we look at the contents of ls, it just has the string it was initialized with. I'll move the output window to the side, and just so we can see the list. So 1, elbow, blue, toad, galaxy, socks is in ls. ds is empty because we took all of its values and we moved it to ls2, which has the same contents as our original list of strings ls. Now I'm going to make one small change, one interesting change. Instead of a back inserter, since we're dealing with a double-ended queue, we can use a front inserter. And you might take a moment to guess what might happen when we do this, but I'm going to compile and run the code now, and we can see that our elements get put into our deck of strings slightly differently, and that change will be carried down to the move iterator. So our contents of ls2, when we run it again, will be slightly different. So in this case, when we use the front inserter, our elements are in the reverse order, because as they're copied, instead of being appended to the end of the container in the double-ended queue in our deck, they're appended to the beginning, so they're inserted at the front. So instead of our variables 1, elbow, blue, toad, galaxy, socks, we have it in the reverse order. Socks, galaxy, toad, blue, elbow, 1. So all of the elements are there, but they're in the reverse order. And that concludes this demonstration on using iterators to copy and move in C++. In this video, I'll present the replace algorithm from the standard library in C++ to replace characters in a string and elements in a container. So for this demo, I'm including IOStream, algorithm, vector, and string. So we're using cout, replace, vector, and string from the standard library. So if we look at the main function, I start off with the character replacement example. So we create a string s equal to the string 2018-01-01. So we have a string in a standard ISO 8601 style format. So what we do with replace is we give it an iterator with the range of values from the string we'd like to replace in. So in this case, we're just going from s.begin to s.end. So from the beginning to the end of the string, we're going to replace the character hyphen with the character underscore. So the hyphens after the year and month get replaced by underscores. And we'll output s to verify the change. Then for replacing elements in a vector, it works almost the exact same way. So in many cases, the string in the standard library works much like a container of characters, like we have here with our vector of ints. So we just have numbers in this case instead of characters, so 0, 1, 2, 3, 0, 8, 4, 4, etc. So we have this list of integers. So with our vector, we do the same thing. We call replace with v.begin and v.end as our range of values, and we'd like to replace anywhere we see the number 0 with the number 1. So these 4 zeros in the vector will get replaced by 1. And then we output the contents of our vector v to verify that this change was made successfully. Along with replace, we have the replace if algorithm. So replace if works much the same way, but instead of taking a pair of values, it takes a function or a function object or a lambda expression. Some function or some way of having code that performs this replace, but it does it on an if condition. So what we do is give it the beginning of our vector, or so v.begin to v.end. Then we have a function, in this case a lambda expression, which takes an int, and it returns the int. So it takes the int I, does a mod 2, and compares it to 0. So if I mod 2 is equivalent to 0, it means the number is even. So what it does for every even number, it replaces the value with -1. So all even numbers in our vector of ints will be -1 after this replace if. And then we output the contents to verify the change. So we'll do a Control F5 to compile and run our code, and we'll verify our results. So if we look, our date that was in ISO 8601 with hyphens now has underscores. So we have 2018_01_01. Our list or vector of ints had 4 zeros in it, and those were replaced by 1, so there are no longer zeros in our vector of ints. Then we do the replace if, where we had a function that determines if a number is even, and if it is even, it replaces it by -1. So if you look at the output, the list of numbers here, we have 2, 844, 34, 22, and 2 as even numbers, and they're set to -1 in the final result after our replace if. And that concludes this demonstration on using the standard replace in C++. In this video, I'll list the modifying algorithms for use with containers in the C++ standard library, and I'll demonstrate one of them with a short example. So the lists are as follows. We have the transform modifying algorithm, copy, copyIf, copyN, copy backward, move, and move backward, unique and unique copy, remove and replace, reverse, rotate, random shuffle, partition, and stable partition, next permutation, previous permutation, is permutation, fill, generate, swap, and iter swap. Now the one I'm going to demonstrate is random shuffle. So I'm including at the top of my program IOStream, vector, algorithm, C standard lib, and C time. So we get our random shuffle from the algorithm header. We're going to be random shuffling a vector, so we've included vector. And we're going to seed our random number generator so that random shuffle is different every time. So we're using the cstdlib and ctime for srand and time. So srand will seed our random number generator. And then I have that as my first line in the main function to make sure that we get a new seed every time we run the program. That'll be based on the system clock, so we need to call time. So srand takes an unsigned int as a parameter, but the time function returns a time underscore t. Now, in every implementation that I know of, time t is an integral type, but just to be strict about it and be safe about it, it should always be cast as unsigned, so that srand is definitely getting an unsigned int. Time also takes another time type, a time underscore t pointer as an argument. Now, quite often you'll see time called with the number 0 or with null. But in C++, in modern C++, we should be passing null pointer if we want the current time. So this is, as it's written here, is strictly correct for modern C++. So we have srand with an unsigned cast and a call to time with a null pointer as an argument. Now I have a vector of ints v set to the values 1, 2, 3, 4, 5, all the way to 9 plus 0. So we have these 10 numbers from 1 to 9 and 0. We call our random underscore shuffle, and it takes two iterators, a range, so the beginning and the end. So we do v.begin for our lower bound and v.end for our upper bound. So that will shuffle the entire vector of ints. And then we output the contents with this for loop. We loop over contents of our vector v and output the value delimited by a space. So that's all there is to random shuffle, and if I do a Control F5 and compile and run it, we should see our vector of ints v in a shuffled random order. So if we look at the values, they're much different than what we had. So we have like 2, 4, 0, 9, so they're all out of order. But if I stop it and I run it again, you'll see the values are different. So this one starts with 4, 5, 6, 5. Because I'm seeding it with the time, each time I run the program, it will give me a different shuffled order. And that's probably what we'd like. And that concludes this demonstration on using modifying algorithms with containers in C++. In this video, I'll present how to use the standard sort expression in C++. So we get our sort expression from the algorithm header, which I've included at the top of the program, along with iostream, vector, string, and functional. So we get to use the standard cout, vector, string, sort, and the comparators from the functional header, less and greater. So in our main function, I start off by creating a vector of strings vs. And these strings are just individual characters, but they're strings, so there's double quotes around them. And what we'd like to do is do an alphabetical sort on this list of strings. So we call our sort function from the standard library algorithm, and then we give it a begin iterator and an end iterator, or a lower bound and an upper bound we'd like to sort. So in this case, vs.begin and vs.end is our bound, so it's the entire vector of strings. And then we're going to use the comparator less. So that will sort it from least to greatest. So the comparator has to be less, parameterized by string, and we give it these parentheses. So it uses this as our sorting, how we compare the elements in our list. Now just below this, I'll show you how to do it in the reverse order with greater. So in this case, we'll get an alphabetical sort, and we output the contents using this for loop. So we output each string, or in this case, each character string, delimited by a space, and then we do a double carriage return before the next example. And in this case, in the second example, we're going to do a numerical sort from greatest to least. So we have a vector of ints v set to the following unsorted list of numbers. So these are values from 1 to 10. And again, we call sort. In this case, we give it v.begin for our vector of ints and v.end as our upper bound. So we go from the beginning to the end of the vector, so we're sorting all of the elements in the vector. And the comparator we're using is greater. So we use this comparison object greater, we parameterize it by int, and then we use its function or its overloaded function operator with the double parentheses. And then we do a for loop over all of the ints in the vector and output the sorted contents, and it should go from 10 to 1 in this case. And then finally, we're doing a custom sort using a lambda expression to define our comparison. So instead of using the built-in ones or letting it be a default ascending order, we're going to sort the values in a custom way. So again, I'm going to sort the entire vector v, so this vector of ints, but we're going to use this lambda expression, which takes two ints, int a and int b, and it's going to return the results of their comparison. So it's going to return the a mod 2 greater than b mod 2. So what this is saying is that we're just looking at the odd and evenness of the numbers. We don't care about their values. So we want all of the odd numbers to come first and the even numbers to come second. So if a mod 2 is odd, it will be 1, and b mod 2 will be 0 if it's even. So it'll say that the odd number is greater than the even number in all cases. So we should end up with a sorted list with the first 5, in this case, in this particular vector, with 10 elements from 1 to 10. All of the odd numbers will come first, so the first 5 will be odd and the second 5 will be even. And we output the contents of the vector after that modification using sort. So let me compile and run the program now, and we can verify our results. So if we look at our list of characters, our strings, our vector of strings, we just have A, B, C, D, E, F, G, H, I, J, K, L. So all of the characters got sorted in alphabetical order. Then using the vector of ints and using the greater comparator, we got our vector of ints sorted from greatest to least. So 10 to 1. And then our custom sort using the lambda expression by just looking at the sign of the number, so whether it's even or odd, and making the odd numbers always greater than the even numbers, we get all of the odd numbers sorted first, and then the even numbers come after. So we have 9, 7, 5, 3, 1, and 10, 8, 6, 4, 2. Now the reason that they're in descending order in this case is because the previous list was in descending order. So if it wasn't put into sorted order first, the odd numbers wouldn't be in any particular order, as well as the even numbers. But it sorted it that the odd numbers got pushed to the front of the vector and the even numbers got sorted to the back of the vector. And that'll conclude this demonstration on using the standard sort, including an example with lambda expressions in C++. In C++, the standard library sort function takes iterators as arguments to specify the range of elements to sort within a container. In this video, I'll demonstrate how to sort a subsequence of elements in a vector using iterators. So in this example, I'm using IOStream, vector, and algorithm, so I'm including these headers, and we're going to use cout vector and sort from the standard library. Now in the main function, I start out by creating a vector of ints v with the following fairly random set of integers. So just some numbers I picked off the top of my head. And what this program is going to do, well, first it outputs the contents of v as they are to begin with. So the initial contents of v, we loop over the elements in the vector and we output the integer followed by a space. So we get a space delimited list of our ints in v. And then we do a double carriage return, and then we're going to sort a subsequence of this vector based on the values from 6 to 8. So we're going to do a find to find the value 6 and a find to find the value 8, and we'll use that as the start and upper bound of our subsequence that we're going to sort on. So what I do starting on line 16, I have an auto itr underscore start. So I auto declare this variable because it's an iterator returned by find. So we want to start at 6. So it's going to look in the entire contents of our vector from beginning to end for the value 6. And when it finds it, it will have an iterator to it. So itr underscore start should be pointing to the 6 after we call this. Then we're going to look for an upper bound to our sorting subsequence. So instead of starting at the beginning, well, we're just going to start at our itr start plus 1. So we're going to start at the 10 and look through the rest of the vector for the value 8. So in the find call on line 17, it returns an iterator itr underscore upper based on the range from itr start plus 1 to the end of our vector, looking for the value 8. So if we look in our vector v above, we can see the 8 is here, and the entire range is what I've highlighted, 6, 10, 1, 7, 9, 8. Then we're going to call sort. But remember sort, the beginning, the itr start in sort that we call in sort, it will include that. So the start 6 will be included in our sort. So we sort from the 6, including the 6, until the upper bound where the 8 is, but it's not going to include the 8. That'll just be our upper bound. So we're just including the values from 6 up until 8, but not including 8. So that's our start and upper range. And then we call the sort, so we sort that subsequence, and then we output the final contents of v to see if that subsequence is indeed sorted in ascending order. So I'll do a Control F5 to compile and run. And I'll move this output window to the side so we can look at the results. So the initial contents of v is just what we initialize our vector to. And then the final contents, we just have to look at the values from the 6 up until but not including the 8. And we have to make sure that they're in ascending order. So the 6 was our third integer, and that gets replaced by 1, so we have 1, 6, 7, 9, and 10, and those numbers are indeed in sorted ascending order, so it worked as expected, and we were able to sort this subsequence in this vector of ints. And that concludes this demonstration of using iterators to sort in C++. In this video, I'll present how to use the standard library sorting with different containers in C++. So in this video, I've included IOStream, vector, dec, and algorithm so that we can use cout, vector, dec, and sort in our example. Now, the important thing to remember about algorithms from the standard library is that they don't take particular container types, nor do the containers implement the algorithms themselves. The data structures are kept separate from the algorithms. So algorithms don't take containers as arguments, they take iterators as arguments to specify ranges of elements inside a container. So we operate on the whole container with an algorithm by giving it the begin and end iterators as our lower and upper bounds respectively. So that's what I do in this example. I have a vector of ints v, which I initialize to the values 5, 3, 1, 4, 2. And then we call sort on this to put it in sorted order from least to greatest. And to the sort, we're not just specifying our vector v as an argument, we pass v.begin and v.end as our lower and upper bounds. So it sorts all of the elements starting at the beginning up to, but not including, v.end. And then after we perform the sort, we output the values. So for int I colon v, so all of the ints I from our vector v, we output the value followed by a space. So it will give us the contents of v after we've sorted it, delimited by a space. So let's compile and run to make sure this version of the code works. And so we get our values 1, 2, 3, 4, 5. So our vector v was sorted correctly. Now, one of the neat things is that sort is not tied to any particular container type. We could easily replace vector with dec, D-E-Q-U-E. So we have a deck of ints, and I've made that change. I'll compile and run again. And again, we should get the elements in sorted order because we've only changed the container. We didn't have to change anything to do with our iterators. The sort function doesn't change. We can still loop over the elements with a for loop in the same way, so our for loop doesn't change. Now, one of the neat things is, with a minor modification, we can change this from a deck of ints to a int v, so an array of ints v, but v is just an array of ints, so it doesn't have a begin and end member function, so we can just remove the v.begin and change this to begin v and end v. So if we want to use the begin and end iterators, we'll have to add it because these functions come from the standard library, so we're using the standard begin and standard end so that we can have an iterator into just a plain old int array from beginning to end, and it will treat this int array almost like we would a built-in container in C++. So we can sort a basic array using the standard library algorithm without a container, but just a basic array of ints. And let's run this just to make sure it works correctly. So I'll do Control F5 to rebuild it and run it again. And you'll see we get the same result, 1, 2, 3, 4, 5, with a very minor modification to our code. And that concludes this demonstration on using sorting with containers and a basic int array in C++. In this video, I'll present how to use standard library sorting with a vector of custom objects in C++. So we start out by including iostream, algorithm, string, and vector, so we can use the standard library cout, sort, string, and vector. So the custom object we're going to be using for our sorting is our class record that I've created here. So we have class record, and we declare a public section for our int id and string value. So we have these two member values, id and string. We have a constructor record that takes an int I and a string s and initializes the member's id and value with those. And the most important part of using a custom object with sorting or any type of comparison with standard library algorithms is overloading a comparison operator like our less than. So we overload the less than operator, which returns bool and takes a const record reference r as an argument, and it's important that this function be const as well. And then we just return the object's id comparison, so id less than r.id. So it'll compare the two objects so that the sort can decide what order to put them in, and it will be based on the id parameter. So now in our main function, I create a vector of records v, and then I call a number of pushbacks on our vector v, where I create a record, and the first one I give it 5 as the id, and the string 5, five, as the string. So we have 5, 1, 3, 2, 1, and the string literals 5, 1, 2, 3, 2, 4 as our strings respectively. So now we output the contents of our vector of records in original order, outputting the id, comma, value, followed by a carriage return. And then we do a sort from v.begin to v.end, so the entire vector of records gets sorted, and it's based on the id. And then after the sorting, we output the new contents of our vector to see that it's in sorted order. Now let's compile and run the code to make sure it works correctly. So the original order is exactly how I pushed the vector or the records onto the vector, so 5, 1, 3, 2, 4. And then after sorting, we get 1, 2, 3, 4, 5, as expected. Now again, the most important point here is the custom object overloads the less than operator that sort can use to put our records in the correct order. And that concludes this demonstration on using the standard library sorting with custom objects in C++. The standard library merge algorithm takes two sorted sequences specified by ranges of iterators and merges them into a single sequence. In this video, I'll present how to use the standard merge in C++. So we start out by including iostream, vector, string, and algorithm in our headers, and we're using the standard cout, vector, string, and merge in our examples. Now in the main function, I start out with two vectors of strings. So a vector of strings, v1, set to the strings Bob, Steve, Joe, Alex, and William. And then our vector of strings v2 contains Jane, Sally, Allison, Pamela, and Emily. So one of the important properties of merge, or one of the important caveats when dealing with merge, is that it takes two sorted sequences. So if we want to merge our v1 and v2 into a third sequence, then v1 and v2 have to be in sorted order. In this case, in sorted alphabetical order. So we sort v1.begin to v1.end and sort v2.begin to v2.end. So this ensures that v1 and v2 are indeed sorted. Then we create a third vector of strings. So we have vector string v3, and then as our argument, we give it a size. So v3 will contain the merged elements of v1 and v2, so we give it a v1.size plus v2.size. So it's going to be large enough to contain all of the elements from both vectors. Then we call our merge. So we merge v1.begin to v1.end and v2.begin to v2.end. So that takes care of our first four arguments. So we have the lower and upper bound for our first vector, the lower and upper bound for our second vector specified by iterators, and finally a place to insert the merged result. So the last argument, the fifth argument, is v3.begin, because we're going to start inserting at the beginning of our vector v3. Now there's no requirement that it has to be at the beginning of a vector. It could be an iterator to anything else, as long as there's enough room where we start inserting to insert all of the elements from the merge. And then we output the contents using a for loop to see the final vector of strings, the merged contents, delimited by a space. So let me compile and run this so we can have a look to see the results. And then we get our merge results in alphabetical order. So we have Alex, Allison, Bob, Emily, Jane, Joe, Pamela, Sally, Steve, and William. So our merged vectors in sorted order, done by the standard library merge. Now what happens if they're not in sorted order? So let's comment out the sort of v1 and v2. So we'll end up trying to do a merge on an unsorted vector, two unsorted vectors of strings. So if I compile and run it again, we get an error. So the application actually crashes. So it's very, very important that you're only dealing with sorted sequences when we're doing a merge. And that concludes this demonstration on using the standard library merge. The standard library includes algorithm returns true if all elements from one sorted sequence are contained within another sorted sequence. In this video, I'll present how to use the standard includes algorithm in C++. So we start out by including iostream, vector, and algorithm. So we're using the standard cout and bool alpha from the iostream header so that we can output the results of includes as a string true or false. Now the sequence, or the sequences we're going to be looking to see if they're included, are going to be vectors. In our example, vectors of ints, so I'm using the standard vector. And then we're also using the standard includes and sort from the algorithm header. Now it's very important that we include the standard sort because the includes algorithm requires that our sequences be sorted. Okay, in our main function, we have a vector of ints v1 that's set to 2, 3, 5, 7, 11, 13, 17, and 19, and v2 of another vector of ints v2 set to 5, 7, and 11. And you'll notice right now that 5, 7, and 11 are contained in V1. So if we look to see if V1 includes the elements of V2, we can see that it does indeed include the same some of the same elements. So the 5, 7, and 1 are included in V1. So we should be able to verify that. Now, if we look at the integers, you'll see that they're already sorted. So we don't really need to call sort explicitly, but just to be safe, we'll do it, and we'll show that if we move elements around and we don't sort it, it will cause problems and often cause our program to crash. So it's very, very important that our vectors be sorted before calling the includes function. So on line 16, I create a bool called doesInclude, and it's equal to includes, which takes 4 arguments. So we have v1.begin and v1.end. So that's the lower and upper bounds of our first sequence, and then v2.begin and v2.end as the lower and upper bounds of our second sequence. So we're looking to see if our sequence specified by v2.begin and v2.end are contained in the sequence from v1.begin to v1.end. So then we do a cout of bool alpha on the doesInclude variable, and in this case it should return true because 5, 7, and 11 are contained in v1. So Control F5 will compile and run the code, and it does return true. Now if we modify this slightly, one thing we could do is change the order. So instead of 5, 7, 11, we do 11, 5, and 7. Now, the way I have it here, it should work just the same. So if I do a Control F5, it will sort V2, and it will be just like it was before. Now, just to prove this, so you don't have to take my word for it, I'll do a quick compile and run, so we can verify that that is indeed true. And it is, so it does work. But if I remove the sort, let's remove both sorts, and we'll move a couple of elements around, so we'll make sure that it's not in sorted order, but it will contain the same elements. So in this case, both of these vectors are not sorted. I've commented out the lines that did the sort explicitly, and we're going to call includes anyway. And this causes our program to crash, which is a very important thing to be aware of when we're using the standard library includes. So when the lists or the vectors or the sequences are not in sorted order, we run into major problems. So I'll just put that back in. And let's remove something. Let's remove the 7 from our vector v1 so that we can get a result with false. And in this case, it returns false because 7 exists in v2, but it doesn't exist in v1. And that concludes this demonstration on using the standard library includes algorithm in C++. In this video, I'll present how to work with standard library set operations for containers in C++, namely set union, intersection, difference, and symmetric difference. So these are typical set operations when dealing with sets of values. In this case, in C++, we're dealing with containers of values. So we're going to take these common set operations between two vectors of ints, and we'll look at what the results are and how these set operations are performed. So we start out by including IOStream, vector, and algorithm because the set operations come from the algorithm header. So we're using the standard cout, vector, set union, set intersection, set difference, and set symmetric difference. So now in the main function, I create a vector of ints v with the values from 1 to 5, a vector of ints w with the values from 5 to 9, and a vector of ints t which will contain the results of our set operations, which will have enough room with the size of v and plus the size of w. So it has to be able to contain at least 10 elements because v has 5 and w has 5. So t will have at most 10 elements. So that's how we initialize it. Now, our first operation is a set union. We do a set union on our first subsequence, so the start to the end, so v.begin to v.end, our lower bound to upper bound of our first sequence, w.begin to w.end for our second sequence, and where we'd like our results to be stored. So we'd like to start inserting them at t.begin. So we pass an iterator to store the results of the set union, and the set union function returns another iterator which points to the upper bound of our result. So the results will be contained in the container t from t.begin to the iterator p. So if we look at the set union contents, we take an iterator from t.begin and we iterate until we reach the iterator p, which was returned by our set union. And on each iteration of the loop, we increment the iterator and output the value with a space delimiter. So we do that for each of the operations. Now if we look, we have set union, set intersection, so the elements in common between the two sets, which in this case is just 5. Set difference, which is the elements that are in the first sequence that are not in the second sequence. So in this case, the elements in V that are not in W are 1, 2, 3, and 4. Because 5 is contained in W, it won't be included, so we just get 1 to 4 as the set difference. And the set symmetric difference are the elements that are in either but not both. So we'll have 1 to 4, it'll exclude 5, and then we'll have 6, 7, 8, 9. So let me run the code and we can look at the results of these 4 set operations and see the results. So I'll do Control F5. The set union, which contains the contents of both sets or both containers, we get the numbers from 1 to 9, and you'll notice 5 is only there once because it includes the elements uniquely. The set intersection, the elements in common with both, is the element 5, so that gets printed. The set difference is 1, 2, 3, 4, and the set symmetric difference is everything except for 5 because it's contained in both sets or both containers. And that concludes this demonstration on working with standard library set operations. In this exercise, you'll create a program that uses a non-modifying algorithm on a container in C++, that uses a modifying algorithm, that uses a standard library sorting, and uses a standard library merging with containers in C++. Now you can pause the video and perform the exercise, and when you've completed it, come back to the video and I'll walk you through what I did. Now here's what I did to carry out the exercise. So in my program, I'm including IOStream, vector, and algorithm. So I'm going to be performing my operations on a vector. And we're going to be using the algorithm header so we can use some of the modifying and non-modifying algorithms. So we use the standard cout, vector, sort, merge, all of, and for each. Now in my main function, I create a vector of ints v with the values 0, 10, 30, 20, and 50, a vector of ints w with the values 8, 4, 2, 6, and 12, and then a vector of ints t that's not initialized to any particular values, but it's initialized with a size, which is the v.size plus w.size. So since we're going to be doing a merge and merging the values from v and w, we need a vector that will contain the results of that merge that has enough room to hold all of the elements from both. So we carry out our sort because the merge requires sorted sequences. So we sort the values in our vector from v.begin to v.end, and the same with w. We sort from w.begin to w.end. So here we've ensured that v and w are sorted because that is required by merge. So merge needs sorted sequences. So it takes v.begin to v.end, and it'll merge it with w.begin to w.end, and it's going to insert the merged results starting at t.begin. So it's going to so t after this merge will contain all of the values from v and w. Now, one of the non-modifying algorithms I'm using in this example is the any of. So we're looking for any of from t.begin to t.end, and we're looking at the lambda expression that returns I mod 2 is not equal to 0. So what we're saying here is, are any of the values from t.begin to t.end, are they odd? So if any of them are odd, it will return true. If they're all even, it returns false, because I mod 2 not equal to 0 implies an odd number. So our bool b will contain that result, and we output the odd values question mark, and then the true or false, depending on what the value of b is. Now, a quick inspection on the values shows that there are no odd values in it, so this should return false. Another non-modifying algorithm that's commonly used is the for each function. So we have for underscore each, and we loop over the values. We do this for each from t.begin to t.end, so we're looping over all the values in t. And we have a little lambda expression that takes it into I and outputs the value with a space at the end. Now, I'm also going to insert something here that I didn't do previously, is a cout of a line return after this for each. And I'll copy this and do another one at the end of the program, just so we have a little extra space to work with. And then I call a modifying algorithm. Now, if you were clever, you may have thought, well, sort and merge are non-modifying and modifying, or our modifying algorithms, sort and merge, they change the contents of our vectors, so they are modifying algorithms. So the fill might be kind of extra, but I just didn't want to use the ones that I had requested, because I did explicitly say to use a modifying and sort and merge. So for a modifying one, I chose the fill algorithm, which takes the t.begin to t.end and fills all the results with 0. So after all that sorting and merging and displaying of the results, I erase our vector t by setting all of the integer values to 0. And then we output the contents just to verify that the fill did work by running the same for each on t.begin to t.end to output the contents after everything was filled to be 0. So now I'll do a Control F5 to compile and run, and we'll verify the results of this exercise. And if we look at the results, the any of returned false because there are no odd values in our list. The contents of our vector t after the merge contains all of the values, so 0, 2, 4, 6, 8, 10, 12, 20, 30, and 50, all in sorted order as expected. And after our fill, all of the values have been set to 0. And that everything worked as expected. And that concludes this exercise on using algorithms and operations in C++.